Hello. Good morning, ladies and gentlemen. I hope you all had a wonderful time yesterday and are ready for another insightful day at the 35th IARP National Conference on Radiation Protection for Sustainable Nuclear Energy, Adapting to Climate and Technological Changes. It is an absolute honor to welcome our esteemed speakers, distinguished guests, and enthusiastic participants to today's session. We have an exciting lineup of talks, discussions, and presentations that will surely add value to our understanding of radiation protection and its critical role in various sectors. To start the day, we have a plenary lecture on epidemiological foundations of radiation risk estimates, radiation protection, and risk communication by highly esteemed Professor Y.S. Maya. Before we have Y.S. Maya on stage, we would like to give a small introduction about Professor Y.S. Maya. May I please call upon Mrs. Purnima on stage.
Good morning, everyone. Dr. Y.S. Maya, visiting professor at IIT Bombay and former head of Radiological Physics and Advisory Division at BARC, has contributed to diverse aspects of research on aerosol science, electrodynamic levitation, radon monitoring and modeling, epidemiology, nuclear safety, radiological physics, and radiation protection over the past 50 years. His studies have nucleated several national programs in the areas of radiation epidemiology, nuclear aerosol research, radon and decay product monitoring techniques, and large-scale outdoor air cleaners. He has made several fundamental contributions in the respiratory risk assessment, charge particle and droplet dynamics, and spray drying technologies. He spearheaded theoretical studies on near-source aerosol modeling to address the question of number loading factors in the environment due to combustion emissions. His epidemiological studies on Indian atomic energy workers in the 90s remain the only real data studies on this topic in India. He has continuing to guide generations of students in pursuing research in the past several decades. He has co-authored 200 papers in referred journals. Professor Y.S. Maya was nominated an aerosol pioneer by American Association for Aerosol Research in 2018. He was a president of the Asian Aerosol Research Assembly from 2005 to 2007, member of editorial board of Journal of Aerosol Science from 2004 to 2014, and a recipient of K.G. Vovra Memorial Award in 2018. Now I welcome Professor Y.S. Maya sir on the dais, and we are handing over the session to him. Over to you, sir.
Thank you. Good morning, everybody. Thanks, young lady, for reading out so long about me. I hope it doesn't cut into my time. But thanks, and thank you once again. It's nice to hear about yourself a little. So, first of all, before I thank, yeah. So before I start, let me thank the organizers for giving this opportunity to me to speak on this subject, especially the President IARP, Dr. Anand personally said I must speak on this subject. Dr. Karunakar insisted that I must speak on this subject. It's so I couldn't refuse, so I said I don't have much new in this, but as a part of recounting the story of health, safety and environment, I thought maybe it's worth doing it, so I will be recounting that. It's a great pleasure for me to be here for many, many reasons. One, of course, this is my alma mater, and I am born in this place. This is the great ancient Tulnad. It's nice to come and speak in this land of mine, from where I got my education in doing science or inspiration to do science, those school teachers who guided you. And also this august audience, it was a pleasure for me to recount seeing mentor generation of Dr. Siddhappa, Dr. Raghavaya. It was nice to see colleagues of my generation, like we have Pradeep. I saw Pradeep there, Dr. Pradeep, then Dr. Ravi, and some others. And also to be here to see all the youngsters with whom I interacted in the university, like Karunakara. It's a, after I retired, the only connection I had on radiation was through Karunakara. We used to interact with the students, like Sudeep is there, Mohan is there, Nayak is there, student. So it was a pleasure for me to continue the research on radiation through him, and I really thank him for that. Take this opportunity to acknowledge that fact. And also, it is a great pleasure for me to see my colleagues, younger colleagues in HSCG, a generation down the line with whom I worked very intensely in those young days, like Vinod Kumar, then Woza, and Prabol. This is a kind of a feeling that it sort of rouses those old emotions when we lived. And also it is satisfying to see your own students today rise to the level of division heads, like Balvinder is there, Woza is there. So somewhere you feel there is, maybe you have done something in training people. So thanks once again for all these reasons to be here. And also, that generation when we worked on radiation, we also spread the technology to outside. And when I see Dr. Reddy sitting here, I remember the days when the first software for analyzing glow curves was created by the collaboration between Nambi and Dr. Reddy here. Today is a big technologist, he has a big industry, but somewhere it was instituted by the great outgoing spirit of people like Dr. Nambi. So with this, let me come to the topic per se. So I'm using words like epidemiological studies. I really don't know how many do think it is a science today, but we firmly believe that it was a science. It's a very respectable science the world over. So radiation epidemiology is a very respected subject. The reason why it is important is that we as professionals, we are trained for speaking with precision. Whatever statement we make, there are two levels of approaches. If I have to communicate to a public, you have to communicate in a certain way. But that public communication cannot be half-truth. It has to come from a very rigorous scientific basis. And we as health and safety professionals are asked to focus on that science, to create that science and carry forward. Epidemiology tells you the question of whether radiation is harmful or not harmful is a binary question. How you communicate to public is a different matter. It's a matter of English language. It's a matter of connecting it with the political views, socio-economic factors of the society. But as professionals in health and safety group, we are proud to have created it scientifically. So we don't simply ask a binary questions, we ask statistical questions. Because if somebody asks radiation is harmful or not, I will simply say, okay, at what level you want to listen? What is the mean? What is the concept you are going to introduce? So I'm going to discuss some of those inner details which go into it, on which all the public speaking has to originate and emerge. That's a different art together. But our job is to get at the truth, and this is the perspective which we learned from the foundation. See, this is what I want to bring in. So when we speak of Dr. Ganguly, I was there for 3 years when he was a director, an enormously scientific person, a person who liked precision. And he, the conflict between the management and health physics is ancient, right from day one. I was from plutonium plant, so it's always there. So there will be always complaints against the health physicists. They're not allowing us to do our job. They're unnecessarily putting obstructions. Nowadays, it may not be there. It's much better. But in the olden days, all arbitration, everything was within BARC finally. So it was Ganguly who would always say, safety, they're doing the job that they're designed to do. They have to excel in their profession. They have to develop the best instruments, detect radiation as level as possible, and if ALARA has to be stuck to, it is the instruction given to them. They have to stick to ALARA principle. So now why and what of it is second level of knowledge. It has to come separately. So that was the founding with Ganguly, and specifically epidemiological studies were started by Dr. Soman and Dr. Nambi as a part of providing scientific basis for public speaking and public awareness. And as I will tell you along, there are reasons why this was started. So I am basically indebted to these people for inculcating in us the spirit of scientific professionalism, not just loose talking, but to be able to talk with numbers, with the bounds, and how to calculate the bounds, and how to do the correct statistics. Without statistics, there is no science. Everything has to be countered with an error margin. No paper will be published if you don't give your error margin, for example. Similarly, you can't speak of risk without a 95% confidence limits. So this is the way it has to be understood. And so I would say this entire radiation protection is a very noble discipline. It is noble because it gives you opportunity to explore your subject in a homogeneous and synergistic interaction with many disciplines. If today I am speaking and I am very comfortable with the chemical engineering discipline, talking to chemical engineers and they respect you, it is because of the fundamental graining in safety that you have ingrained in health and safety group. Some problems of health and safety group are of that type which required chemical engineering precision, like aerosol science. That gives you science. Similarly, some other problem in health and safety requires chemical understanding, very good chemistry. Entire dosimetry is based on solid state physics. Munish is there, I'm sure he can give a lecture on that. So you see that every discipline of dispersion modeling requires extremely good fluid mechanics. So all these disciplines finally come in one place, and I personally feel honored and lucky to have been in health and safety group because I could pursue many areas after my responsibilities are over there. So that is one of the reasons. And epidemiology is one such discipline which again comes from medical science but becomes important for giving meaning to the quantities we are using today. So in the next few minutes, I am going to cover these aspects. Let's come to the topic. I'm sure most of you know, and also let me tell you, I have nothing new in this. I am basically trying to inspire I won't say inspire, maybe that's too much of a word. I would like to put it across to the young generation to see whether some studies can be revived. Epidemiology is a serious business, and every nuclear program should do it because we can speak whatever we want to speak, and you want people to listen only if you have done an analysis yourself. Otherwise, you will be only reading from books and talking, and you don't get respect, and your own people it will not probably help public awareness. Now, coming back to the question of radiation limits, we all know these numbers, of course, 20 millisieverts and 1 millisieverts, all, again, over and above the existing background. You must always say that because many times it is forgotten. So, and what is the basis of this? It's based on actually risk projection modeling. I agree, it's a model based. So again, the numbers, 4%, it's approximately 4, it has a variation for worker, and 5% for public, encompassing a risk of 10 to the power minus 3 of death per year is the kind of comparison with other industries. Nuclear, how do you compare with other industries? Truck drivers' risk, for example, it's another industry. So to compare, you have to bring in everything to some risk coefficients, and that is what it is. Now, the basic logic for it comes from a concept called, I don't know if this works. Anyway, basic concept called primary risk coefficients projected onto a population. ICRP has generated, I'm speaking of ICRP 60. The days when we did the epidemiology, and it generated the attributable risk death probability curve for various ages of exposure, various levels of exposure, and then at around 20 millisieverts per year for exposure between 20 to 65 years, the risk is coming to be 1 in 1,000, which is a safe industry risk. So you go ahead. That is how the limits are set. So that is the logic used again for 1 millisievert per year. It is 1 in 10,000 per year kind of a risk, and that is achieved when you have about 5 millisievert, when you have 1 millisievert per year for a Western population. This is again for a population whose longevity is long, baseline cancer risk is high, projected cancer risks are high. But they had made calculations based on what is best. So it is the recommendations. Countries are free to implement it, not free to. It's entirely your choice. But this is the recommendation from the Commission. So what I want to say here is the primary, therefore, question here is what are the primary risk coefficients? So when we say there is no harm from radiation, I will ask, what are you trying to say? Your ERR is less than 0.1 or more than 0.4? My question is going to be of that type. Scientifically, when we speak, simply saying there is no risk is one, of course, very qualitative way of speaking. It is nice in general public, but professional, if I ask, go to UNSCAR and ask, or an epidemiologist you ask, he will ask this question. So are you saying it is -1 or +1 or 0.4, some number? And what is your confidence interval? So this is what epidemiology does. So exactly like radioactivity counting, if you have to certify a food and say there is no radioactivity or there is radioactivity, what do? You say below detection limit. As a professional, you write BDL. Somebody interprets it as no radioactivity. That's another level of communication. But whole science goes into whole of Poisson statistics, type 1 error, type 2 errors, everything goes in deciding on your BDL. So epidemiology is a kind of a covering science which provides that. So as I mentioned, this is the primary risk coefficients for solid cancers as well as leukemia for males and females. All this I will tell you how this has come. But this is the key $1,000,000 issue on which we are talking. It is not the 5% per sievert or 4% per sievert. It is the ERR, the excess relative risk coefficient of 0.4, for example, is what we are debating. Is it 0.4 or 0.1 or -1 or +1? That has to come from data, the empirical science of epidemiology. Now, when this is projected over to a population, you get the risks at various, lifetime risks at various ages. If a person suffers an acute dose, then do a mathematical projection and one arrives at that population averaged value of 5% per sievert. That is what ICRP has demonstrated, and that is a methodology. This one now gives us an idea of saying, okay, I assume my primary risk coefficients are same because it's a very difficult thing to get that data. I can now tweak or work on a number of real risk for my population because my population is not Western. My population has its own cancer rates. Our people die of other causes at the age of 63 in those days. Now it is 68, I think, expectation of life. So cancer occurs after 70. So maybe I don't have to worry that much about cancer. It may not be 5% per sievert in my case. This kind of questions were asked. To address that, we actually took up epidemiology. Nambi, in fact, Nambi and Soman said that will be a very nice way of illustrating that we have a huge safety margin. So for that, of course, you have to go through some, I will introduce a kind of jargon, mainly for young people. If you want to pursue this, what are the concepts on which these are based? The concept of attributable conditional death probability rate, the death probability rate for a person living at that age. So it's age dependent. So if you are exposed to a sievert, what is the extra risk you are facing at age 60, let us say, if you are alive? Unconditional or attributable, which means the probability of risk equal to probability that you are alive and the probability of conditional risk. So joined together. If you have died of other causes, there is no risk. So that is called unconditional death probability rate. So the curve we saw previously was unconditional death probability rate. Includes the survival, it includes the survival probability SU, and then of course lifetime probability of death, which is the 5% number that comes, which is denoted by R sometimes, and sometimes the ICRP uses Q dot here or something and P dot here, but for simplicity we have been using P and Q, where SU is the survival probability at age U since age 0. For workers, it will be SU 18 because you should survive the age 18 to get exposed in any case. So that is the way it was done. So what are the various requirements to project the risk from ICRP to your population? First, you must have a so-called demography, the survival rate. So this is the survival probability curve. That comes from the death probability curve, and Europe has huge data on death probability curves accrued over, of course, here it is 1950, but they had data from 1750 onwards. There is a great universality in this shape. It is in fact called e to the power 6 curve. This curve goes as u to the power 6. U means age to the power 6. But there is a pattern, whether it is 1950 or 2017, the lowest curve, you can see the shapes have remained unchanged. This region is called juvenile risk-taking region, where there is a sudden increase in slope here. Youngsters always tend to take extra risk in life and they die. Earlier it was horse riding, delivery for women, horse riding for men, now motorcycle for, and it ultimately is manifest here in this. So shapes have remained, and mathematically it is represented by Gomper's curves, but for our purpose we have to integrate it to obtain the so-called survival probability. So expectation is somewhere the average of this curve, 63 would come in this, but you can see the Western Swedish population, everybody lives up to almost, today it's 90 or so. So people almost live up to 90, almost everyone. Whereas in India it's 68, it's still a great leap in our society. Our grandfather's era, it must have been just 45 to 50 years, average people live. So cancer risk increases with the age. So more expectation you have, which is good, of course, which shows your nutrition is improved, but risk projection, it works the other way. Then about the cancer mortality curves, which you need again, because most of the risks are expressed in relative risks. They are not absolute risks. So Japanese A-bomb survivor data, the primary data is relative. Relative means you have to multiply by the background existing radiation, existing cancer. Radiation adds to that after multiplying with the baseline. So this baseline is, you can see the Western population is the black curve, dotted is the Indian population. Leukemia you always separate because of the high, low latent period and high risk. So you generate these two curves. We had less cancer risk for males, high for Western. This is a logarithmic graph, by the way. So factor of 2 margin straight away comes here. Then you, of course, there's a very interesting concept called world standard population, because every country has its own population structure. You can artificially tweak your number to say what you want by not adjusting to the fact that your population, for example, basically consisting of very young people, whereas somewhere else the population has a lot of old people. Apparently there will be lot of cancer there and very less. We cannot say we are very healthy people, we have less cancer, because nobody lives up to that age. So to adjust the risk to a world standard population is constructed. This is a mathematical construct, but normally everyone projects onto WSP and calls it as standardized mortality rates. So you will see these words, then it is always done over WSP. So with that, these kind of conditional curves are constructed, and you can see there is a margin. The Indian, so this is both conditional and unconditional. Let's look at males here. You can see this is the unconditional curve for ICRP, the Indian conditional curve. We didn't have much data above 75, so that is where it is less. More or less, you can see a factor of 2 margin existed, and this is of course the unconditional curve after multiplying by SU, and all this was projected to the Indian population. So this is a kind of risk transfer exercise. Then the summary. I think Pradeep yesterday mentioned that we have a list, actually half the risk, which is true. It comes from a calculation like this. So if the ICRP coefficient gives a lifetime probability of cancer death for 1 millisievert per year of protracted exposure. This is not acute exposure, protracted. Then if Western ICRP number was 0.4, we have about 0.18. This was in 1990s story. It could be different today, but I'm just telling you this is the way it is to be done anytime. And similarly, you can see, Indian is about 0.2, and there are various other metrics, lifetime probability of cancer death, assessed at age 18, and there are other metrics, like for example, life expectancy loss is one metric. The LLL, it is called loss of lifetime if cancer death occurs, is a very important metric in assigning the limits. All this is being considered judiciously, weightage is given to all these metrics. So you can calculate, once you have a recipe and protocol of how to do the risk projection calculation, you can just, maybe there are softwares today which do it, but in our time it was all done by hand. It gives you a lot of experience to do it yourself also. So that is how do you do a projection. There were many other projections we did, but this is some summary of how we did. The source of all this, as I mentioned, are the primary risk coefficients. And these primary risk coefficients, as I just projected already, they give you a unit called ERR per sievert, excess relative risk per sievert. So when you talk to any real professional of radiation risk, he will just, if you make any statement, he will just ask, what are the ERR you have got in your study? Then of course we will not have much to say. So that is where we have to say, we have to start our study. I'm again repeating the same thing, but that is the kind of spirit behind this concept. So the ERR that was used for ICRP 60, which is the basis of 20 and 20 millisievert on an average per 5 years, I think, and even today 1 millisievert, comes from basically an downward extrapolation of, I agree that about a sievert dose, more than 500 millisievert dose, but studies were not there at that time below 500 millisievert. Today it is not true. Japanese A-bomb survivor also had large population who have received less than around of the order of 100 millisievert. So that analysis is done. 2012, large number of papers, I think some of them I may show, have done this job. So it is not fully correct to say that A-bomb survivor is all high dose, which was true at the time of 90. But we must educate ourselves and read the more latest studies, take a balanced view of the whole subject. And so at that time, because there was no data, and from animal experiment studies, they knew that the risk is actually non-linear slightly, with the linearity at the base, but otherwise in between a non-linear quadratic relationship. So they did another slope of factor of 2 less. They reduced it by a factor of 2, whatever risk. So that is called DDREF, dose and dose rate effectiveness factor. It's called DDREF, and number 2 was used. Again from animal experiments, definitely, not from epidemiology, animal experiments. There are many objections, right? In the 80s itself, this was discussed. Today, yesterday, whatever I was hearing, there was really nothing new. 90s, definitely this matter was debated like anything. Oh, you can't use atomic bomb survivor data for our radiation protection. It is based on acute exposure. Ours is chronic exposure. And they're calculating the risk on people who have survived the trauma of nuclear bombing. So they're basically strong people. They're not general population. So you will find very less risk in them. Whereas we are irradiating, we could be irradiating our much general population. So maybe radiation is more dangerous. There are groups like that. In fact, that's called the Kaufman group. There are, I don't remember the full name. There are so-called super linear lobbies, very strong, who are saying that LNT is wrong. It is actually super LNT. So this kind of debates were very common. And another objection is, of course, linear versus non-linear. This is even now going on. All these objections existed. But then scientifically, we have to take the best path, and that is how the whole thing came. Now, it is true that if you have a data here and a data point 0, always 0 equal to 0 is 1 point always, there are infinite ways of joining it. So you can join it supralinear, as that, I'm forgetting the name, Roshman or somebody did it. He in fact demonstrated the entire Japanese A-bomb survivor data can follow the supralinear graph, which was later rejected by statisticians, but there was a graph. And then there are sublinear models on which the threshold model also come. This is being tested even today. It is not that epidemiologists are not aware of it. Every data is being tested for the so-called protective effect and hormesis. But it should satisfy the bounds. It should satisfy the meta-analysis. Meta-analysis is like the election forecasting, they do results one day before. What are exit polls? One poll, 8 polls, they average and give you a number, right? And then give you a bound. So it's exactly the same statistical procedure is allowed. You should do a meta-analysis of all the epidemiological studies before you come. So normally you will see some 8 such studies, whatever, some averaging is being done. So, but then there are many reasons why the straight line is chosen as the best option, because that is the most sort of conservative. We all know that it's easy. Otherwise, you have to measure the dose rate of a person along with dose. If it is non-linear, then dose alone you will not do. The effect depends on the dose rate. Your health physics is going to be more complicated. Right now, we have to only give sievert annual dose, and that seems to be simpler. That was the thinking behind. It's actually to facilitate nuclear industry and to make radiation protection more transparent, both in the public perspective as well as professional perspective. Well, actually, if you attend an UNSCARE meeting, lot of discussion goes into the attributability questions. Attributability is now that the entire process is on cancer, and cancer is a multifactorial disease. How do we, if a person catches cancer and goes to court, and then what can we say about, this is of course a genuine question. Of course, one way is to, you can say that on radiation is no risk, he has nothing to do with radiation, fine. If you can win the case by that way, it's fine, well and fine. But the next best, you ask a professional epidemiologist or somebody, he will say risk is 10 to the power minus 3, varying from -1 to +1 with 95% CI, all that will come. But in any case, there is an attributability question. And attribution has concept of counterfactual conditionality. If he was not exposed, would he have developed the cancer? Very difficult to answer. Again, probabilistically only you can answer this question. So this is being discussed very somewhat at certain philosophical level of unscare, providing a framework for statistics and logical presentation. This thought process is based on certain debates on logic. You can see, I think Dr. Gonsalves is very good in this counterfactual conditionality logic, and he vehemently puts forward. Of course, they were all pro-nuclear lobbyists, so obviously this violates causality question. But there are people who say that all diseases are acausal. The disease theory has its own theory of causality. It is not physics. Physics, yes, you press the force, acceleration comes in, Newtonian law. Diseases, there are multifactorial, so there is no causality. Actually, I was very touched when Gonsalves came to India during Ganguly's talk. He is the one who awoke me to Akshapada Gautama's Nyayashastra logic, the so-called Pramana Prameya Samshayanumana Drishtanta Siddhanta. You know, pure concept of logic of how to establish, test a truth. What are the metrics you must use was postulated 2005 years ago by Akshapada Gautama. It is a famous Nyaya Sutra. He is the father of world logic. Aristotle came much later in Greece. So he said, you people should go back. Your Ganguly would have done that. I remember him telling. Then I checked up with the original lectures by some Manjul Hegde or someone on Akshapada Gautama, and very nicely 16 criteria he had put forward. Some of them could still be very relevant to our radiation protection logic, foundational logic, I am saying. So this is another very important. Occam's razor principle is the very famous principle on which L&T is based. Occam's laser principle says that the simplest and most elegant explanation is usually the closest to truth. If you have no other source of information, linearity is the best thing to do if you have 2 points. We all do that. So it is basically comes from Occam's razor. So now let me come to the role of epidemiology, how these primary risk coefficients have come. We will only run through what is epidemiology. Since I think it must have been a forgotten subject in the last few years. So in the 90s, I underwent a formal training by International Agency for Research on Cancer, IARC. I'm grateful to Nambi for having deputed me there. I was a physicist. I liked only mathematical physics. I disliked anything to do with diseases. But Nambi said, that is your bread and butter, you must do it. So he deputed me to this place, not France. They are holding a lecture in Ahmedabad in those days. 15 days course. I attended epidemiology. Immediately I was a convert into the discipline. It's a beautiful discipline. It has very nice mathematics, very nice statistical principles. It's a new wealth of knowledge that you will get about diseases. In India, there are epidemiologists, but not on radiation. Now, I don't know if Dr. Koya is there. He is the one epidemiologist I know in Kerala today who has formally studied epidemiology. And without that knowledge, we cannot talk of, at least somebody in the HSCG must know how epidemiological studies are designed and conducted. How, for example, people realized that HIV is the cause of AIDS. It came from epidemiology. You can't laugh at epidemiology. You'll be joker doing it. And today, how people discovered that it is the airborne virus which is causing COVID-19 and not touching. If you remember, the first few months of COVID entirely misguided us by asking people to wash their hands and not touch anywhere. Then somebody dug up epidemiological evidence that it is actually transmitted through aerosols. So by cause-effect relationships, and afterwards the whole logic changed, you might have seen. So epidemiology has been, every medical doctor knows that whatever he is speaking comes from an epidemiological discipline. So it is a very respected discipline where statisticians and doctors have come together and formed a discipline. So it is aim is basically, as I have written here, it's helpful in postulating the etiology. It's basically studying pattern. It is not quantum biology. That quantum biology, by the time it gives you an answer, your grandchildren's generations will come. You cannot run a plant or establish a rule, but they all help you. The so-called deterministic or scientific process-based explanations will help you formulate an etiology, and that will be tested by epidemiology. Now, it's an observational science. It's useful for generating hypotheses, and it was used to control infectious diseases in Europe in 19th century, and in radiation context, it is useful for countering exaggerated statements. If somebody says radiation is very harmful, use epidemiological data. The only framework for radiation protection, honestly speaking today, that is the basis for our radiation protection. I will not go into it, but there is a, recently this was discussed, that so we have biological mechanisms, now adaptive response, protective effects, all these are coming. Are they not sufficient for us to regulate radiation workers? It's a far cry going from a cellular level study, which is very useful to, it will help you form a hypothesis, then actually take decisions on actual populations. It is like you can't get the taste of your food by just studying the chemical properties of elements, right? You have to integrate. There are many steps involved before the actual expression of cancer. So in any case, even if you develop actual biological sciences, it has to be tested against the reality check will be through epidemiology. So that is why it's an observational science. Basically, that is the, in 2021, somebody discussed this issue saying that ultimately you cannot totally rely on biological statements. Epidemiology has to be the test against anything. So when you do epidemiology, there are some basic concepts. I'll not just go there. You have to actually measure the incidence rate in a population. There is a protocol of how to do that. Then concept of prevalence. Some people misguide you by doing epidemiology of prevalence. Prevalence is not epidemiology, really. I will tell you what it is. It is done for health, public health effects, cholera breakout. If you have, quickly you count some number of people and see, oh, there are too many people having cholera, let us declare an emergency or a medical emergency, like that. But not for rare diseases. Similarly, mortality rate is another. There is a mathematical relationship between prevalence and incidence rate. So then there are many other concepts. ICD-9 was in our time. All diseases are classified by ICDs. Today it is ICD-10. I am not familiar with it, but ICD-9 used to be by heart for me. 200 onwards is leukemia, 164 is lung, like that. All these numbers are there. Concept of relative risk, which is observed risk divided by background risk. Cancer incidence rate. Excess relative risk is RR minus 1. Confounding, which is a very important concept in all rare disease studies, especially cancer. Confounding is an effect which is a third body which causes the change, but it happens along with your radiation. For example, if you just, assuming that radiation causes cancer, if you just take the total dose of people versus cancer, you will find it high. Because you have forgotten to say that those who have got more dose are also people who are older. Because they would have got more dose. Older people, total accumulated dose will be more than younger people. And older people naturally have more cancer. So that age becomes a confounding factor with the radiation dose. So you have to separate it out first by what is called as adjustment for confounding. All this is done by epidemiological methods. So then, of course, odds ratio is a measure of risk. It is not relative risk, has many measures. One of them is odds ratio, which is odds of catching a disease if exposed as against the odds of catching if unexposed. Then these are some other standardization and crude rates. There are many studies again. So epidemiological studies, when you decide on to do, you should decide what you want to do. So the ecological studies we don't do for radiation epidemiology. It is done in the peacetime by IARC, does it to see whether Italian populations' cancer risks in America have come down to the, rather have changed to American levels, or they still remain their Italian ancestors' cancer levels. So this kind of studies of population patterns over 100-year period is done by ecological studies. So radiation, it is not much useful. Cross-sectional study, as I mentioned, is for public health purpose. The two famous studies on which radiation risk was assessed is the cohort study, which is a very systematic study like the LSS, the Japanese EM bomb survivor study, lifespan study is a cohort study. It recruits individuals along the lines first exposed and unexposed right away, and then follows them through lifetime and sees how many incidences have occurred, then calculates the rates. Then there is a case control study, which is a retrospective study. It's a very beautiful design, which is uniquely epidemiological. Cohort study you could have thought of, anybody, any physicist can think of it, but case control, unless you are a professional epidemiologist, you cannot think. Here you first collect the case. There is a hypothesis that one nuclear industry has caused so many leukemia in our place. You have to disprove it or prove it. You have to do epidemiological studies. You cannot simply say that no, it is not possible. So how to do that? Then you have to go for case control study, where you first identify the cases without looking at whether they are exposed or not. All leukemia cases in the neighborhood you collect, find controls for them. Controls are, there is a protocol for adjusting controls. Then look for who are exposed, unexposed. Their exposure to unexposure ratio is equivalent to risk via odds ratio. So that is the concept. And very sophisticated logistic regression is developed. It is developed by a physicist called D.R. Cox, who is basically a random walk modeler, to address regression of categorical variables. Epidemiologists use it not mathematical variables, but categorical variables. Exposed, unexposed. Say a person of one religion versus a person of another religion, supposing you want to establish male versus female. These non-dichotomous quantities, if you want to do regression, one uses conditional logistic regression, and it also adjusts for confounding automatically by sub-selecting the data. It's a very nice subject. So in cohort study, very simply, as I just mentioned, you take a group of smokers, a group of non-smokers, and follow over lifetime, and then compare the outcomes, calculate the incidence rate here, incidence rate here. If the incidence rate is more here for, let's say, smokers, then you say there is a more risk, but if it is the other way, you say it is a less risk. Then apply classical statistics to obtain the bounds. If the 95% bounds are narrow and tight, as per a pre-assigned p-value, then you say that yes, there is a significant statistical significance. If it is not there, then you say there is no statistical significance. So mostly my number is fortuitous. We need to pull together more studies. That's the way epidemiology proceeds. So case control study. So you first collect cases, as I mentioned, some cases, and then choose controls. It's a big job to choose controls for cases. You have to adjust for age, sex, and if possible for genetic factors, and all the known factors you have to adjust as much as possible. Then look at who are exposed and who are unexposed. So likewise you do that, and then develop what is called as a factor table. So it will be a cases and controls grouped into exposed and unexposed. Then you have, let's say, A, B, C, D. Then the relative ratio, it is equivalent to odds ratio is AD by BC. The cross multiple 100 people if you have cases, not exposed are 500. Similarly, controls you had 300 and 200, then it will be this AD by BC is 100, 500, 300, 200, 5 by 6, less than 1. Now you make a statement. So the logic of why that is relative risk is you can interpret two ways. AD by BC basically means A by B divided by C by D. That is, odds of being cases among exposed versus the odds of being cases among unexposed is also a measure of saying that the exposure is the cause or not cause of it, one way of looking at it. Or odds of being exposed among cases, here it's cases among exposed, here exposed among cases divided by odds of being exposed among controls. So it is the exposure status among cases versus controls is also a measure of risk. Or cases or controls in the exposure status is also a measure of risk. So this is the logic, and excellent statistical methods exist for analyzing the bounds on this relative risk. That is the basic idea. Now, what we did in 1990, honestly, is not epidemiology. So when the international body doesn't recognize our work, we know why it is. Because they know that what we did is what is called as the health status study among DAE employees. This was actually to give more teeth to public speaking of our public awareness groups, to give numbers. In fact, Parsarthi was told that fortunately I can always cite you paper. It gives me so much strength rather than citing from UNSCAR and ICRPs and saying everything. We can say our own studies exist. So that was the kind of support or encouragement that one got from various agencies for this study. So our study was essentially 1990 to 97. I'm sure Pradeep would have heard so many times. So very old work. So I'll not spend much time. Whatever data, in fact, this was so limited. Whosoever helped us only we could do. So some nuclear power station directors said no data sharing, we will not give. But some people via influences of people like Soman, Nambi and L.V. Krishnan, I must thank him there, and people from NFC, health physicists that time, I'm even forgetting the name. So it was all personal level contacts. So we made use of all the data that was available at that time. Yeah, I think Chavara data was also, Alway data was also available at that time. I think it was a Paul's influence. So NFC, so these were the 5 data we collected. It is a very small database, but we learned in that process. Basic idea was that. So we took the cancer mortality data from the death certificate. One good thing is all our data was reliable because it's from our hospital. So cancer is reliable, not in the public domain, but this was good. Then can someone tell me the time I have? Few minutes? 5 minutes? Yeah. So basically these are the various sources of data. Most of you would know what it is. So as I mentioned, we took the cancer mortality from the Indian registries. Bombay Cancer Registry was very good. It was the best. So we took it from Bombay Cancer Registry for Ahmedabad, Bombay and neighborhood, but we called it national baseline. There is no other way. That's the best we did. Today it could be much better, that data. And this is the age structure of our, only males were to be worried about for radiation study. So we focused only on males in those days. So this is the way the age structure is presented. You will see this kind of picture in all epidemiological studies. Age structure is presented this way. Then we pulled together, we had 81 deaths only total. And of these 5 units, 40 from BRC only. So these are the, with 81 numbers, you can see Poisson error itself is 10%. Obviously, radiation risk cannot be detected. There will be 10 deaths by random anyway. 81 plus minus within 1 sigma level. 2 sigma level, it will be 20. So definitely we know we are not going to detect any risk, but it is more like establishing a method, starting a science in a nuclear institution. So that was the idea. Then you finally calculate what is called as the standardized mortality ratio, apply Poisson statistics rigorously. Then you get a bounds, 95% confidence bounds like this on the standardized mortality ratio. There are excellent papers in biometrics from which we took this formula. And you find that most of the, in fact, most of them were within the upper bound, very well within the upper bound. Some of them were more than 100. More than 100 means some more risk compared to general population. Less than 100 means less risk in DAE compared to a general population. So healthy worker effect always operated. DAE people are well fed, less diseases due to infections. So all that was visible very clearly. And there were some really very healthy worker effects here, these parts. So this was the status. It was very useful for AERP at that time. Just started, like Parsarthi used to say, that it's very useful for me to do public speaking because at least it shows that our DAE people are just about as healthy as any other healthy industries in the country. Yeah, so I will, then of course we attempted, didn't publish this, to do a comparison between NRW and RW. It's very premature. One should not do it. Half studies are very dangerous in epidemiology. One should take a full cognizance. That is one reason that we were not publishing all the results. But just I'm showing that we can do a relative risk estimate, and even that was lower. You can find that the radiation workers were less risk than this. Now, coming to the world, this kind of a job, because it was going on in many places, like you can see already by that time we had lots of publications from Hanford, Rocky Flats, ORNL, Sellafield. Sellafield is the many other issues, so pooled, etc. And there is a famous work by Cardis. Again, as I mentioned, meta-analysis. We must go for meta-analysis of such studies. So Cardis et al. Has pooled the entire nuclear industry. And 2 papers in 95 and 2005 she submitted. 95 came into great criticism. There were some flaws. So she probably corrected it in the 2005 paper. And they had an excess relative risk per sievert of the order of the ICRP risk coefficient of 0.4 per sievert within the acceptable, within the boundary limits. So there is a matter of debate. So this is one such study. There were, of course, I will not go into the ABSS study, but reanalysis of ABSS was done after 2000. And I'm not referring to the old atomic bomb thing, 86,500 people, cancer deaths, so a huge number of cancer deaths are there. So you should be able to detect it at some level. It is not very superficial, about 8,000 deaths, and of 40,000 total deaths, 40% I think cancer deaths or something. Then dose distribution, you had significant dose of the order of 10 less than millisievert. So analysis is not entirely high dose. So the recent trends, for example, very clearly, this is by Pierce. These are classical epidemiological studies of the A-bomb survivor, established the 2000, yes, 2000, that even if you postulate threshold, that threshold is of the order of 6 millisieverts using ABSS data. I'm not saying it's one study, but otherwise there is a greater evidence for greater fitting function value for linear rather than the superlinear or sublinear. Sublinear is the threshold. So this was a kind of verification of the ICRP risk coefficient itself. So he had given the risk coefficients, all of them are around 0.4, you can see, more or less like the ICRP, but reanalysis, it's not the old analysis, it's the reanalysis. I am not much in touch with what happened after 2012, I couldn't get the time to study, but this is the status up to 2012, I must say. Now, Karunagapalli study, it is our study, it has definitely shown negative risk coefficient. ERR coefficient is minus 0.13. They have followed excellent statistical conditional logistic regressions. It's a beautiful Indian study done professionally. However, when you go to UNSCARE, that is not the only study. There are Tekka River study, Karunagapalli, Yangjiang study, Taiwan study. They have all, many of them have not shown an extra risk. But these are pooled together. I'm not going to discuss individual results. So the community's collective wisdom is based on pooled studies of this type. That's what I want to say. And this is the radon result. And all the radon studies have shown higher risk recently. It is not, so based on this evidence, you have to counter it. You have to counter it epidemiologically or statistically only. But otherwise, there is no easy way to just dismiss these positive risk coefficients. And they are not very alarming. Everything is of the order of less than 5% per sievert. It's a small risk, but it is shown. Why we cannot detect is here. We calculated, it's our published work, that you need about 3,600 radiation workers exposed at 10 millisievert per year, followed for their lifetime, to detect risk at the level of the current ICRP list. So we didn't have it. So that's why Dr. Nambi said at the time of retirement, Maya, no point in doing this study for the next 20 years. Let enough data accumulate, and maybe then there is time to, maybe it should be looked at. So that is one reason why it was not pursued later, because no point in doing half analysis and doing, communicating all kinds of numbers. UNSCARE also tells like this. There is a UNSCARE table which tells you how many people are required for you to detect risk at the order of 0.4 per sievert or something. So, well, I am at the end of my talk. So where do we go from here? And I have, these are the something shared by, I think, Arshad and Anand. So if you look now, the number of non-DAE radiation workers are significant number. Just before retirement, I just wanted, tried to establish one Indian IRRW as a project, I think one of those planned projects. I don't know, the whole thing was wound up later, I heard. So it was the idea that along with the dose registry, we will also have other information of radiation workers, preferentially as much as possible on health effects, so that somebody can do an epidemiology later. We called it IRRW, Indian Registry of Radiation Workers. I think later maybe it was not sustainable, so it was not continued. But the idea is that you will do. And today I think you have of the order of 120,000 kind of lakhs of dead workers, and significant amount of collective dose of the order of 120 person sieverts, large experience of person, year experience exceeding 1 million. Feel that it is, of course, collective doses are all very less. Individual doses are very less. Obviously, of the order of a few millisieverts. This is a matter of discussion here. But collective person sieverts, could be a source of our strength to do an epidemiology and say with certain confidence interval that we do not have risk. I agree. That is, of course, all of us know inwardly that it's really a very trivial risk. It's really a clean energy and all effort should be made. But that effort should be made through a scientific foundation, and this health and safety is the right place where all knowledge exists to do this. So that is what I want to summarize and bring it to your attention, that at the current level of understanding, epidemiological approach continues to remain the only guidance for radiation protection. From hardcore biology or biophysics, it will come, definitely. Many Nobel laureates have to come through to be able to make definitive statements of radiation risk at the age of 90 for a person, for example, or 80, whatever. So that is a long way ahead. Work initiated in the 90s in BRC was a bold step at providing quantitative support for public communication. One zone data analyzed is far stronger support in public awareness than borrowed statements. This is what Dr. Pasarthi used to tell us in those days. It will give great strength for putting forward our views in international fora like UNSCAR and ICRP. And as of now, sufficient PY database would have accrued to offer reasonable confidence intervals and statistical strength. So it's kind of my wish or my request or my view to put forward to you that it is maybe time that a second round of radiation epidemiological studies is initiated in DAE. At least the expertise built, people trained, and activity at some other point in time carried. If nuclear energy has to grow, it has to grow with its science and with the proud professionals of health and safety group. As Dr. Nambi once put it when he was in service, we as HSCG are actually the key people of the entire DAE program. Our TLDs required all the solid state physics required. We developed it ourselves, deployed it, demonstrated its working. Everything was indigenous. So that is the pride, I think, of being a health and safety professional. And with this, I wish all the best for all youngsters here, youngsters, oldsters, all, including myself. So we have to do everything possible to, help the country in the energy needs. And now in public domain, I always take this opportunity about nuclear energy being the cleanest energy, no doubt, sustained by our understanding, but coming from studies of this epidemiological type. Thank you all for listening to my talk.
Thank you, Professor Maya, for your valuable insights. We can have the discussion of this lecture during tea break. I now invite Dr. Karunakarayan, Convener IARP 2025, to present a token of appreciation to our distinguished speaker. Before we move on to session 4, there is an important announcement. The following delegates have not given the PPT of oral presentation. The names are as follows: Madhur Swarnkar, Anu David Raj. We request you both to kindly hand over your respective PPTs in a pen drive at help desk as early as possible. Hello. We now move on to our first technical session of the day, chaired by Dr. P.P. Haridasan, former Senior Safety Officer, Department of Nuclear Safety and Security, IAEA, and Adjunct Faculty, Enapoya University, Mangalore, and Sri S.N. Tiwari, Officer in charge, ESL. Before we go ahead with the session, we'll have a brief introduction about the chair and co-chair of the session.
The chair of the session, Dr. P.P. Haridasan, former Senior Safety Officer, Department of Nuclear Safety and Security, IAEA, also adjunct faculty in Napoya University, Mangalore, has nearly 25 years of professional experience in BRC, mainly associated with radiological protection in the mining and processing of thorium and uranium. More than a decade of professional experience as Senior Safety Officer and Radiation Protection Specialist in the Department of Nuclear Safety and Security, IAEA, Vienna. He was responsible for developing a number of safety standards, including occupational radiation protection, application of the concept of exemption, radiation safety in well logging, nuclear gauges, accelerator-based isotope production facilities, and radiation safety in research and education. He was also responsible for the publication of number of IAEA safety report series, received Individual Merit Award in 2014 and Recognition Award in 2019 and 2021 from IAEA. Team leader for the IARPA's mission in UAE, lecturer in International Radiation Protection School, NEA, Stockholm. Member of ICRP Task Group 76, organized more than 70 international workshops and meetings worldwide. He was also invited speaker in many international conferences, including IRPA Congress, Health Physics Society meetings. Haridasan sir holds PhD in chemistry from University of Mumbai and has authored and co-authored more than 90 publications. The co-chair of this session is Shri S.N. Tiwari, OIC, ESL, Rawat Bata, Environmental Monitoring and Assessment Division, BARC, has experience of more than 35 years in the field of radiation protection in waste management facilities of BRC, environmental radiological surveillance around nuclear power plants. Main responsibilities include pre-operational surveillance activities of the upcoming nuclear power plants of Chutka, Madhya Pradesh site and Mahi Banaswara site of Rajasthan, surveillance activities during operation of nuclear power plants and response during emergency preparedness.
Thank you, ma'am. And this announcement is just to confirm that oral presenters of session 4, T3008 Prasant Sahani and T3022 Jayadevan PM are not present here today. I repeat, the oral presenters of session 4, T3008 Prasant Sahani and T3022 Jayadevan PM are not present here today. And now we hand over the session to the chairs.
Very good morning to everyone. We have one invited talk in this session. Mr. Dr. Suresh Kumar from Health Physics Division, Baba Atomic Research Center. He will speak on practicing RP challenges and opportunities. This is a practical topic, I think the most relevant in this audience. Dr. Suresh Kumar joined BRC Training School in 1998 after completing Masters in Chemistry from Cochin University of Science and Technology. He started his career as a health physicist in plutonium plant Trombe and has operational health physics experience of more than 25 years. He has played pivotal role in implementing radiation protection scheme for many new plants and processes like the metallurgical waste processing plant and power reactor Thoria fuel reprocessing facility. Currently, he is heading the Radiation Hazard Control Section of Health Physics Division of Baba Atomic Research Center and is distributing his time and efforts equally between implementing health physics activities in operating plants, safety review of design of new facilities, research for improvement in health physics practice, and imparting training to new generation of health physicists. May I now invite Dr. Suresh Kumar for his to deliver the lecture.
Thanks, Chair and Co-Chair. Good morning to all. I am talking on the topic practical radiation protection challenges and opportunities. What happened? Is it not working? This one. This up and down. Not function. Okay. What is some issue? What is this problem? What is the issue of this? She's okay. Once again, good morning to all. Sometimes I feel like that we are lucky to be in India because basically we don't have a very dirty nuclear site what is in UK, Russia or USA. And from the beginning itself, the nuclear energy program was with the government. Therefore, there was a very good coordination between the management commitment for radiation protection, the worker participation in that, and the radiation protection expertise required for that. This was a good part of India. And further, we can see that we have started this program around 15 years later when the Western world done it. One advantage is that many of the ill effect of radiation at that time, by the time itself something was known. Therefore, that also have an advantage for us. Basically looking, our facilities are mostly safe. There is no major accident. And we have well qualified radiation protection staff. Why I am telling is, for the equal type of job, for the same type of job actually in India, we are utilizing slightly overqualified people for the same type of job. That is one advantage we are having. And definitely because it is in the government sector, cost was not a bottleneck in our program. Now, as a practitioner, when I am looking at radiation protection, I will look at what are the ingredients for it, what are the support for us. And I have given a color code here, basically looking at how the status of each of the supporting system I am having. Now, trained manpower, we have very good trained manpower, both for health physics and medical physics. Yesterday there was a discussion that medical physics, there is a manpower shortage. Basically, it is not like that. If we are looking at the people going out from India after medical physics training is too huge. Therefore, the industry problem is something different. We have a very good regulatory infrastructure, that means whether it is AERB or BSc. Our dosimetry system is fairly developed. We have good environmental measurement and environmental modeling system. Radiation protection instrumentation, when we are talking, definitely we have very good instrument with us. We are very good at using it, but there are some problems like most of the elements, detector elements are basically imported. That is one aspect we have to address. And further, we have to see that the system for checking or qualifying the instrument, especially some specific instrument that have to be developed. Radiation protection research as such, but we are seeing we have a very good research team in India, but at the same time, what is the effect of this research or how the research is getting into the practice, that is somewhat more efforts have to be done on that. Then what about documentation? For a country like India, where the breadth of the program is too huge, that means what we are doing from mining to reprocessing waste management and all the industrial activities, this documentation side definitely we need some more improvement. Regulatory science. This regulatory science is not in a very good shape in India. I will give some example where the improvement requirements are there. And the last talk probably might have seen why I am putting a red here, because basically for real studies have to be started again. Now, overall we are looking, we have a good radiation protection infrastructure existing in the country. That should be our conclusion. Now, what is the net result of all this radiation protection infrastructure existing in the country? I'm just giving what is the exposure of the population in India. We can see that this is the number of radiation workers. The number of radiation workers in non-nuclear industry has far outnumbered. That is around 1.4 lakh now, comparing to the nuclear industry workers. Similarly, if you are looking at the collective dose, the collective dose of all that is what is this figure, the collective dose also crossed the collective dose of the nuclear energy workers in the country. Therefore, the major occupational dose as on today is basically this an industrial and medical application of radionuclide. This we have to understand that when we are looking in nuclear energy and the rest in comparison, we should understand that it have already crossed, and definitely this is something how the human development index is growing in our country. That is a very good indication. But again, you see what is the average dose of the worker. The average dose of worker of nuclear industry was regularly decreasing in the last 2 decades. It was a continuous process. And at the same time, the average dose of the other industrial and medical workers, that was remaining almost constant or slightly decreasing. Therefore, this figure indicates that the radiation protection infrastructure in the country is functioning in an excellent fashion. That is what we have to tell all those people who is maybe talking against radiation. Now, if we are looking at the dose in the reactors also, it's similar. I am just giving a picture of the power reactor exposure for the last 10 years. You look from the 2012 to 2020. When comparing the collective dose of the Indian reactors and all world reactors, we have slightly higher number. This higher number basically, one of the reason is that because we are having more PHWR compared to PWR in the rest of the world, and the PHWR slightly giving the internal dose due to tritium. Otherwise, we will match. And when we are looking at our reactors, PHWR in rest of the PHWR, the data is matching. Therefore, why I am indicating this again and again is that our radiation protection system can be equalized with the rest of the world. That is what I wanted to tell here. Coming back to the history of radiation protection, I am showing a picture here where the collective dose of a facility which we were operating around 60 years in the country. You see, from that time, that means 1960s and 70s, from that time while we are reaching this, near the last 10 years, it have reduced maybe of the order of 20 times, And looking at that data, we can see that looking for further optimization may not be required. We have optimized it so much that the exposure to the workers are so trivial that there may not be needed to do much on that further in the occupation in the nuclear fuel cycle facilities. Now, these have resulted due to various reasons, like the reduction in the dose limit in between the ICRP, the design improvements in the facilities, introduction of the collective dose budget. This has come in the regulator after some time. Then the periodic regulatory inspections done by the regulators and improvement in instrumentation. All these have contributed this drastic reduction from there to here. But if I am saying that because everything is done, there is nothing can be done further, no, it is not like that. Definitely, there will be a next stage of reduction, but that next stage of reduction will definitely come when the process is automated. Process is automated, the meaning that instead of people going to the active area, all the plant operation is done, most of the plant operation is done remotely from the control room. When that is achieved, definitely we will have a next stage of reduction in the nuclear fuel cycle facilities. But this is not the case with the public dose estimate. I have told that in the nuclear fuel cycle occupational dose, it is already reached a minimum. But in the public dose estimate, we can do something further. Why I am showing a figure here, here you see, this is again another operating facility we were running for last 40 years. This is the dose limit, that public dose limit given by the dose apportionment, and this is the actual releases from the facility measured. Why I am showing here, if you are adding all the releases of this particular component for the last operating period of the 60 years, still it will not be crossing the 1 year of present release. This much margin we are having in our calculation, many times the public dose calculation. We have too much margin. Therefore, the argument that we will not have sufficient margin for operating the facility, etc., is not fully true. We have sufficient margin in many of the systems. Why it is coming? Because basically we don't have much of the data in-house for this calculation. We have an over-reliance on the literature what is available, that literally making us to do the calculation, and generally we will stop with the generic model if it is suffice for the regulator. Now, why I am pondering a little bit more on this, basically the dose calculation from, for example, air route, it will depend upon, basically everybody use this standard form that material at risk into damage ratio in air release factor, respirable factor, leak path factor, all these calculations we are doing. But where we will get the ARF or RF, that type of numbers? Unfortunately, in India, we have not made this. It is not somebody's mistake, because basically when this particular document made it, that is, this work is mostly US done in the 1960s, 70s and 50s. It is a very huge costly affair. Making engineering system for scientific data is a very costly affair for countries. Therefore, what we are doing when we are asked a calculation, when we have to submit something to the regulator, basically we will look at this book, we will take the number from there. That number have a huge margin. Huge margin, for example, a particular release fraction, they may give a bounding value 10 raised to minus 3 to 10 raised to minus 6. When I am calculating, definitely I am a safety person. I will be forced to put 10 raised to minus 3 instead of any other number, even if it is something low. And this margin is actually what we are seeing in our calculation or in the public dose limit estimation. There we can do something so that within the existing limits itself, we will be able to improve our nuclear program. This is what I wanted to stress here. Now, instead of making engineering facility, we can do something else also. For example, we have operating experience, we have operating plant. Whether we will be able to generate the data using the operating plant, for that we have to put some provision. We have to force the operating facility to, already we are doing that job, how to generate data from the operating plant for getting the release fraction in each stage of the plant operation. A similar advantage we will get if we are looking at the release through solid route, because we are doing a very generic estimate, very conservative estimate by converting the dose rate into activity. We have done some studies how if the position of the source is varying a lot, how the activity will vary, what is the margin in that. Such studies we have done. Therefore, what I am saying here is both in the solid system and the gaseous system, we have very good margin available till today, so that we can have more plant using the same public dose limit available today. Now, I will be looking at two other aspects again, because why I am putting it is, there is always a question that whether the practice is actually fully scientifically based. This number, this derived working limit for skin, this number is existing in our IARP document for last 30-40 years. The beta contamination is 1.5 becquerel per centimeter square. When the nuclear program started in the Western world, they had some calculation, they had some scientific basis for that, and that has come to our regulation also. But the rest of the world moves, the regulatory changes come to it, but sometimes we are little bit delayed in adopting it so that our life will become easy. I am putting it here. When these numbers were generated, there were two bases for that. What is the skin penetration of a particular radiochemical, for that it can give an exposure. What is the skin dose from it is presenting as an external exposure agent. We have studied the penetration of different radiochemical, and I am saying that most of them doesn't penetrate. For example, maybe technetium and iodine and tritium is penetrating, but the rest of the radionuclide or radiochemicals, penetration even 1% is not there. Therefore, there is a large reduction is possible in this type of numbers. I am giving another example. You look at German Radiation Protection Organization, their number is 10 becquerel per centimeter square instead of our 1.5 becquerel per centimeter square. I am telling that Germany is a country which is dead against nuclear system, and they are closing all the reactors, but their number is 1.4, 10 becquerel per centimeter square. Similarly, if you are looking, all other countries, they don't put a number. What they are doing is, they tell that you see the contamination, you decontaminate with some little mild agent. If the contamination persists, you calculate the skin dose, add to the value of the dose of the worker, and release him. We are not following. That is what I am saying, that there are some improvement is possible in our regulatory system. Still, we can have a this effective radiation protection system. I am giving one more example. As a country, we have to have a large number of nuclear medicine facilities have to be created. Now, in India, we have a radiation protection rule which say that we should release the patient only when the patient dose after iodine administration should be 5 mR per hour at 1 meter. This is a restriction. What I am doing, after administering the radiomedicine, I am keeping him in the bed in the hospital, waiting for him, the dose rate should come to 5 mR per hour. And other patient is waiting behind for the bed. This is a fact. Now, the same thing if we are looking at the US data, this is the 5-year data I collected from one of our center, which is having around a quarter of the iodine treatment in India. This is the data of around 7-8 years collected from the US NRC reports. Basically what we are seeing is, they are not holding any patient in hospital even after administering 300 millicurie of iodine. They are not keeping, because they have a questionnaire, they have an analysis of what is the possibility of the dose received by any public, whether he can be released, what is the availability of facilities in his home for avoiding dose to this. I am not saying that US is equal to India. Basically, they are driving themselves, they have big mansions, everything is fine. But is it affordable for a country like India, because of the exemption dose limit, to keep them in hospital with this type of stringent dose limit? This have to be, again, these are why I am putting is the overly conservative approach. Many of the countries, are slightly moving away without making any sound. What I am telling you, they will not tell I am going to do, they don't tell like that. The regulatory process have a regular review, and that regular review is not happening in the science alone. They put the social surveys, they ask the question from the public, what are the changes to be carried out, all these things, ultimately they do something in the regulatory change which is aiding their people. And actually I think that this regulatory process is somewhat absent in India. We cannot make a regulation only from laboratory. It is only thinking. It is not like that. They have a lot of things to be done behind it. That similarly, I am putting two more monitoring practice experience here, because we can see there is a number. What is the number of air changes in a room required? This is again a regulatory number from the safety manual of IARP. Definitely, air changes are required, but if I am running an iodine handling facility, the air changes required is same as a air changes required for a uranium oxide facility which is dense. No, it is not that. There will be huge difference. But what is the basis of this? How I can do? Whether we have done enough scientific studies behind it, how it is we are doing something. But I am putting that there are requirement of regulatory improvement or regulatory science making behind the numbers what we are following in our country. That is why in the first picture I was showing that our regulatory science is not developed as per the requirement or what we needed. I will put one more question on this regulatory aspect. We had area gamma monitors. If you go to a bigger plant like INRP in Tarapur, you will have area gamma monitors maybe 1,000 in number. What currently the regulator tell that you calibrate these every 2 years. I'm telling that it's impossible. It is impossible to calibrate the 1,000 AGMs every year, removing it and doing it. It's not possible. But what is the way to avoid it? Basically, the calibration requirement is based on the instrument performance. How to generate this performance? We have to look at the schedule of that. We have to look at what is the drift is happening in it. And this number should be generated by the operator. There should be force on the operator to generate such numbers so that I can have a dilution on this. I can have a free work in the future facility. This type of things have to be happen. For a radiotherapy machine, IARP is giving 3 years. For all other radiation instruments, we are giving 2 years. And the radiation instruments are so many types available in. Therefore, this type of data generation is what is actually going to make the health services life easier, plant operation easier. These are, I have given only 2-3 examples from the field where we can say that there are possibilities for improvement within the existing system itself.
Suresh, can you conclude?
Yes. Fine. Therefore, I'm stopping here. Now, if you are looking at any low-dose health effects, there will be in any international, like our similar society anywhere, you have a lot of wish list. But what we should do in our system? Basically, we have to prioritize our research area and concentrate on R&D, which will influence the health services practice. I am insisting that science is something, but basically what we should look is what R&D will change the practice or aid the practice happening in the field. This is most important while coining the program, and concentrate on the quality of data produced from field. Why I am saying this? The field data, they have two use. The field data, when I am doing a field measurement in any plant or any facility, the first purpose is definitely aiding the process, aiding the productivity. But there is definitely a second use of that is the prediction of the next facility or improving our program. For that, we should definitely have very high quality data production from the field, that we should insist on that. And in addition, we should include social, economic and evolving factors in decision making, including regulation. And this is not for us. Basically what I found as a practitioner, that radiation protection system shall not be too complicated. Why I am telling is, unless you have a PhD, you will not understand the basis of radiation protection. It should not happen like that. There should be something simple so that we can convey and try to remain stable for a reasonably longer period. Why I am telling it to remain stable for a reasonably longer period? Because the units of radiation protection, the measurement, everything, for a minor improvement, even international organizations change it periodically. And that is actually what is the benefit of that changes. Actually, we should be able to argue with our data whether it is required like this or not. That I'm putting the synergy between our scientific bodies, regulators, and the practicing people, that only will make the world forward. Thank you.
Thank you, Dr. Suresh Kumar. We can have one or two questions, please. Are there any questions?
No.
I don't see any. May I have a question, please?
Yes.
Have you thought of any artificial intelligence application
I think
in our nuclear?
No, basically, we are working on like that. For example, predicting the air activity. When you are making an air activity measurement, you will have radon regularly coming into the filter. Whether the data analysis can predict or subtract that value to get the real radionuclide. We are using that artificial intelligence in many. We are thinking about ML and AI algorithm in this many practical field.
One more question is your point on surface contamination limits. Can we deviate it for a specific to a facility?
Yes, definitely. By many of the countries, this radionuclide contamination, they give radionuclide specific based on what is the radioactivity handled in the facility. But that is basically a cumbersome activity, because regulator cannot do like that each radionuclide. There is a difficulty for putting in that fashion.
Okay, thank you. Thank you very much.
Thank you, Dr. Suresh Kumar, for your presentation. May I request Chair of the session, Dr. P.P. Haridasan, to present a memento to our esteemed speaker. Thank you, sir. We'll now move on to the oral presentation, and I request the chair and co-chair to take over.
Now the next lecture is by Sally Goyal on the topic of characterization of radioactive waste generated during molybdenum-99 batch production.
Thank you. Good morning, everyone. Today, I'll be presenting a work on the characterization of radioactive waste generated during molybdenum-99 batch production. Molybdenum-99 is crucial because it is required for production of 99 technetium, which is widely used medical isotope in diagnostic imaging in nuclear medicine. When Moly-99 production is carried out, radioactive waste is generated in liquid and solid forms. This waste needs to be managed and characterized for radioactive safety, radiation safety, and environmental protection. So in this presentation, I'll discuss the basics of molybdenum-99 production, methods and materials used for the characterization, and results. This is the decay chain of molybdenum-99. Chain of molybdenum-99. Molybdenum-99 has multiple betas and gammas. 81% of the time, molybdenum-99 decays with beta emission of 1.2 MeV 99 technetium, which finally decays to 99 technetium via gamma emission of 140 keV, and 99 technetium has a long half-life and decays with a half-life of 2.1 into 10 to the power 5 years to 99 ruthenium, which is stable. In nuclear reactors, there are two ways to produce molybdenum-99. First is the fission. In fission, highly enriched uranium is irradiated with neutrons, high flux neutrons. And molybdenum-99 is produced as a fission product in approximately 6% of the fission. The second process is neutron activation. In molybdenum-99 has 35 known isotopes, out of which 7 are naturally occurring. So molybdenum-98 has abundance of 24%, that is maximum. In neutron activation, molybdenum-98 is bombarded to produce a highly unstable with high flux neutrons to produce highly unstable molybdenum-99 compound, which finally emits gamma to produce molybdenum-99. The neutron flux is of the order of 10 to the power 14 neutron per centimeter square per second, and the irradiation is carried out for 7 to 8 days. Since 98 molybdenum is chemically similar to molybdenum-99, so the resulting product has low specific activity as compared to the molybdenum-99 produced by fission. But disadvantages of Moly-99 produced by fission is that a large amount of nuclear waste is generated, which needs to be handled, and uranium-235 enriched targets are expensive and require containments, and traces of other radionuclides which are produced along with molybdenum-99 are always there. After the production of Moly-99, our main target is 99 technetium, so we need to separate molybdenum-99 from technetium. For this we use technetium-99 generator, in which we load the generator with alumina. Alumina absorbs molybdenum. Molybdenum is loaded in molybdate form, and it is absorbed on alumina. Now, technetium has lower affinity for alumina, and technetium as decays, and technetium when decays, it is eluted using 0.9% of saline solution. It is eluted as sodium pertechnetate ion. This is the equilibrium between molybdenum 99 and technetium 99M. They are in transient equilibrium, and molybdenum 99 activity decreases continuously, while daughter activity, that is 99M technetium activity, increases and then reaches a maximum, and then when it starts to decrease, we elute it using using saline solution after 23 to 24 hours. Then the daughter activity reduces to 0, and again it starts producing and reaches maximum, after which elution is carried out. These are the materials and methods. We have carried out the characterization using HPGE detector, high pure germanium detector. The activity produced per batch is around 40 curie of molybdenum 99, and in a year 40 to 45 batches are carried out, which averages to 1 batch per week. In each batch 80 gram of solid waste is produced and 200 ml of liquid waste is produced. Solid waste generally consists of adsorbent sheets and tissue papers, and liquid waste consists of beakers that are washed and reused. And this waste is stored for a decay period of 2 to 3 months before it is transferred to waste management facility. These are the results. First, we have the identification of the radionuclides and the activity that is given from the gamma spectrometry. We have applied the dilution factors and decay corrections to account for the decay from the day of production to the day of counting, and then we have calculated the activity in becquerel per ml and converted in the percentage form. So the most predominant isotope is molybdenum 99 along with iron 59, cobalt 60 and Nb92M, which is for the liquid waste samples. Solid waste samples had much diverse profile. It is in the solid waste samples also we have calculated the percentages by the same method. So in solid waste samples, we have a much diverse profile which contains of activation products and fission products also. Long-lived fission products like cobalt 60 and cesium 137. Since the adsorbent sheets and adsorbent sheets are used, and the container in which the molecule target is there, it is cut on those absorbent sheets, there is a possibility that there might be some minor contamination that is there on the container, and it has been spread on the absorbent sheets. That is why some fission products are coming. This is the spectrum that we have received from HPG detector. This is for left is for liquid sample and right is for the solid sample. As we can see, solid sample had much diverse profile. So using the activity that we have received, that we have calculated, we have calculated the amount of activity, amount of radioactive content in annual radioactive waste generated after a storage of 2.5 months, after which it is discarded as radioactive waste. So for liquid waste stream, we have multiplied the decay factor for 70 days with liquid waste generated per batch, that is 200 ml, and batches per year. Similarly, we have done it for solid waste also. For liquid waste, it is concluded that radioactivity content per year generated is order of 30 microcurie, and for solid waste, due to long-lived isotopes, it is 9 millicurie per year. For 1 year, molybdenum 99 production activity is 900 curie, and the waste generated is several orders magnitude lower than the annual molybdenum 99 production activity. Thank you.
One or two questions can be taken from the audience. So, questions, please.
Efficiency of the HPGE detector. Please specify. No, it's okay. Could you understand? I just want to know what is the efficiency of HPGE detector as regard to molybdenum-99. Have you done the calibration?
Sir, I have
Let's
not
check.
done the calibration. The apparatus is with someone else, so that division might have done the calibration.
Okay, okay. Thank you.
So, Madam, one question I want to ask actually, that before sending these waste, liquid waste and the solid waste generated during that molybdenum operation, do you holding that waste at your end or directly you are sending the waste to the waste management facility?
So we are holding it for 2 to 3 months, and then we check the radiation field. If it is under the compliance of, it is another compliance that is 200 mR per hour se kam hai, according to the category, we send it to the waste management facility.
Okay, okay, thank you.
Our next presentation is from Mr. Jason John. This is the depth profile of Gnome levels into inland mining areas of IREL Chavra. Mr. Jason, please.
Namaste to all. Good morning and respected chair and vice chair and senior delegates and young enthusiasts. I am presenting here the depth profile of naturally occurring radioactive material levels in two of the inland mining areas of IREL Chavra. IREL Chavra, is located in a very renowned natural high background area of southwest of India, means southwest coast of Kerala, and another unit Manavalakurchi, which is in southwest coast of Tamil Nadu. Here the study is on the IREL Chavra's inland mining area. The unit is mostly involved in the beneficiation of heavy minerals like ilmenite, rutiles, zircon, selimanite, it's monocyte, sorry, it's a typographical error. And that requires raw sand collected from the as the input material. So raw sand is coming from beach sand as well as the sand in the inland area close to the beach areas. So the Chavra mineral division, which is involved in this activity, and as I told, it is located in the natural high background area. And the mining activity, it's actually mainly in two types, as I told. One is beach sand mining and other is inland mining. Inland mining goes to a depth excavated for the raw sand collection, and beach sand mining is not involving the depth, means going to the depth of the beaches to collect the raw sand, but only on the surface raw sand is collected. So the radioactivity of heavy minerals is mainly due to monazite and zircon. They are the naturally occurring radioactive material. And the monazite it contains around 0.35% uranium and 9%, about 9% of thorium. And it's all in orthophosphate forms including rare earth. So it's a monazite is the rare earth resource for India. Here we come to the microscopic pictures of monazite. 96% of monazite looks like this in microscope, and the zircon looks like that. The right side picture. The radioactivity content in monazite is around 320 to 380 becquerel per gram, and that is of thorium-232, and around 30 to 40, 30 to 38 becquerel per gram of uranium-238. And both uncyclical equilibrium, but the crystal or the monazite crystal is a very strong crystal in terms of its stability, and it is of a very high density of 5.25 it comes to. And so the emanation or that kind of issues are very limited to monazite crystal, because the gas coming from, means emanated from thoron emanated from monazite is very negligible because of the crystal strength of the crystal structure, and it is strong up to around 1000 degrees centigrade. The zircon contains around 0.5 to 1 becquerel per gram of thorium, and it contains more uranium, 1 to 5 becquerel per gram of uranium-230 around. And in a raw sand, the heavy mineral contribution means his composition is for majorly ilmenite. Ilmenite and rutile are titanium minerals. They are 4 to 15% and 0.4 to 1.8%, whereas monazite comes only 0.05 to 2.5% in Chavara region. Zircon is only 0.3 to 1.1%. And in fact, total heavy mineral comes around 10 to 30% of the raw sand. So this is the picture. The right side top picture shows how the inland mining is taken place. It goes up to the level of depth of 6 to 8 meters sometimes, and there are cases they go up to even 12 meters. And the samples are collected at in 2 locations, 2 of the inland mining locations. One is Karithura and there is Veluthamanal, which is Karithura is coming in the southern side of this IRL Chavara unit, and other is in the north side of them. And we have analyzed those samples in secular equilibrium after in the standard 3x3 sodium iodide detector and 6-inch shield. So and the energies used for estimation are for thorium-232 naturally for 26 the standard energy, thallium-208 energy 2.61, and radium-226 is for bismuth-214 1764 kV, and K40 1461. And all it is the calibration was done using argent, thorium, and uranium, and density corrections and interferences were accounted. For example, in case of potassium estimation, K40 estimation, actinium-228, which is having very low abundance gamma in 1459, that is also to be accounted. And this coming to the results, thorium-232 seems to be increasing in terms as the depth goes up to 3 meters to 4 meters, and then up to, and the fifth, we could collect only up to 5 meters sample. So it came down. So this indicates that only not the top level, which is actually much lower than the deeper levels. So yeah, in both the locations, the top levels are showing much low level of Gnome level, thorium-232 and radium-226. Whereas potassium-14 naturally being mostly associated with organic content of the geological matrices is higher at the top surface and lower as it goes down. It comes the potassium-14 comes down, and the ratio of thorium to uranium mostly varies from 7.1 to 8.2 here. Now, as the thorium activity increases, thorium to uranium ratio is increased. And we could observe in the different studies in monocyte, in Manawalakuruchi, it goes up to even 9, almost 9. And when we consider Indian average and world average unscale report values, it comes only to 2.2 and 1.4. And coming to the radiological parameters, radium equivalent was calculated, and external hazard index was also calculated. And external hazard index is actually against the world average, it has because of natural high background area. You can see how large the values are. So when the ratio is much higher, especially considering external hazard index, it goes from it's around 2 times to 55, 60 times higher from Indian or national average. So coming to the conclusion, the depth profile was of these two locations were estimated and quantified, and radiological parameters also were estimated and were found around 2 to 60 times higher. And the observed dose rate we could estimate in the air was 0.4 to 9.2 microgram per hour, which is almost same near to the what we could observe with our dose rate meters. And this indicates that the Gnome levels is for associated minerals and geological composition. It's not a surface phenomenon. It can go. It goes down to around 8-10 meters, or in some locations goes down to around 12 to 15 meters. So it again shows some kind of doubts on how these formations has taken place. If it has all come from Western Ghats, whether these all these minerals can still go down in 12 meter, 15 meter depth. These are the conclusions. And others are grateful to the support of Health Safety and Environment Group, RPSNF Group, as well as IREL Chavra Management. And thank you indeed for your patience. Here.
Thank you, Jason, for good presentation. Any quick question? I can take only one question. Yes.
Yes, sir.
You had taken samples from 2 locations, and how far away are these 2 locations?
In aerial distance, maybe around 5 kilometers.
Okay.
The first location, Karitura, is around 1 kilometer south of IREL unit, and the Veluttamanal is around 4 kilometers, 5 kilometers north of IREL. So
and how far it is away from the sea? Both are almost equidistant from sea?
Around 300 to 400 meters away from sea.
Both?
Both.
Okay.
Both.
So more or less similar as compared to the distance from the sea?
Yes.
Okay. Oh, thank you.
Okay, thank you.
Thank you.
If you have any more questions, please discuss. Thank you.
Thank you.
So the next presentation is by Ms. Riya De on the topic of numerical modeling of air flow and particle deposition in containment pipelines.
Can you just okay.
Hello, a very good evening, good morning to everyone. Myself Riyade, and today I am going to talk about our work on numerical modeling of airflow and particle deposition in containment pipeline. Now, we all know that in nuclear facilities, for example, spent fuel reprocessing and waste management plants, sometimes the radioactive liquids are often transported through pipelines. Now, what is the inbuilt safety feature in that? So there is a pipe-in-pipe containment system which ensures the containment of radioactivity. So what happens is that there is an inner pipe which carries the radioactive liquid. So here I have shown it here. And then there will be an outer pipe which is a solid pipe, and there is a gap between this inner pipe and the outer pipe. So there is an annular space between them. So this annular space is purged with particle-free air, and if any air activity comes into that zone, it can be detected. For example, if there is any leak in the inner pipe. So this is what is the purpose of this pipe-in-pipe containment system. So here in this context, the most important parameter for the effective use of this technique for monitoring is that the aerosol penetration efficiency. That means if there is any leakage in the inner pipe, can we detect it after some distance in the annular space of that pipe-in-pipe system? So the primary objective of this study is to understand the aerosol's transport and distribution using computational fluid and particle dynamics, which we call CFPD, through simulations. And based on this, we want to understand the effective leakage monitoring system mechanisms. Now here I have shown the simulation geometry where I have mentioned the inner pipe, hollow space and outer pipe thicknesses and the dimensions of these regions. So as I told, if there is any leakage in this inner pipe, it will come into this annular space. So this is our simulation area. So we have used a refined mesh geometry to discretize and solve the governing equations using finite volume method, and there are 4.79 million cells in this 1 meter long pipe. So here you can see these meshes are very refined, and near the wall the mesh is highly refined. So as we go towards the wall, the mesh size is gradually decreasing. This ensures the error in the simulation calculations is very small as compared to the other regions. So coming to the input parameters, so here in this pipe-in-pipe containment system, there will be an air inlet. Then there will be one probe which is used for aerosol injection port. And the next to that, there can be several ports for measurement. Here I have considered only one port for measurement, which is at a distance of 600 millimeter from this injection port. And the total length for this prototype containment pipe is 1 meter. So physically in experiments, we will do this experiment with a 4 meter long pipe, but for this present calculations, I have considered a 1 meter long pipe, and there will be an air outlet. So a suction pump will be attached to that, and based on the suction rate, air from this air inlet and aerosol injection port will come into that system, and we will try to detect if there is whatever aerosols we are injecting, can we get that information in port 2 or not. So this is the typical aerosol concentration at the injection port, which is 10 power 9 particles per LPM. And the aerosol size distribution, we have considered a log normal distribution with the CMD 1 micron and GSD 2.5, which covers this size range that I have mentioned here. Now coming to the governing equation, so this is just a glimpse of few equations important to the system, so there are many more. So here obviously we have the continuity equation for both the dispersed phase, that is the aerosol, and continuous phase, that is the air. Then again we have the Navier-Stokes equation, which is the momentum transfer equations. Then obviously we will have some particle transport equations. For example, the first equation you can see here is the equation that determines the number concentration of these aerosols as it move with the flow. And this J term is the source term. So here you can see two expressions of this J. The first term is the diffusion term, and the second term is because of the inertial impaction. So to give you an idea how long this simulation takes is that this approximately, for this 1 meter long pipe, for a 3-second simulation, it will take almost 1 week in a 300 nodes of a parallel supercomputing system. And these simulations are carried out using OpenFOAM aerosol code with OpenFOAM. And also we have introduced new modules for this, for our present study. And the particle depositions which will happen inside this containment system are governed by these 3 major parameters. One is gravitational settling, then there will be Brownian diffusion, and finally the inertial impaction. Now, why we need these CFPD simulations in this case? So our goal is to identify the critical boundary conditions that can govern this situation. So our target is how to model a suction system. So what type of boundary condition to be incorporated at the inlet and the probe locations. And next is how to understand the impact of probe location and aerosol inlet positions on penetration coefficiency, whether there is any dependency on that. And finally, to understand the nature of the flow with higher inlet flow rate, for example, whether it is linear or turbulent. Is there any dependency on the deposition because of this flow profile or not? Next is coming to the result part. So here I have shown the purged airflow profile at a steady state conditions in the XZ plane. So here you can see this red portion is the aerosol inject port where 5 LPM airspeed was there. And since the area is very small or narrower, that's why the velocity is higher at these port locations, and at the outlet also you can see how the air is flowing into that, coming out of the system. So to zoom it, you can see it here. This is the flow streamlines at the injection probe. And here some recirculation zones we can see. So these zones are very crucial in locally depositing aerosol particles while it comes into the system. At the outlet, similarly, we can get an idea about how the fluid is coming out of the system. And this is the profile for the pressure and velocity at the probe 2. That is the measuring point. So you can see the pressure is almost uniform, and there is a dip in the pressure at the probe locations, and velocity is mostly following the typical parabolic shape profile. And you can see the boundary layers, the blue lines, that the uniform boundary layers have been generated at both the inner and outer surfaces. Now coming to the aerosol part, so at this left side picture depicts how the aerosols are transporting into the system from the injection port. So here this is a pictorial representation of that. And finally, this is the penetration, particle penetration plot with the particle diameter for different injection injection port for different inlet, different suction rate at the outlet. So here this is the at 600 millimeter. Now I must stress that this is a result after 1 second. So we have to do this study for much longer time period, and this will take a much higher simulation time. And finally, we have to compare our results with the experimental setup. So coming to conclusion, so this study actually identifies the critical boundary condition, as I told, and this result highlights the importance of probe positioning. And in future study, we will explore the effect of the timing and sequence of the probe openings to ensure the reliable airflow and the aerosol data. And this framework actually will provide a robust platform for optimizing leakage detection mechanism and designing a safer and efficient monitoring system for high-level radioactive liquid waste transferring through this pipe-in-pipe containment system. Thank you.
So due to that paucity of time, it is kindly requested that questions, if any, may please be discussed during the lunch hour. And thank you for this presentation.
We have the last presentation from PLA Electro Appliances. Anybody is here? Yes, please. You have 10 minutes.
Hello.
Very good morning to all of you. I am Tarak Shah, Director of Ply Electro Appliances Private Limited. First of all, let me thank organizers of IARP conference who have organized such a conference and also giving me opportunity to present about the activities of my company. So we welcome you all. So our company, Ply Electro Appliances, was founded way back in 1965. We have over 50 years of experience in designing and manufacturing of radiation monitors in wide variety. In fact, we are the first private manufacturing company who entered in this field when there were others, there were nobody ready to enter in this field because of the fear of nuclear radioactivity. So we have strong association with BARC and DRDO since of many years. So many of you are already aware that we make very large variety of radiation monitors like survey meters, area monitors, hand, foot and clothing monitors, whole body monitors, portal monitors, organ monitors, laundry monitors, floor monitors, food water monitors, air and gas monitors, gate and vehicle monitors, etc. And this covers entire spectrum. That is the instruments required for nuclear fuel cycle, right from mining to enrichment to fabrication to reprocessing to nuclear waste management. Then we have instruments for defense, especially for nuclear war scenario, to detect the nuclear explosion and also to survive in the, or rather aiding the rescue team of the fallout rescue team. So then we have the nuclear disaster management instruments for nuclear disaster management people. So all the centralized police forces, NDRF, this SPG and this kind of agencies. Then for all the regulatory requirements by hospitals and radiographers and this kind of industry. So we have indigenized several Russian, German, American made radiation monitors like teledetectors, ronjonometers, contamination monitors, dosimeters, all this type of instruments. We have all infrastructure under one roof. So we are basically electronics company who specialize in nuclear radiation measurement. So we have facilities of as a electronics manufacturing company, then software development, then we have our own mechanical fabrication workshop and our own radiation calibration lab and test facilities. So our specialization lies in designing compact, low power and lightweight instruments. Our workforce is of around 115 people who are all skilled, and a majority of people are engaged, or rather nearly 15% of the people are engaged in new developments. There are various types of people. that is nuclear physics, electronic design, software designers, mechanical engineers, like that. And we do all this for to meet our, for our passion of indigenization. So this is our, we have our own radiation calibration lab. It is, in fact, India's first AERB recognized calibration lab, and it is the only private NABL accredited lab that can calibrate even the teledetectors, that is up to the range of 1000 R per hour. Our lab has, actually our lab consists of two separate labs. One is using cobalt-60 source and other one is cesium-137. Both the labs are accredited by NABL, recognized by AERB. This is our NABL accreditation certificate. That mentions the scope also. So now I talk about new developments, but which are nothing but endeavors to indigenize and make India self-reliant for at least the radiation protection instruments. So this is the first one. We have indigenized the teledetector, the automass teledetector, and we have done this, or rather we have been doing this since more than 15 years. It has got a small story. It was before some 15 to 20 years when Dr. D.N. Sharma had invited us to RSSD Mode Lab and appealed that if we can indigenize the teledetector. The work started ever since then, and then continuously we have gone on improving the teledetector. Obviously, the first first few teledetectors were not perfect. Then we kept on working. We kept on working on every aspect, be it telescope, be it its response time, be it its weight, its retraction, extension, then the sag, the energy response. Like that, one by one we have taken up several aspects of only one instrument, teledetector. So everybody knows teledetector, its range is from 1 microAR per to 1000 R per hour. Yeah. So in teledetector, we have gone even to the extent that we set up the calibration lab to do calibration up till 1000 R per hour. This is teledetector, I'll go a little faster. So very soon we will be coming with this graphic LCD type analog digital teledetector. Another instrument, German instrument, again COMO 170 as it is known as, we have indigenized with our own PCRM 170. It is 170 square centimeter effective area. It can detect alpha, beta, gamma, all the three simultaneously. And of course, single channel instruments are also available. The beauty of this instrument is its weight is only 850 grams and its ergonomic shape. Then, like the imported COMO 170, we have also made its attachments, like floor bogie to do the floor contamination check, then drawer assembly, then to filter papers for, then it can be used as a palm monitor also. Also, we introduced a miniature version of this same COMO instrument with 100 square centimeter, and with different scintillators. There are separate versions. If you want alpha, beta, gamma, it is there, only alpha, only beta. Weight is only 675 grams. So you can compare it with the weight of an Alcin monitor, which is 2 kilograms. As compared to this is only 675 grams. This reduces your fatigue when you do continuous survey. So then we have also introduced this famous instrument, Red Eye PRD. We could not reduce size to the one that Red Eye PRD stands, but then it has reduced, the size has been, rather I will speak in terms of weight. The weight has been reduced from 2 kilograms to only 300-400 grams. So it has been made wide range from 1 micro-hour per hour to 10 hour per hour. Its weight is very less. It has got sodium iodide scintillation detector. Even though it is a sodium iodide scintillation, its energy response is only 15%. And it is very quick response. It can detect a change in background only by 10 micro-hour per hour within a second. It has got rechargeable batteries also. Next instrument that we have made is, or rather indigenized, is portable spectrometer. So portable spectrometer has got a MCA inside, and it can also do the spot identification. And it can use as a micro-hour accelerometer, or rather wide range micro-hour accelerometer, 1 micro-hour per hour to 10 hour per hour. Then this new instrument, integrated radiation monitor, this combines all the instruments that I introduced in this few minutes back. So it is all in one. So it is a alpha, beta, gamma, then it is a micro-hour accelerometer, it is a wide range accelerometer, it is a spectrometer, it is an isotope identifier, it is an alpha contamination monitor, also it is a beta gamma contamination monitor. And it has got a good battery life, continuous battery life of 25 hours. So this is for ideal for even this. Yeah.
This time is up.
Yeah.
Please conclude.
So this one is ideal for emergency workers. This is another one which is ideal for emergency workers. This is a gamma portal monitor made by Ludlum. And the beauty of this instrument that it is folding instrument. It has got 6 detectors and thick plastic scintillation detectors. It comes in a carrying case, and you can take it to the site and install it within 7 minutes flat. And it has got a good MDL of 0.5 microcurie in a walkthrough mode. So this is another instrument by Mirion Technologies, GEM 5. So this kind of instrument, by looking only at the specifications, we have indigenized. So it has been made functionally same, whereas it is our own design, like all the previous products that I described. So this one has thick plastic scintillators. It is scintillators are of total volume is 80 liters. In the walkthrough mode, it is 0.1 microcurie cobalt 60. Then this is a remote radiation monitoring system, where this was required for a defense project, where there are multiple cobalt 60 sources in their ground. And so all these are wide range probes, and they have 2 GM tubes each. So 1 micro-hour to 1000 hour per hour. They want to do the environment radiation monitor of their distributed source, their ground having distributed source. So all these probes transfer the data to their central console by wireless RF network. And distance is, direct distance is 1 kilometer. It is using Zigbee protocols. So it can also, the distance can increase if you put the repeater. This was a test setup in our office.
Conclude.
Yeah, only
please
last.
Conclude.
Yeah.
Just 1
so
minute.
This is the last instrument. It is a multi-communication servometer. It has got a GPS sensor, and also it can transmit the data by RF, as well it can give SMS. Okay, so then there are many other instruments. I will just put it because we don't have time. So all these are indigenized, or rather some of them are made with DRDO Defense Lab Jodhpur. These are meant for NDRF. This was one, Praval Chaudhary sir is also there. This was for MRDS system for local police across 60 cities in India. This was the kit. In so many cities, this in the police patrol vehicles, this is installed. And these are some other pictures of training and other things. And thank you.
Sorry to interrupt you, because there are many slides. It was very informative, but unfortunately we are running out of time. Thank you all the speakers and my co-chair for chairing this session. I'm sorry that we are delayed for 15 to 20 minutes, and we close this session here.
Thank you, speakers. May I please call upon Dr. K.S. Pradeep Kumar, former BARC, to present mementos to the chair, Dr. P.P. Haridasan, and co-chair, Sri S.N. Tiwari. We will now take a short tea break. I request everybody to gather in the auditorium at 12:10 p.m. I request everyone to gather back at 12:10 p.m. There is an announcement. An informative brochure on topic Industrial Safety Practice in Radiation Facilities based on paper T7001 is available at Help Desk. Some 50 copies of these brochure are available. Interested can collect it from the Help Desk.
Hello. 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 Hello.
IARC, joined Biaba Atomic Research Center in 1991 after graduating from 34th batch of BARC Training School. Currently, he is heading Radiation Safety Systems Division of Health Safety Environment Group BARC. His expertise is in meteorological, atmospheric, groundwater, and aquatic dispersion modeling, as well as radiological impact assessment. He has developed several atmospheric dispersion models like equidistance puff model, particle trajectory model, area source model to study dust dispersion from open cast uranium mines, as well as multiple source model for carrying out dose apportionment for thrombosite, 2D oil spill model to study the dispersion and deposition of oil spill around Mumbai coast, and BARC Lagrangian puff local scale atmospheric dispersion model. The atmospheric source term esteemed by him for Fukushima Daiichi nuclear power plant accident was in line with internationally accepted values. The co-chair of the session, Dr. S.M. Pradhan, RP and AD, VARC, Shri S.M. Pradhan, occupied his MSc in physics and diploma in radiation physics and is working with the radiological physics and advisory division of VARC Mumbai. He has extensive experience in TLD based monitoring of radiation workers to access occupational exposure to external ionizing radiation. He is currently involved in quality assurance and performance monitoring of the TLD laboratories in the country. His research interests include developing dose algorithms involving uncertainties in TLD-based personal dosimetry, enhancing the reliability of small dose measurement, and analyzing glow curves. He is a member of AERB committee to review radiation exposure cases. He has published about 50 papers in different journals and has written 3 book chapters. We are handing over the session to the chair and co-chair.
Hello. Okay. Thank you, madam. So in this session, we have a very interesting papers as well as the invited talk, because I think the internal dose anyway, it is the one pathway which is really very difficult to estimate, but at the same time, it is the most important pathway also. And we have with us Dr. Pramila Sawant. So we have with us Dr. Pramila Sawant. Dr. Pramila Sawant is currently, she is heading internal dosimetry section of Radiation Safety Systems Division, BARC. And her research areas include internal dosimetry, decorporation of radionuclides, and analytical chemistry. Also working on rapid bioassay procedure for emergency situations, screening methods for urine using LSS technique, speciation studies of actinides in human body, development of in vivo monitoring, and development of internal dose coefficients for Indians. So with this, I welcome Dr. Pramila Sawant to give the invited talk.
Next one. Previous.
Put this. Leave. So my timer has started. Okay. Good afternoon, everybody. Dignitaries on the dais and off the dais. Today I will be talking the challenges which we are facing in internal dosimetry in case of radiation emergencies. The work which I am presenting is the work which is being carried out by my section, by my team people. So the topic is building resilience, effective strategies for monitoring of internal contamination in radiological and nuclear emergencies. So these are the points which I will try to cover. I will give a brief introduction of the past incidences which have happened so that you can correlate what are the difficulties which we will be facing as internal dosimetry professionals. So let us see now. So as you all know, in the recent years, maybe in around after Hiroshima, Nagasaki, in the last 30-40 years, we have seen that the radiation, application of radiation has increased, and so has the risk. Certain incidences have taken place which you all may be aware. That is, one is Goiânia in Brazil, Chernobyl, Fukushima, and one polonium poisoning case which has taken place in UK. So after any radiological and nuclear incident, workers, responders, public, everybody may be exposed to external radiations or may be internally contaminated. And in such cases, it is necessary to have a public health response in time. So today my topic is on rapid screening, how we can do it and what are the challenges we are going to face in the implementation. So you just see, in case of large monitoring, you may have to carry out decontamination of actually contaminated patients, and you may also have to treat some people whom we say are worried well. That is, we take into account psychosocial things where the people feel that they are contaminated, but actually they are not. So you have to deal with lot of public adults, old senior citizens, patients, as well as these people who are worried well. So what I am trying is, over the years, under the guidance of Dr. Pradeep Kumar, when he became our head and we were transferred to RSSD, and Dr. D.D. Rao, we got the experiences of working on radiation emergencies. Till then, we were this field was confined to radiation protection of radiation workers. Slowly, we tried to understand what is our requirement in the field of internal dosimetry in case of radiation emergency. So now I am going to, in this topic, understand the capacity gaps which we will be experiencing. What are the challenges in managing internal contamination? If somebody is internally contaminated, you may have to decorporate and carry out medical management. That is another extensive field. And what is internal dose? When the radionuclide goes inside, by whatever route, maybe inhalation, ingestion, absorption through skin or wound. You use different methods like in vivo techniques or in vitro techniques, and based on that you carry out assessment. That is known as internal dose assessment. So just for briefing the students over here, what was the Goiânia incident? Goiânia incident happened in 1987 and there was an unsecured radiotherapy source of cesium-137, approximately 51 terabecquerel.
which was stolen, and it was handled by many people, resulting in death of 4 people and around contamination of 1,12,800. Just see the capacity. I have given the name of people who are required to be monitored in certain situations, and out of them only 250 were found to be contaminated. But the monitoring was large scale. Actual people were only 250 who had internal contamination. And the incident came to, the authorities came to know about the incident after nearly 2 weeks. Then there was a Chernobyl incident, which is quite famous, which took place in Russia. We happen to know this Chernobyl incident because regularly the ESLs of our Indian nuclear power plants monitor goat thyroid. So goat thyroid showed indication of iodine 131, whereas our nuclear reactors were working fine. But Tarapur, Hegde sir was there, and the goat thyroid showed iodine 131. That indicated that some nuclear incident has taken place. And slowly it was realized that it was Chernobyl. So you see, iodine 131 was so volatile that it was detected in India, and the incident had happened in Russia, Chernobyl, now in Ukraine. And the fallout forced nearly 3 lakh, around 3,50,000 people to evacuate from their place. So this is another social psycho factor which we have to take into account when such incidents occur. Then the next incident, only 4 incidents I will be talking about. The next incident was of polonium, where a Russian spy was given polonium, 2.6 microgram around, and this led to monitoring of around 700 people. And out of that, only 138 people, and this was by urine measurements. The hospital, the offices, the whichever place he has visited had to be monitored. And polonium being alpha contamination, it has a gamma of 803 keV, but the abundance is very, very less. So it has to be detected by alpha, and for alpha contamination, we already had a technique with us, and similar technique was used in UK, and it was found that 139 people showed contamination. Out of that, 36 people were in the range of 1 to 6 millisievert, 17 greater than 6 millisievert with the highest dose of 100 millisievert. So this is what we have to monitor in case of radiation emergency. If you have to give any decorporating agent, you have to act very fast. That's why I'm saying rapid screening is really required. Then next is Fukushima incident. This incident we know killed many people due to the natural disaster than radiation, but you had to monitor nearly thousands of people to find out what was the internal contamination or whether there was any radiation exposure. So be it you go for follow-up or you go for decorporation, initial phase you have to screen the people for internal contamination. So you just see now, I'm given an example of Goania. This is the famous slide where they had done the contamination monitoring. You see the number of people who were monitored during medical triage, 1,12,800 people. Out of that, people contaminated were 1,129, not even 0.1%. To detect this 0.1%, you had to monitor 1 lakh people, and then some people had contamination, some people had bone marrow depression, some people had acute radiation syndrome, and there were death of 4 people. So when you come for such situations, you know you have to do medical triage, you have to monitor people and survey the environment also for contamination. Medical treatment has to be initiated immediately. Now if it is internal contamination by inhalation ingestion, it's okay. In case of any wound injury, you may have to go for excision of the wound. So that is additional thing which the doctors have to do. And important point, like Dr. Shukla has said, clear information to the public. This is also very, very important. You should not hide things, but to give clear information, you should have some data, some monitoring data of the environment and the people to give them assurance that you are safe. So for this purpose, my colleagues at IDS have developed multiple systems. We are slowly moving. Though the speed is slow, we are trying that we have some portable systems which can be taken for field operations in such situations. The first system which was built during Rao sir times is the portable wound body monitor. This is at GCNEP in Hisar. We have placed this system. Now slowly we have changed from, we have changed from this dimension to a standing posture so that maximum area of your thorax is covered in this. And this is a very sensitive system, not for radiation monitoring, but yes, for emergency, yes. It is 10 times higher detection limit than what we use for routine monitoring, but still the dose detected is in microsievert within a day. And such systems can be taken at the field for monitoring of people. We may have to multiply these systems and place in ERCs. That is the biggest challenge which we will be facing now. And these are the lab-based systems. So in case you detect people, medical triage is done, you find them significantly contaminated, such people can be brought to all over India. We have ESLs or the facilities where whole body monitoring can be done to record an accurate or realistic assessment of those. But in case of emergency, portable systems are much more sufficient. Then this is the thyroid monitor, and this system also was used during Kakrapara incident during Pradeep Kumar sir's time, and this is a portable system. This single cylinder we detect with a sodium iodide detector placed inside it, and this system can be placed in ERCs in case of any emergency response needed at that particular place. And then similarly we have lab-based systems. So I am just showing you that lab-based systems are there, but they cannot be used in case of emergency. That's why we have gone for portable systems which can be used in case of any radiation emergency. This is a quick scan monitor again. Mainly most of the ESLs will be slowly getting it. So in case a portable system shows any contamination, after decontamination for realistic assessment, you can count the person over here, and within a minute you may get what is the burden present in the whole body burden present in the contaminated individual. So for this we have done technology transfer to 3 parties. Now this is very important, contamination in wounds. In case of any explosion, sharp nails, it may enter the body, and you may have to remove the sharp nails as well as the tissues. And you may have to identify at what depth you may have to go to remove the tissues. So slowly with the experiences we have gained, we have developed the SOP, my colleagues at IDS, and we now exactly can help the doctors in wound excision. But this is in specialized in this, but in actual scenarios, this may be a real challenge. And what we are going to do during certain situations, maybe we may not be able to immediately tell the depth, but yes, we can tell the activity present and at what part it is present, so that they can carry out the excision of the sharp nails. So these are the systems which we have. We have an array of HPG detector. These are very specialized systems. This cannot be taken to the place where it is required. This is for low energy photon emitters, and we have some LED, you can see it here, shielding type of thing, so that we can map the wound. Where the activity is present, we can map it using this, and by this studies which we have carried out on Monte Carlo, we can estimate the depth of the wound, so that when during excision, none of the nerves get damaged by the doctors. This was a very important work which was done in our IDS. Now slowly from this specialized system, we are moving to wound monitoring system. First system has been developed. So if you see over here, this is the system which is being developed. It is there in our laboratory, but only single system. Slowly we may have to multiply such system. We are trying to make it trolley based, so that it can be taken wherever required. We will be slowly supplying these systems to all ERCs, so that we not be present everywhere. Even the ERCs can take up once the protocol is standardized. And then we are making it also for low energy photon emitters. In addition to that, we are also going to do probe type of wound monitors, so that some specialized system like this are not required. Even the probe can tell you where the contamination is and then what depth it is. This is the system. This cannot be made portable. This is for inhalation of low energy photons, and this is a very specialized system. You require specialized detectors, you require specialized shielding. So in such case, if you have to know the internal contamination, you may have to bring the person to such facilities which are present at NFC Hyderabad, at Kalpakam, and in Mumbai and Tarapur. So only 4 places in India have this system. So it will be very difficult to, we are not talking of 1 or 2 or 6, we are talking of 10 to hundreds and thousands. So all these challenges we may face in actual emergency. So how we are going to meet all this, really I don't know. So we are working, our mindset is changing on how we can do this, but as of now we are not able to do it. But yes, then this is a vehicle mountable system. So this we came to know from Chernobyl, where the food and everything was contaminated, and the people in Chernobyl area are monitoring their own products. Even the milk, before selling, they take it to a counter, they measure it over there, and then they sell it, or then they drink it. So this led to a vehicle mountable system. So based on the experiences gained in the past, we are trying to develop the systems which can be used in case of any unfortunate event incident takes place in India. So whatever the system is so simply made that any person, any public person also can keep the sample, just press a button and he will come to know the activity present in the sample. So this is very important because we cannot be there everywhere. We are experts, we need to develop the skill with the people, we need to develop the skill with the university students. So public participation is very, very essential in case of any radiation emergency to handle internal contamination. That's why nowadays the word used is integration of citizen science. So this is very, very important. You have to make the people part of the monitoring so that they exactly know how to monitor themselves. The thyroid monitor can do it, the whole body, all the systems are just press a button. You have to stand there for 1 minute and you will come to know what is the activity. Press the button, you will come to know what is the radiation level, gamma emitters, all these are gamma emitters. You will come to know the activity present in the food, soil or vegetations. We have made such 5 systems, but the detectors have not been available. Once the detectors come, these 5 systems will be given to ERCs, DA-ERCs, 5 DA-ERCs. These are the phantoms, so these are available with us. Whichever system we have developed, we require these phantoms for calibration. So physical phantoms are not available with everybody. So now ICRP has come up with voxel and mesh phantom. So we feel that all the laboratories which are dealing with whole body monitoring should have the expertise on mesh phantoms. So that's why I presented over here, or in the universities, if you can include it in skill development, this will be a beneficial thing. So even for pregnant ladies, so they have covered complete spectra of population, from newborn to pregnant ladies to adults, everybody for different postures. So in case of any emergency, you will come to know different postures, what would be the calibration factors or what would be the intake in that person. Now the things change when it comes to biopsy. Biopsy, I mean urine analysis. So in case of alpha beta, pure alpha beta emitters, it's a very big challenge. You may have to do urine analysis. So first thing we started was by preparing a protocol if the incident takes place in some other place, like it takes place in Madhya Pradesh, the samples may have to reach Mumbai, but there was no protocol for that. So slowly we started how to pack the samples, how to bring the sample, what should be the volume of sample which should reach to our laboratory or any other laboratory which can carry out certain things. So this protocol is established now, how the samples will be reaching, whether we will have to cool it and bring, whether you have to add acid and bring, all the protocol is now ready with us. So if you go for urine analysis, it takes nearly 4 to 5 days for single analysis. But 4 to 5 days you cannot wait in case of radiation emergency, because you may have to give decorporating agent, and that within 6 hours you have to take a call. And you have to tell the doctors or the RSOs over there that whether decorporating agent is required or not required. So in that case, load is on people who are carrying out the analysis. So for that purpose, we have come from sensitive technique to rapid screening technique. Instead of using ion exchange which takes 8 hours, we have gone for solvent extraction chromatography, where the solvent is covered on silica and then we carry out extraction. There are very specific extractions for uranium, polonium, lead, you name it, and the extractants are available. So what we have done, gross alpha, gross beta initially by LSS, and then if you want to know the specific radionuclide, you can go to this type of systems and you can finally analyze it with alpha spectrometry. So this is one of the things of polonium which I said. This technique was already available. My predecessors had developed this technique and this system, but silver planchets were required. And every laboratory may not have silver planchet, but most of the laboratories have stainless steel planchets. So we developed this, we changed this technique and methodology so that whatever is available in the market can be used. Even copper, stainless steel and nickel, we have standardized the method with that and which can be used. Similarly, when this incident took place in UK, the reporting level was 30 millibecquerel. That is below 30 millibecquerel means the dose is less than 1 millisievert. But polonium is naturally occurring in our body, so it is naturally occurring in urine. So what we did is, we collected sample from members of the public to find out the range. So our range was from 5 to 15 millibecquerel and the average was 11.7. So before reporting that value is 30 or no, we have to subtract this baseline. So baseline data has already been generated for Mumbai population. I cannot say India, but for Mumbai population, we have generated the data. So if no data is there, at least 11.7 can be subtracted before assigning any dose. Now this is the, I can say, workhorse of internal dosimetry. We have multiple systems, and so these systems are also available with ESL. So we have targeted our rapid screening techniques using ESL, these LSS systems. Additional system which we have is this portable system. This is a triethylar from Hydex, so that we can carry it to the field, but it is sensitive for beta. Alpha, it is not yet capable. I will show you why. These are the limits at which we have to detect. You can see MDA and the derived urinary excretion within a day. That is the value which you have to detect. 4.2, 4.3, 900, 0.4 and 1.5. And what we get is MDA, what we have achieved. And this is based that you take urine, whatever comes to you 100 ml, just take 5 ml, add 10 ml of the cocktail and keep it for gross alpha beta. With that, we were capable to detect most of the things except plutonium. Plutonium we have to count overnight. Then only we were capable of detecting plutonium. So 1000 minutes counting was required. Procedure is well standardized and validated. Then we went for separation technique. We have not only urine sample, we may get nasal swabs in case of any incidents. We may get wound, we may get fecal sample, we may get filter paper sample. So all this together, what we did is we developed a technique, just ash them, make it into solution and take 1 ml aliquot of that, put it in the cocktail, and the method was standardized. Now though what we are planning is plutonium-239 being alpha, we are not able to detect, we require 1000 minutes. But plutonium isotope, plutonium-241 is a low energy beta emitter, which may be 20 times higher in activity compared to alpha. So we are targeting to detect plutonium-241 in the samples. If we detect that, we will slowly come to know that whether plutonium contamination is there or not. Similarly, the techniques have been developed for strontium. So mainly we have done initially gross alpha, gross beta, and then we have gone for specific radionuclides. This is these are in future, maybe we may have HRIC PMS, which may reduce the burden. Then we are trying to automate slowly things. So LED fluorimeter which we have automated. So instead of a single sample, now we can do 16 sample at a time to reduce the workload. So multiple systems if you use, maybe you will detect uranium faster and you may take some action. Then lung monitoring system, yes, this is a very specialized thing, we cannot make it. Then we had one mobile radiological laboratory initially. Similar type, we may have to develop a mobile biopsy unit which may have a whole body counter, or certain systems like LED fluorimeter or a triethylar type of things, portable gross alpha system, so that you know that vehicle itself be taken instead of the samples coming to our laboratory. So yeah. These are the automation systems, because we cannot be there everywhere, nor everybody is expertise. So we are trying to develop automation of radiochemical samples. This we have done with Nokia Technologies. The system has come, but there are some software issues, so we are trying to resolve them. Now, main challenges come. This is in routine also we are facing the challenges of decorporation. Now, when decorporation come, it is to be done by a skilled medical professional, not by us. So, internationally they are trying to have decorporating agents which can be administered orally. This work is going on, but still a lot of research is required. Even DTPA replacement has come, that is HOPO. Recently I came to know this chemical is 10 years of research, more than 10 years of research on HOPO. Maybe within 2-3 years it may come to market after FDA approval. Now DTPA, we are getting it only from Germany, and it is really very difficult for us to get it for routine. So emergency, I really don't know what we will be doing. Prussian blue, yes, we need not import it because INMAS has made some Prussian blue, and they have done the technology transfer which can be used. But DTPA, they may have to work on it still. They have not started the procedure. So you can see once DTPA is given, multiple injections, multiple monitoring has to be done. So this is another challenge. So all these things for routine is okay, but in case of emergency, this is going to be a very challenging task. So we need to develop pockets all over India where, you know, we can get support from them. Maybe universities, maybe institute like Career, maybe Hisar, so where we can get support and they can aid us in doing the monitoring of individuals. So quality assurance I will not go, maybe I don't have time, but yes, this is important for sustainability. Maybe like Pradeep Kumar sir said, we may require manpower and all, but we have to also sustain them. Maybe emergency may come, not come, but sustainability is very important. Capacity building and capability building along with sustainability is important. So in case no emergency is there, we may have to have intercomparison exercises for quality assurance so that the people involved come to know that this is important and you have to maintain the quality when you are assessing the dose. So I will just skip this. Software development also my colleagues are doing so that we need not have international 2 minutes. So we need not have dependency on international import of software. I will not go into the details of this now. So this is what we are targeting. We have 25 DAERCs and we have some NDRF and some centers like this, which can be groomed, can be trained to help us in rapid screening in case of emergency. This is extremely important because there are hardly 20-30 people in internal dosimetry who are expert, who cannot be there everywhere. So I really feel that this appeal goes somewhere that we need to have a group of people. I don't say that let them do internal dosimetry daily, but yes, they should have the required capability or skill to analyze in case of radiation emergencies. So for that, what we have done is, we have developed an IndosNet network, and what I thought is, this was during Suresh Babu sir's time, so that we can bring all the people who are there in India doing internal dosimetry come together. So in case of any mass scale incident or accident, they are available and they are on same line as what we are talking, they understand. We have done 2 meetings up to now, and we are slowly trying to develop systems and give to them so that they understand what is the requirement and they can help us in such incidents. So this is my last slide. Preparedness and response of any off-normal situation is always an evolving and dynamic assignment. We are not saying that we have completed everything. It is evolving. As the challenges come to us, we will be evolving. Lessons learned from the past incidents, because we do not have any significant radiation emergency over here. But yes, we are following it up internationally, what are the requirements, and we are trying to groom ourselves in that direction. But so far, so small. A lot of work needs to be done in this, and that is what I have written, miles to go before I sleep. And thank you very much. I thank the organizers and my seniors who have guided us in this.
Sir, please.
Congratulations for the leadership for developing a good team, a good laboratory. But I like to continue from the last what you told. We have to go ahead. So the question is, internationally it is identified the potential for illicit trafficking, radioactive sources smuggled into different countries and being used for dispersion or even in explosions.
Yes, sir.
See, in such scenario, due to single radionuclide or multiple radionuclide, through various pathways, people can get the internal exposure.
Yes, sir.
So such a scenario, when large number of people, maybe 300 or 400 people are suspected to have radioactivity in them, and it can take place anywhere in the country, need not be near to your laboratory. How you are planning and going to give an assurance to the country that yes, we can take care of them, and at the earliest we will be able to monitor, assess, and even administer the protective, decooperating agents, etc. Okay. What is your plan?
Sir, that is what I said. We are slowly moving at the scale of a tortoise walks, because to integrate, because everybody has their work, ESL has their own work. Now they are ERCs for us, so they have their routine work, and then we are enforcing something on them which needs to be done. So that is why I have made this network, So they understand the requirement. They will be busy responding to environmental monitoring. In addition to that, we will be giving them load of individual monitoring. So this needs to be sorted out. So we need to develop center of excellence, maybe at university level or colleges level, but as of now, I have not thought of it, how we are going to go about. Maybe we may guidance from you only that how we need to implement this, because it's very difficult, sir. And unless you train the people, it's difficult. So I cannot comment on this, that how I am going to do, because it will require inputs from the students, from Center of Excellence, like Dr. Karunakara said. So when he said yesterday in the panel discussion, I thought, yes, this is the way we can move about. But how to do it, I have not thought of it. Okay.
Thank you, ma'am. I request Chair of the session, Dr. Oza, Head RSSD BARC, to present the memento to Dr. Pramila Sawant. We'll now move on to the oral presentation, and I request the chair and co-chair to take over.
Yeah, moving over to oral presentation, we have got first presentation in this session by Athira B. Warrior Isaac. Topic of presentation will be contamination monitors calibration system.
Good afternoon to all. Myself Athira B. Warrior. I am working in Radiation Application and Technology Division, Safety Group, Indira Gandhi Center for Atomic Research. My field of work is calibration of instruments. Today I am going to present a calibration system for alpha-beta contamination monitors. Okay, as you all know, contamination means the presence of radioactive material in a volume or surface where they are unwanted and undesired. So this contamination is a significant concern in radiological facility where there is a potential spread of radioactive material can lead to hazardous condition to both personal and surrounding environment. So this contamination can be caused by the spills or leaks from radioactive material, use of unsealed sources, and airborne radioactive material deposition. These all can cause contamination. So we should monitor this contamination, because monitoring only helps us to determine whether contamination is there in that area, to prevent its spread, check whether the contamination are in prescribed limit, and to detect breach in containments. And for good working practice, we have to monitor this contamination. And we all know that monitoring can be we can't do with our sense organ. We should require some instruments for monitoring purpose. So these are the figures, some of the portable surface contamination monitor instruments. These instruments are based on GM based detectors are there, scintillators are based detectors are there. So many contamination monitors are available. Now, so the question is like whether we can whatever the values they are showing, we can reliable on that, how much accurate it is. There comes the need of calibration. So now this calibration is very much important for our safety practices and emergency response cases. So here we are introducing one novel calibration system for the contamination monitor. So what is the advantage of this one is like, it is incorporated with automated source movement, and also it can enhances the efficiency and eliminates personal handling of radioactive sources. Here we are using large area traceable source, and we are having a fixed reproducible distance. Here the calibration procedure mainly consists of two steps. One is like we are finding out the efficiency of the detector. Next one, we are calculating a conversion factor. This conversion factor tells about the relation between the net count and the activity per unit area. So these are the two things mainly we are calculating here. Now this figure shows our contamination monitor system. Here this system is having a dual security feature. So only authorized person can only operate the system. This dual security is, first one is password protection, and second one is we are having a key. So with key protection and with password, we are securing the system. And the system having a dimension of 1000 by 400 by 1000 millimeter and around a weight of 70 kg. Here this system, here we are having a detector location. When the system is in home position, safe powered off situation, we are detector location, we are covering with this protective covering plate. And we are having 4 indicators in the system. For safe storage position, we are having a red indicator, green indicator, and 2 sources corresponding to that 2 red indicator. And for the transit position, we will be having a orange indicators, and these indicators will show the status of the source. So here we are having 2 sources, one for alpha, one for beta. For alpha, we are using americium-241, and for beta, we are using strontium plus yttrium-90. And these sources having an activity of 1 kilobecquerel and an uncertainty of plus or minus 3%. And these sources are traceable to section of radiation physical and chemical measurements, metrology and technical supervisory department, government office of the capital city Budapest. And here that's I already told the system having an advantage of we are having a large area traceable standard source, so the detector can see a uniform source, and already that detector placing this location which is having a active dimensions of source which is coming around 250 mm by 170 mm. And we are able to produce a fixed reproducible distance we are maintaining here between the source and the detector. So normal cases what we are using disk source and we are calculating, that time we are the detector is not seeing full area of the source. Here we can see that, and we can't tell that whether we are always keeping the distance fixedly. So fixed, so that here we can able to keep a fixed distance, and also here the detectors is a uniform source. Now you can see this is the calibration certificate we got for our sources. First one is for strontium plus yttrium-90, and second one is for americium-241. And these sources are calibrated as on April 2023, and having an activity of 1 kilobecquerel, that is measured with an uncertainty of plus or minus 3%. And now how we are doing this calibration procedure is like, first once we get the instrument, first we will do the visual inspection, whether the detector is connecting wire, detector probe, everything is in good condition, and what battery status, all these things we see. First we will do visual inspection of this detector. Then after that, detector location you can see here, there we will place the detector, and after placing the detector we will take the background count. After taking background count, according to this contamination monitors, if it is corresponding to alpha means we will select the alpha source, if it is corresponding to beta contamination monitor means we will select the beta source, and we will calculate the gross count. Now we are coming to the results. So what we are here doing is radiological calibration determine the counting efficiency for activity measurement. Here we are placing the detector over a planar standard source of non-activity, and gross measurement we are taking. Now we are getting the net count by subtracting this background from this gross count, and we are finding the efficiency in terms of CPS per DTPS. So efficiency is calculating as per gross count minus background count divided by activity in that detector area. So we know that the activity per unit area we will calculate, and into the detector area we will multiply and find out the detector area activity. Now next one is like we are finding the conversion factor, because activity per unit area is very much important for the users, because the contamination levels, all these things, regulatory compliance, and for facility licensing, this contamination limit they will be expressed in terms of becquerel per centimeter square. So we are finding out the conversion factor. So, and we will express this conversion factor in CPS per becquerel per centimeter square. And the conversion factor is net count rate divided by the activity per unit area. As on April 2023, for our source having an for ammunition 241, 2.35 becquerel per centimeter square, and for strontium plus yttrium 90, it is 4.5 becquerel per centimeter square. So, this calibration system ensures reliable and efficient performance of contamination monitors, and by incorporating automated source movement, we can avoid the manual handling. It can enhance the safety, and use of traceable large area standard sources and fixed reproducible distance between sources and detector provide consistent and reproducible calibration results. These advancements contribute to improved contamination monitoring practices, aligns with the goal of radiation safety and sustainable nuclear energy development. Further work, we are our focus on expanding the scope of this contamination monitor by different types of all the detector we can calibrate, and diverse contamination scenario, different types of energy levels of energy sources. So this is all about our contamination monitor system. I am very grateful for this opportunity. Thank you for your time and attention.
Yeah, we can have 1 or 2 questions from audience.
Yeah, it's a very good presentation. I just wanted to know, these contamination monitors are generally used for contamination on the floors and surfaces, right? So there will be some dust load and all those things. So are you taking into account, or how it can be taken into account, the attenuation, especially for alpha, there will be attenuation due to the dust on the surfaces. So your calibration, your efficiency will change when you really do it on the floor as compared to your standard.
Sir, actually, if you go through so many books and standards, they are telling that whatever the planned scenario during calibration, whatever the real scenario, that we can't make it in the calibration laboratory. For any type of instrument, it is not possible to make that real scenario in the calibration laboratory. What we are doing in our calibration laboratory, we are having a standard source with a fixed distance, with a environmental condition also we will note down what are the environmental condition we are doing that calibration. With that, this much the value we are getting, we will report them. This is the thing for this type of source. So whatever the planned scenario, whether there will be efficiency differences, that all, like we have, if they are taking some samples here, we are checking that one, then only we can tell. Now with our calibration laboratory, we are having a standard source. With that, we will mention the value what we are getting.
Yeah, that is okay. But probably if you can think of some theoretical calculation for
yes,
attenuation.
Sir, yes, sir. Actually, this is now we are developing the system, sir. We have to find out. That is what I am telling. Our scope is diverse contamination scenario also. What we are doing is like exactly not that we are, and we are seeing so many different sources also. Here we are only having one sources. So that all we have to expand the scope. In that we have to expand these all things, sir.
Thank you.
Yes, one more question is regarding what is the uncertainty associated with your calibration?
Sir, uncertainty calculation, actually for their activity measurement, they are giving plus or minus 3%. And for our this one detector fixed, it is a fixed distance, no? For area measurements, that 250 by 170 mm, actually they are not giving any uncertainty of their area measurement. So as for us, I am considering as a 0.1 centimeter is the uncertainty. With that, when combining all these factors, with our uncertainty is coming to 6 to 7%. I'm not taking the detector things. Now if I'm taking detectors, this standard background values and mean values, if I'm counting into, that varies, depends on different detectors.
Yeah, thank you.
Okay, thank you.
Next presenter is Mr. Lokpati Mishra, RSSD VARC. Its topic of presentation is online actinide in vivo monitoring portal and overview.
Hello. Hello. Very good afternoon to all. First of all, I would like to thank the organizers and my parent organization BRC for allowing me to be here and present my work. So the title of my talk is Online Actinide in Vivo Monitoring Portal, which we have recently developed, and I will give a brief overview of this portal. So those who don't know, I work in Actinide in Vivo Monitoring Lab. This slide is. So our lab is situated at BRC Hospital in Mumbai, and what we are doing, we are assessing internal contamination in radiation workers, mainly for plutonium, uranium and americium or other actinides which emits low energy photons less than 200 keV. So in our lab we have two systems, detection systems. One is based on array of HPG and other one is based on phosphorus detector. Both these systems are housed inside totally shielded steel room, two different steel rooms. So workers from fuel fabrication facilities like UED, AFD and IF3 etc. Also workers from fuel reprocessing facility, plutonium plant, FRD, and workers from radiometallurgy as well as radiochemistry wing of RLG are regularly coming for in vivo monitoring to our lab. Sometimes we get monitoring requests from RMC as well as research reactor and waste management facilities. So basically our communication with these facilities is through health assist or RSOs. So on an annual basis, we are monitoring around 500 radiation workers from about 20 to 25 facilities. And this whole procedure involves basic 3 steps. So our communication is through a BRC form 10H. They send a form with the worker and we do the measurements and we do data analysis, and whatever results are that we report. So till now it was, the whole procedure was manual. A physical form has to be sent, then we do manual analysis and then we create report and send through, nowadays we are sending through email. Sometimes we face a problem, either form is missing or some report got missed or some scheduling, /scheduling problem is there. So we thought that we need to streamline this procedure, and therefore we have developed this whole procedure in a digitized platform. So for that we have developed this Actinide in vivo monitoring portal. And this portal, the beauty of this portal is, those who are aware, in BRC, some of the facilities which is inside BRC, those we can't access from outside Trombay premises. So this portal is hosted in Anunet based server. It can be accessed from within BRC as well as from outside BRC, and through this AIVMP anunet.in it can be accessed. Some very important features I will try to describe in this presentation. So this was developed using Angular open source framework for front-end development, and for back-end we have used PostgreSQL database management system along with Redis and Nginx web server, and also Python-based fast API was used for various applications development in this portal. So basically any plant, if you want to use this facility, first and foremost the plant HP or RSO need to be registered in this portal, and there are different role-based login in this feature, and these are 5 important logins. So first is for health physicist. Health physicist is assigned a role so that he can register radiation worker of their respective facility, and if he want to send for monitoring, then he can fill 10H form online, and once the monitoring is over he can view their respective report. And the other login is for lab user, which is for our lab. So the lab user can perform the analysis of the results, and also they can create the report. And officer in charge of our lab will verify the reports, and then they can recommend for further approval from head IDS. Head IDS will scrutinize the report and approve. Once reports are approved, it can be viewed by the respective plant. Also there is a login for super user. Sometimes different admin features are required, so super user can take care of that. This whole communication starting from health physicist, registration, health physicist to lab user, then OIC and head ideas is online. Automatically in each step, an email is generated and sent, and accordingly, whatever action is needed, that is taken care of. So, whenever a health physicist want to send for monitoring, he need to register for the first time the worker, basic details like name, his employee number or pass number, date of joining, and his picture is taken, and the worker is registered. We have the provision to acquire fingerprints as well. It is implemented. As of now, we are not using, but it is there. Once the worker is registered, all the details will come in the left side of the portal. And for any monitoring request, we are having different types of monitoring, like routine, special, follow-up monitoring, or task-related monitoring. For each monitoring, different parameters are needed. The essential parameters will be marked in red star. All those parameters will be filled by the HP, and the form will be submitted. All these forms will come to our lab, and this list of form will come as a pending list or accepted list or processed list. So basically in this list, each form we will scrutinize all the details. If everything is okay, we will accept that form, and an email will be sent to the HP with the assigned slot. And on that particular slot, the person will come and we will do the monitoring. And once monitoring is over, we will analyze the analysis is also carried out in this portal. For analysis, first of all, we have to choose the date of counting, and then we have to choose detector. We have two detectors, so either of which or both we will use. And then in which geometry we have measured, whether bone, liver, knee, wound, or lungs. On routine basis, we do lung counting. And for each counting geometry, there will be different background files. So appropriate background files we will use, and then we will perform the analysis, and these analysis is carried out in this portal automatically. All the results will be stored in the database, and then these results will be used for generating the monitoring reports. So the monitoring report feature is also very interesting here. We can generate the report plant wise for each plant, for each division. For each detector, we can generate the report in any monitoring interval. Say for daily or weekly or quarterly or monthly or annually, we can generate report. At the same time, we can generate report, consolidated report in any period, total number of how many monitorings we have performed. And once these reports is generated, then we send for further approval from OIC as well as head ideas. So this is just a sample report for your information. These reports can be viewed online as well as they can be downloaded in a PDF form, and it can be downloaded as well as it can be seen online. So in conclusion, this AIVMP streamlines the internal contamination monitoring process by digitizing data entry, scheduling and reporting, and Porter's comprehensive functionality allows for precise tracking, improved data analysis and optimized scheduling, thus saving time and resources while ensuring thorough safety oversight for radiation workers across BRC facilities. I would like to acknowledge encouragement and guidance of all my seniors and colleagues who have directly or indirectly worked in this work. Thank you all.
Thank you, Lokpati. Now, we can have one or two questions. Okay. Then once again, I thank Lokpati for completing the presentation in time. Thank you.
Thank you.
Next paper is by Soumitra Panda, a rapid technique for estimation of americium-241 in filter paper using polymer inclusion membrane. Soumitra Panda.
Hello. Hello.
So good afternoon everybody. I am Soumitra Panda, working in IDS RSSD BRC. Okay. So I am thankful to the organizers and my parent organization to give me that opportunity to present my work in this forum. Okay. So today I will discuss in an important area of research involving polymer inclusion membrane, PIM, particularly their role in extraction of actinides. Basically, we have focused in this study americium-241 from filter paper samples. So the title of my topic is a rapid technique for estimation of americium-241 in filter paper using polymer inclusion membrane. It's not moving. So why this analysis is important? So basically monitoring of airborne contamination in radioactive lab is a critical aspect in ensuring safety in this environment and as well as the workers, radiation workers working in that environment. And one key method involves the analyzing alpha emitting radionuclides found in this glass fiber filter paper matrix. These glass fibers filter papers are generally used in particulate air samplers. The analysis not only helps in detect nuclear signature with high sensitivity but also plays a vital role in safeguard verification, and it also ensures the compliance with international safety standards. Furthermore, early detection and monitoring of internal contamination are crucial. They provide a pathway for timely implementation of medical intervention. So given the importance of such monitoring technique, our research basically focuses on improving the extraction method for actinides, specifically americium, from this glass fiber paper filter paper matrix. Let's now take a look at the current practices that is commonly employed for this purpose. In the left hand side, you can see this is the technique based on solid phase extraction chromatography. This technique was developed by Maxwell et al. And what they have done, they have first they acid digested the filter paper, followed by column separation using solid phase extraction chromatography. Then they electro deposited on SS planchet and measurement was carried out using alpha spectrometry. The limitation of this technique is it is a time consuming process. Let's say 1 day is required for this column separation and large volume of acid is required. In the side way, we have also developed a extractive liquid scintillation based technique. Our team has developed this technique in 2022. This is a solvent extraction based technique where we have extracted americium and plutonium from these nasal swab and filter paper samples using 0.2 molar DEFA, and subsequently we have stripped the americium from the aqueous to the aqueous phase using 0.35 molar HNO3, and measurement was carried out using liquid scintillation spectrometry. The limitation of this technique is high volume of volatile organics that is required in this analysis. So given this limitation, it is clear that these techniques are effective, but they comes with significant limitation. Okay, so given this limitation, it is now clear that there is a need for more efficient and effective technique, and environment friendly solution is required. So that brings us to the motivation for adopting polymer inclusion membrane. The main advantage is small ligand inventory. Then it can simultaneously extract and backstrip is also possible. Here you can see in the picture, from the feed phase, the metal ions is extracted in the polymer inclusion membrane and subsequently it is transferred to the receiving phase. Earlier in the solvent extraction method, we have to go through two-step mechanism. First you have to extract, then you have to backstrip. So 2 times of solvent extraction was required. But in this system, simultaneously you can extract and strip the metal ions. Then you can use it as a detector by preparing scintillating PIM, and it is very cost effective because the carrier that is required, that is very less. So it is important to understand what PIM is. So it's a liquid membrane which basically consists of these three things. Polymers, it is the backbone of the PIM, then plasticizer and carrier. Polymer basically provides the mechanical strength to the membrane, and plasticizer basically provides the flexibility as well as ionic mobility, and carrier extracts the analyte from the sample solution. And we have optimized the composition of the PIM in this for this study. This CTA is our polymer, 2-NPO is our plasticizer, and HDHP or DEFA is the carrier here. So what we have done, we have prepared a homogeneous solution and then we pour it into a flat glass slab. Then we let it be there to evaporate the solvent. So after 12 to 16 hours, the solvent was evaporated, and we can see one of our colleagues holds this transparent PIM above the filter paper. So this transparent part is the polymer inclusion membrane. Okay. So with this knowledge, let's look how we tested this membrane in our study. So first of all, we optimized the parameters in acid. After optimizing this parameter, we have taken this to the simulated samples. First, we optimized the acid at which the americium was taken place. Then we have optimized the kinetics so that how much time is required to extract the americium. Then we have optimized the amount of PIM that is required for this study, and as well as this volume, the steering feed solution volume, and ultimately we have optimized the counting parameters in LSA. Then we, from this optimized parameter, we have gone through this simulated kind of sample. What we have done, we have taken blank glass fiber filter paper samples. Then we spiked with americium 241 followed by acid digestion, and we have prepared stock solution. From this stock solution, we have taken 1 gram of aliquot and taken it for further analysis. So this left side procedure is followed, and we have counted it LSA. So here you can see this is the uptake study at different acidity. So first thing I want to say, this HDHP basically forms a dimer. It basically forms hydrogen bonded dimer in this PIM basically, and it extracts americium using cation exchange mechanism. So here you can see one hydrogen is released, and there DEFA is going into there and make the complex. Okay, so as it is a acidic ligand, it basically extracts americium in the pH region. What we have found that at pH 2, we found the maximum recovery 95 plus minus 2. This is the study we have done in acidic medium only. Here this glass fiber filter paper matrix is not involved here. So but at higher nitric acid concentration, means with the increase of acidity, what happened, the extraction efficiency decreases due to the competition between H plus and americium ion. Then we study the kinetics at pH 2 where we got the maximum uptake, and we found that within 15 minutes of time it will get saturated. Okay, so here you can see it basically follows pseudo first order kind of kinetics, and these are the parameters that we have optimized in acid. The PIM weight, that is very less, it is only 10 mg required, and its uptake capacity is very high. It can uptake up to this capacity is 20 mg per gram. 1 gram of PIM can uptake 20 mg of americium, and this EA is very high. So it can go up to megabecquerel level of activity can be extracted using 1 gram of PIM. Then acid concentration is around pH 2. Acidic volume that we have optimized is this 10 ml. Steering time required is 15 minutes, and recovery is 95 plus minus 2%. But experiment with glass fiber filter paper resulted in a reduction in efficiency, that is 63 plus minus 5% we have observed. And we have also tried another carrier, that is TODGA, trioctyl diglycolamide based extractant. Here you can see we have followed the same procedure. Here the uptake increases with the acidity. It reaches maximum at 2 molar acidity, and these are the parameters, but its kinetics is very slow. Means 2 hours is required to recover 80% of the metal ions. Can I get just 1 minute, please? Okay. So experiment with glass fiber filter paper resulted in a reduction in efficiency that is around 35 plus minus 5%. So here you can see this work highlights the potential of PIM to improve the actinide extraction process. Moving forward further optimization could overcome the challenges and expand their applicability. So thank you.
Yeah, we can have one question from the audience.
So you have studied the interference of other alpha emitters?
Yes. Right now we are carrying out this other actinides. Let's say plutonium. In the earlier study, we have the experience with DEFA. Here you can see we have developed the technique in 2022 that is being helpful in this study also. This DEFA we have first extract plutonium americium, then we backstrip because we are using LSC, liquid scintillation spectrometry. The resolution is poor, means you cannot separate plutonium isotopes and americium isotopes. So what we have done, we have selectively backstrip americium from the organic phase using this higher acidity. So similar kind of technique we are using. What we have done in the we are further developing this technique. So what we have done, we have a feed solution of plutonium americium. We extract PIM. The PIM contains, in the PIM there is they picked plutonium as well as americium, and on the receiving phase what we have done, we have taken the higher molarity of acidity. So what happened, PIM releases americium to the this receiving phase, and plutonium remains only in the PIM. So you can directly count it PIM in the this using LSA, and the receiving phase subsequently counted in LSA.
That
so
means the kinetics is different, or?
Yes, kinetics is different, yes.
And but normal air samples,
yes,
normally you find uranium because of the natural.
Yes. But the specific activity wise, it is less significant compared to this plutonium and americium. Its activity of plutonium and americium is very high compared to this uranium. Uranium also can be extracted using DEFA, but we are developing this PIM. Okay, it is the part of my PhD study, so that's why we are just
because amount wise uranium will be more gram wise.
Sir, I think probably you can discuss it during lunchtime.
Yes.
So thank you, Soumitra.
Thank you for your patience.
Now the next presentation is by Sailesh Joshi on ammonium oxalate monohydrate as EPR based chemical dosimeter. Yeah.
Hello. This first slides. Next. Hello. Good afternoon to all respected delegates of IARPNC 2025. I am Shailesh Joshi. I am working in radiation dosimetry section of Indira Gandhi Center for Atomic Research. And in our section, mainly we are working on dosimeter development, TLOSL and EPR based dosimeters, and retrospective dosimetry. So today I am going to present one of our recent work. It is based on EPR based chemical dosimeters, where we have studies one chemical ammonium oxalate monohydrate. So in my presentation, just I will tell the principle behind these EPR based dosimeters. So when any material or any dosimeter gets exposed to ionizing or any radiation, so radicals generates. So these radicals, if stable enough, so can be detected with the help of EPR. EPR is electron paramagnetic resonance spectrometer. And EPR can detect the radical and can quantify also the radical. So, and the concentration of these radical is proportional to the dose. So if we know the radical and their concentration, we can find out the dose delivered to the dosimetric material. And the main advantages of APR dosimetry, it is non-destructive. So we can do the multiple measurement, repeatable measurement we can take, and it is tissue equivalent. So it has minimum energy dependence, and it has very good signal stability. Signal is stable up to 6 months. And very important thing, it can cover the wide dose range from milligray to 1000 or 100 of kilograys. So the industries which are dealing with low doses or high doses, it is applicable to all industries. And that's why it has application in radiation therapy quality assurance to check out the output of beam quality, food irradiation monitoring to check out whether proper doses are delivered to the food irradiation or not, and the same time sterilization dose verification also. So various EPR based dosimeters are available. Out of them, this alanine is the most studied and very well established dosimetric system is there. So it has very good signal stability, and the same time it is tissue equivalent and very good dose range. And lithium formate is the another dosimeter. It is more sensitive than alanine, and it is also having a very large dose range, but its signal stability is only few weeks. Then sugar is easily available, very cheap. That also can be used as a dosimeter. It is already studied. Then tartrate, two types of tartrates are used: ammonium tartrate at soft tissue equivalent, and potassium tartrate as bone tissue equivalent. So this potassium tartrate is studied for like bone irradiation or bone treatment. It can be used to get the exact doses. So in our study, we have used this ammonium oxalate monohydrate is the tissue equivalent chemical, and upon irradiation it forms two types of radicals. And for detecting these radicals, we have used this EPR spectrometer. This is EPR spectrometer available in our lab. It is Expand EPR spectrometer. Its frequency range is 9.1 to 9.9 gigahertz, and it we can use in room temperature, liquid helium, liquid nitrogen. So variable temperature we can use it. For irradiation, we have used gamma chamber GC 5000 with the dose rate of 0.5 kilogray per hour. And it has the sample chamber where we have kept our samples for irradiation, and the same sample chamber we have find out the dose distribution that I will discuss in the later slides. So this is the EPR spectrum of unirradiated and 100 gray irradiated ammonium oxalate. So it shows these two peaks, and the main intense peak is taken in all these study. So in the case, we are taking mainly the peak to peak height as an intensity. So for EPR measurement and quantitative estimation, it is very important to optimize the parameters. For each sample, we have to optimize the parameter. So for in this, microwave power and modulation amplitude are very important. So microwave power optimization is very important to avoid the saturation of the signal. So in this, we have recorded the EPR spectrum at different microwave power from 0.01 milliwatt to 62 milliwatt. And we can see in the second figure, this as microwave power increases, signal intensity increases up to 1.98 milliwatt. That can be seen in the third figure also, that is intensity versus square root of microwave power. And after 1.98 megawatt, it decreases, and at higher power, the signal shifts. So the optimum microwave power is 1.98 milliwatt. Same thing, modulation amplitude is very important to avoid the distortion of the signal. With this is the modulation amplitude intensity EPR signal spectrum at various modulation amplitude. Here also we can see with increasing the modulation amplitude, it increases, but after 4 Gauss. That in 5 Gauss, the upper part signal clipping occurs. So for this, the optimum value is 4 Gauss. So these are the optimum. Other parameters also we have optimized. So these are the optimized parameters for ammonium oxalate. For dosimetric studies, we have established dose response curve from 10 gray to 1000 gray. So in this, we have exposed for each dose 3 samples, and we have reported the average value here. So it has the linear dose response from 10 gray to 1000 gray. And to know the signal stability, we have irradiated the sample and we have recorded the EPR just after irradiation and after the storage of 30 days. So here we can see this is the intensity versus storage time. So initially 10 days the signal is stable, but after that slight decrease is there to overall 7 to 8% fading we have observed in 1 month. So we have a gamma chamber in our group. So to know the exact dose delivered to the sample inside, we should know that what is the dose distribution. So for that we have placed, this is the irradiation volume 5000 ml and sample dimension is diameter is 17.2 centimeter, 20 centimeter height. So we have placed our dosimeter axially and radially at different locations. And we have irradiated the samples for up to 500 gray. And this is the first table shows the doses at various position, and next is the percentage variation from the central dose. So here we can see the axially and radially there is a variation from -20 to +20%. So to know and to compare with the standard dosimeter, what next we have done the same ammonium oxalate we have kept with alanine in the same position, and again we have irradiated to 500 gray, and this is the dose estimated using alanine and ammonium oxalate. So in both the cases we have find out this percentage variation in the dose estimated by alanine and ammonium oxalate is within ±5%. So it is comparable to alanine for this experiment. So finally, in our studies we have optimized the EPR parameter and established the dose response from 10 gray to 1000 gray, and find out the distribution inside the gamma chamber and compared with alanine, and it is comparable. Now we have, because we have done from 10 to 1000 gray, so now we are doing low doses also and high doses more than 1000 gray also we are doing this work. Thank you.
Thank you. Yeah, thank you. We can have only one question. There are no questions. We once again thank
you, sir.
Yeah, Mr. Shailesh.
Thank you, sir.
Next presentation is by Mr. Gopal P. Verma. His topic of presentation is investigation of ambient gamma radiation dose rates and radon activity concentration in the model house constructed using uranium mill tailings. Request to limit to given time of 10 minutes.
Good afternoon, everyone. I am Gopal Verma, working in RPS and HPD. Today I am going to present investigation of ambient gamma dose rate and radon concentration inside a model house constructed using uranium mill tailings. Uranium mill tailings is a byproduct, or ratherly which is called waste, while processing the mines, uranium mines. 99% of the mines product is going as a waste, which we are keeping in a tailing pond nowadays. 150 to 200 hectares of the land is being utilized to keep this uranium mill tailings. Every year 13 lakh tons uranium mill tailings are being generated. So if we are doing continuously this mining operation, this will become liability to accommodate those in that many, because nowadays many population has come near to the mining site. So we are not getting enough land to keep this mining byproduct, which is uranium mill tailings. So we have initiated, because this uranium mill tailings is very good candidate for infrastructure material, because most of the materials it is matching with the fly ash and other sand materials. So we have initiated to utilize as a for construction material. For this, we have collected the tailings and radioactivity and chemical analysis is investigated, and these are the tailing forms which the radioactivity is not very high. It can be used, and so we have converted this. Now, this is the first we have do manually. We have taken this mill tailings from the mill tailing site and mixed with the other binding material and fabricated. This is the first model bricks. After doing the physico-chemical testing, these bricks we have utilized in a construction of a model house. This model house is constructed in Jadugora, a complex of HPU unit, where studies are being done how much radon in fully closed to open condition is being generated. Because the radon is the only, because this is mixed with the radioactivity concentration in this mill tailings, maximum radium-226 is there. So due to this radium-226, radon emanation is there, which is causing when we are going to utilize these mills. So we have to justify this, the radon levels are not much. So we have done round the clock measurement of this radon concentration in the fully closed condition, or we are getting this maximum 700 becquerel is getting when it is fully closed, no ventilation is there. In ideally, we are not keeping any people in fully closed condition. So in the open condition, we are getting maximum 320 becquerel per meter cube with 30% tailing pond we are utilizing for making a brick. If we are utilizing 10% uranium mill tailing for a brick and other binding material, we are getting maximum 250 in a closed confined unventilated condition. If we are doing the proper ventilation, it is rather going less than 100 also. And indoors, so 250 and this model house what you are seeing here, this is readily available and is inaugurated in the August for radon calibration laboratory, and all the other radon studies are being done here. So finally, here we are seeing that radon concentration is not much due to utilization, and the ambient gamma dose rate is also merely above the ambient background of the place where it is situated. This is the alpha guard which we have used to measure the radon concentration inside the lab. Thank you.
I have two questions. What is the purpose? One question.
Purpose is to utilize this uranium mill tailings.
Why there is a shortage of soil in the world? What is the reason?
Shortage of sand is also there in the place to place in this region where we are situated with this uranium mining in Simbhum region. There was some shortage of sand also, and the main
building the house
is shortage of the land, available land. In future, we are not going to get any land to make such tailing of pond, because it's still 150 to 200 hectares lands of being utilized to keep this uranium mill tailings.
So I know you should utilize it. Specifically, why house? This is the doubt I had. You could have utilized it in agriculture and many other ways.
This is the one of the purpose. There are so many other purpose, making paver blocks and concrete roads. So this is one of the, we are doing one simulation we are also doing with utilization as a concrete road. For that we are making, very soon we are making one model road containing this uranium mill tailing. For that
That's fine, I understand. Now I have another technical question. Have you measured radium-226?
Radium-226 I measured.
But what is the correction between radium? Because you were saying radon is not much. Not much is not the way, no? There is a number.
Radon is high, but when ventilation is not much. And
have you correlated with radium? That's what I'm asking. Not with uranium, with radium-226.
This is the Jadugora mill tailing. I measured this uranium mill tailing, which is maximum we are getting 2,840 becquerel per kg concentration. This is the maximum.
That is uranium.
No, radium-226.
So that is 100 times more than the soil radium, correct?
Yeah, because it is coming from the mines. What we are
so I know.
containing uranium.
So you must investigate why your radon is not 100 times more. So that's what I'm saying.
Because radon diffusion will be highly probability tested. Because if moisture will be high, the radon emanation will be low. That is why we have done seasonal variation also. During the monsoon region, we are getting lesser emanation of radon. But as the dry seasons, in winter season, we are getting high radon emanation.
Have you measured the emanation coefficient?
Emanation coefficient I have not measured.
So you have to go through that step, quantify, to be able to model and interpret your radon.
Okay.
Thank you, Gopal. So finally, with this, we are coming to the end of technical presentation. And at the end now, finally, we have a presentation by Nucleonics Instrumentation Private Limited.
Is it moving? Good afternoon and greetings from Nucleonics Systems, Hyderabad. I'm the founder director of this company. Before I started this company, I was with ECL for about eight years. Left at the age of 35 and then started this company. This is our infrastructure. It's built up area of about 16,000 square feet. Some of the important points about our company, it was founded in the year 1990. Production facilities spread over 16,000 square feet, leading company in India in private sector. As to its credit, several first-time manufactured products in India, including few import substitutes. In-house R&D facility enabled accredited calibration labs. Recipient of Dr. Juneja Award for Creativity and Innovation in MSME for the year 2014. INS Industrial Excellence Award for 2014 again from Indian Nuclear Society. And J.N. Reddy received Lifetime Award from Luminous Society of India in 2017. And Certificate of Merit in Excellence Innovation from ELSINA 2017. This is a core management team who are responsible for the development of the products. Some of the achievements. First, microcontroller based nuclear counting system was with embedded code for calculations was those days, it was about 2.5 decades back. Those days people were counting and then calculating using calculators, the activity levels, etc. So we were the first to have developed and supplied to BRC. Developed the NIM standard instrumentation as per AEC specifications. Dual scintillator based radiation counting system with optimal design and optimal excellent performance. Overface scanning system was developed and supplied to UCL. And gasless low background beta counting system, an excellent replacement for gas flow type of low background beta counting system, which was developed was used by BRC way back. Developed and supplied good number of TL research readers and TL OSL research readers in DAE, universities and cancer hospitals for research. Neutron survey meter and neutron area monitor is another product which we developed. Stack monitoring system for medical cyclotron facility was another important product. Supplied large number of instruments for teaching and research labs in IITs, NITs, ISCRs, NICER, etc., central universities, supplied complete package of instruments for medical physics course in universities, and package of instruments for 12 to 14 medical cyclotron facilities in India. Our contributions in different application segments include nuclear education and research and nuclear fuel cycle, healthcare, defense and homeland security, industry. See, these are the counting system, basic counting system for nuclear education: GM counter, gamma spectrometer, low cost version, modular gamma spectrometer. This is a MCA based on BRC technology, 1K/4K MCA. Both hardware and software we took from BRC, this technology. And this is TL research reader and TL OSL research. More than 50 units have been supplied throughout the country. We have exported about half a dozen of them to different countries. And over the past two decades plus, we have 400 PhDs and MPhils have been awarded using our system. And this is the only first company which has made available this for research in India. So this is a typical nuclear fuel cycle. If you see, right from exploration, mining to enrichment, fuel fabrication, nuclear power plants, reprocessing, and waste immobilization. So covering the entire nuclear fuel cycle, we have the product range developed and supplied to various establishments in the country. So I supplied instrumentation to almost all DA units, which include nuclear fuel cycle and the research labs. Way back, I think more than 2 decades back, when they asked, UCL people asked us only detect a sensitive GM detector. So I just told them that we'll give a complete solution, and personally I went through vertical shaft down and then horizontally in the Jadugoda mines. To my surprise, I found 3 persons operating the system. One was holding GM counter, another battery, and another probe. So they were taking the readings and calculating the percentage over grade. So then immediately within 3 months, we developed a compact system like this, which could be operated by a single person, and then supplied this to which helped them, largely simplified their life. It was directly going in percentage over grade. And coming to nuclear fuel fabrication area, NFC, we have supplied number of products, but this is more specialized product. Uranium enrichment analyzer, at 3 zones in the fabricated rod, they measure the enrichment calculations that they do. So this project we developed for them. So there are, for any nuclear facility or radiological facility, air monitors, area monitoring, environment monitoring, and personal monitoring. These are the 4 things that are required. So which comprise of all various instruments: whole body portal monitors, beta gamma and foot monitors, counting systems for alpha, beta, gamma, and dual scintillator based, handheld portables for alpha, beta, and neutron radiation measurements, area gamma monitors in different ranges, type tested qualified, seismic qualified ones, continuous air monitors for alpha, beta, and dual scintillator based, small article monitors, TL badge readers, TL OSL, and then multi-channel analyzers, etc. are the products which we supplied over the years to various facilities. If you look at these, these are the various counting systems. You are able to see the middle one, the low background beta counting system, a gasless system. About 40 of them have been replaced with the gas flow type of systems throughout the country, and all ESLs, BRC, IJCAR, and all NPCL units, health physics units, they have purchased this. These are all area monitors. To the right, you will see type tested seismic qualified ones, which are supplied to some of the radiochemical plants and waste immobilization plants. Left, you will see area monitors, next generation version with TFT displays. So there are small article monitor, whole body portals, and foot monitors, etc. So automatic badge reader, semi-auto. These are the instruments which we have developed for Indian Navy: portable radiation monitors, area monitor, and the ship install radioactive system, single card badge reader. So to the left, you will see 3 of them. These are all type tested, conforming to JSS Penta 5. To the right most, you see the single card badge reader. That's the replacement for Russian version of badge reader for nuclear submarine that was supplied by us. Ship installed radioactive system is the only, we are, apart from ECL, we are the only company to have qualified to supply this product. And we have done, as a developing vendor, a number of projects we have done with for DLJ. So RadMac with the external probe, with built-in probe, ACU. This is for a battle tank T90. And then RadMac A for helicopter version. And the bottom grasp dome-based radiation sensor was also developed one. And we have also integrated with the chemical sensor. Nuclear and chemical sensor integration was done by us. And to the right is a portable radiation dose rate meter, which is under development for neutron and high gamma, low gamma, and neutron dose measurements. Instrumentation for strategic facility, which is coming up at Vizag. Portal monitors, gamma spectrometer system, noble gas monitor, gate monitors, environmental monitors. So these are the ones which are going to for that facility. Environmental radiation monitors, noble gas monitors, gate monitors. This is a gamma spectroscopy system. And health physics instrumentation, we have a lot of products complete. Most of the cancer hospitals, they have been buying from us. So this is a neutron survey meter. For the first time, we have developed that. For the past 3-4 years, we have been supplying this. And these are all again area monitors for that facility. Stack monitoring system is a good replacement for the impulse substitute. It comprises of 3 units: airflow meter, stack monitoring system with scintillation detector and GM detector. These 3 comprise the stack monitoring system. Hand-foot monitor, TL research reader. This is isotope, isotope purity test and identification. That is what is used in the medical cyclotron facilities. This is a typical medical cyclotron in Apollo Cancer Hospital. Process lines. These are the display units. This is a exhaust stack duct area where we installed our detectors. So in all, about 13 to 14 medical cyclotron facilities, we have supplied the instrumentation. For steel industry, which was for steel industry, which were there, all recycled steel industry, which were facing export rejections, way back, a couple of decades back. We were the first to have developed this package of instruments for them. Radcheck meter is one. It sniffs. It's basically micro survey meter. When it touches the component, it attenuates the natural background. If the attenuation is more by 15%, we say component is clean. So with external probe and internal probe. And there's a truck monitoring system, in the container carrying the metal scrap and all that. So we have, in all, we have supplied to about 8 to 10 systems. At seaports, we have supplied to Adani ports. It scans and leaves a signature from which no one can say that there's a contamination or not. Both gamma and neutron scanning is done for this. And for RS and laser for steel samples, special steel alloys, some of the companies are exporting their products. So by using MCA method, we supplied this system. So one can analyze and then find now what is the contamination in that. Right side, the food sample and laser using the same MCA. For some of the exporting industries, we have supplied this. This is again for water sample analysis. No, I'll just take a minute.
Sir, please kindly conclude
just half a minute. So this is for low background beta counting system. This for water sample analysis. As per IS standard, we are the only company offering this system, and quite a few analytical labs have purchased this. So enable accredited calibration lab facilities we have, and some prestigious awards. Thank you for your attention.
Thank you, sir. I think they can have more interaction during the lunch hour or maybe at the stall.
Hello.
So, thank you.
Thank you, speakers. I request Professor Y.S. Maya, Professor, Department of Chemical Engineering, IIT Bombay, former head RPAD, BARC, to present memento to Dr. Oza and Sri S.M. Pradhan, the chair and co-chair of this session. Thank you, sir. There is an announcement. All are requested to kindly attend tomorrow's morning session at 9:30 a.m. about young generation, India, Japan, Austria, Kenya, to share their views on radiation protection and challenges. Your presence will encourage us. And there is one more announcement. The IARP lifetime membership receipt and lifetime membership certificate is now available at the help desk. Those who have filled the lifetime membership form can collect the receipt and the certificate. It's now time for lunch. Please enjoy the meal and take some time to explore trade exhibitions and poster displays. We will resume at 2:30 p.m. for our next session. I repeat, we will resume at 2:30 p.m. for
joined BARC in 1994 after successful completion of 37th batch of BARC training school in computer science discipline. He has carried out design and development of various radiation monitoring systems like aerial gamma spectroscopy system, quad rotor based aerial radiation monitoring system, and decision support tools for nuclear and radiological emergencies. He has carried out planning and execution of several aerial radiation monitoring exercises jointly with defense forces. He has contributed significantly towards the development of 25 DAE radiation emergency response centers across the country. He was instrumental in implementation of quality management system for the Radiation Standards Laboratory of BARC, which is in designated institute for ionizing radiation metrology in the country. As a head of Radiation Safety System Division of BARC from 2020 to 2024, he has contributed towards the activities pertaining to preparedness and response to radiological emergencies, radiation standards, radiological impact assessment, and internal dosimetry. Currently, he is heading Health Physics Division of BARC and is carrying out development of measures to control radiological hazards in nuclear and radiological facilities. The co-chair of the session, Dr. Shashank S. Saindane, is working in Radiation Safety System Divisions of BARC Mumbai since 1992. He is actively involved in the department's program on national level preparedness for response to nuclear and radiological emergencies. He is a nodal coordinator for 25 DAE radiation emergency response centers with trained radiation emergency response teams, equipped with the state-of-art monitoring systems and methodology for radiological impact assessment. His experience and expertise are used in training activities on preparedness for response to nuclear and radiological emergency for the first responders. He is associated with the development and setting up network of gamma monitors-based radiation early warning system. Under his guidance, the developed mobile methodology is used for environmental radiation background surveys carried out for major cities emergency planning zone of nuclear power plant. I welcome the chair and co-chair of this session. We are handing over the session to you, sir.
Thank you for the introduction, and my co-chair, Dr. Shashank. And we'd like to start the session. This is session 6 of the conference. This session is on nuclear instrumentation and system development. The first invited talk is by Dr. Rajan, who is a director, First Reactor Fuel Processing, IGCAR. And his presentation will be on radiation monitoring systems for safe operation of first reactor reprocessing plants. Before I invite him for the invited talk, I'd like to introduce Sri K. Rajan, who is an outstanding scientist, and he is a director, reprocessing group, Indira Gandhi Center for Advanced Research. Sri Rajan he joined IGCAR Kalpakkam in the year 1987. He had completed BTech in Chemical Engineering from Anna University with distinction and MTech in Chemical Engineering from IIT Madras. After completion of training in Mumbai, he joined the reprocessing group of IGCAR and initially involved in the commissioning and operation of the J-Rod facility for reprocessing of thorium fuel assemblies for the recovery of U-233. The recovered material has been successfully fabricated into fuel and deployed at Kamini reactor, which is the only unique reactor in the world which runs with 233 fuel. Later, he was involved in the equipment development at Coral, a pilot facility for reprocessing of spent mixed carbide, 70% PUC and 30% uranium carbide fuel from FBTR, where he had designed and developed the remote sampling system, which is successfully operating in Coral and DFRP. Subsequently, he was involved in the design, construction, and commissioning activities of DFRP. He played a key role in obtaining the regulatory clearance for DFRP after submission of more than 300 documents. DFRP was dedicated to the nation on 2nd January 2024 by Honorable Prime Minister Sri Narendra Modi, and currently DFRP is operating at its design capacity. Presently, K. Rajan is responsible for the operations of both the reprocessing plants, Coral and DFRP, at reprocessing group of IGCAR. May I invite Dr. Rajan for delivering the invited talk. You will have 25 minutes for the presentation. Thank you.
Hello. Can I move on? Okay. Yeah. No, it's okay. Okay. Yeah. Good afternoon to everybody. I'm really privileged and honored to give a talk here on my experiences in reprocessing field for the last 35 years. And I'm really thankful to the organizers. They had a very wonderful arrangement for this seminar, and really thanks to them. And moreover, being a post-lunch session, I know all of you are already overexposed with a lot of radiation lectures. My thing will be slightly deviated towards that. It is basically reprocessing and then how we are managing radiation protection in reprocessing fields. Thank you. Let me go and see. Essentially, all of you know that reprocessing is really, you are supposed to recover spent valuable materials like uranium and plutonium from the spent fuel from reactors. We have a lot of reprocessing plants in India, and most of them are, all of them are mostly for thermal plants actually. And what we are having is reprocessing of fast reactor fuels. And let me just go through the. So essentially, for fast reactor fuel reprocessing, the issues are different. Which I will explain to you later. But any technology is generally, if you see, even in radiation also, if you see that in reactors that radiation is contained in a solid form. I mean, it is, you have to attack only when there is a problem in solid. But here, it is in solid, liquid and gas. In all the three forms it is there, and we have to control in all the forms. And similarly, even in technology-wise also, reactor-wise, you see all the documents, everything is mostly available. You can always get the informations. But in the case of reprocessing plants, it's very difficult. Being the strategic in nature, we are not able to get any informations. Everything, especially fast reactor fuel reprocessing, we have to start from the scratch. See, the first one, the agenda, that is why the first one, phase one, when we have developed, that is, it was in IGCR, it was in the reprocessing development laboratory, and then that was the phase one was our supposed to develop process and equipment. After completing that, this process and equipment, whatever we develop, we have to do by pilot plant level testing. That pilot plant is nothing but coral. It has got the capacity of 12 kg of heavy metals, that is uranium and plutonium, we have to pre-process per year actually. After successful doing that, we have gone to the next level, that is this EBDR, essentially fast breeder test reactor. It has got first one phase 2, that is phase 2, that is pilot plant level, it is go to coral. And then for the, with respect to phase 3, it has to go to DFRP actually. DFRP is the EBDR requires nearly 100 kg per annum. That complete capacity of the EBDR can be reprocessed in DFRP. And then after that, we got a PFBR fuels. That PFBR fuel essentially, initially it will be demonstrated in DFRP for 500 kg per annum. EBDR is a test reactor and PFBR is a prototype, it is a commercial reactor almost. It's a prototype and then followed by regular FBRs actually. From here, then the fourth phase, that it is regular operation of this PFBR fuels, it will be done by FRFC, which is under construction now. See here, you can see here, this is 12 kg per annum. That DFRP for EBDR, it can cater 100 kg. In fact, DFRP can, we are dealing with carbide fuels, oxide fuels, and carbide also, it contains various percentages, 70% plutonium, and then Mark II has got 42% plutonium, and then PFBR has got something like 21% inner core and 27% plutonium outer core actually. All types of fuels can be reprocessed in DFRP and this plant, and as of now, phase 1, phase 2, phase 3, all the activities are completed and we are giving for the, see this is done by NRB, so we are giving the design, complete design and also some of the important first of its kind equipments we are fabricating giving for FRP of FRFCF. This is the status of reprocessing program. I'll just go through next. See, what is the difference? See, thermal reactor fuel, fast reactor fuel. Actually, we have from almost 50 years over PP has started and we have reprocessed sufficient Cyrus fuels. Almost 50 years we got experience. That is a research reactor. Of course, Periphery has started later with for the power reactor fuels. Then these thermal reactor fuels, like which you can reprocess like fuel from Kaiga, they are all very low burn up. Actually, you can see 6,700 megawatt day per ton, and it has got long cooled. Each fuel will have minimum more than 5 years cooled period, and then they will have a low specific. Because of this, the activity is 300 curies maximum. Then there is no plutonium inventory in the fuel. The plutonium, whatever formed in the fuel only is there, and that is 0.3%. Because of that, the advantage of this, any problem, they can very well go inside the cell and they can do the maintenance, contact maintenance. And there is no need of static containment, it's only dynamic containment is adequate here. Whereas, you please see here, the fast reactor fuel, it has got a very high burn up, 1 lakh megawatt day per ton, and short cooled one, because we have the fuel itself, some plutonium. What? The fuel itself plutonium, so it is 70%, 40. So these cannot be we cannot wait for quite a long time in cooling period actually. Otherwise inventory will be lost. So for that the cool is less than 1 year only. Because of that, you see the activity levels. It is almost 10,000, but in fact, actually, the plant has been designed for 12,000 curies per kg. These are all the different types of fuel which I have told we are handling in DFRP. Again, the problem is, since it is a there is absolutely no possibility of contact maintenance. Everything has to be done by remote maintenance. So all the equipments has to be designed in in such a way that if it fails, either you can do maintenance by remotely, or you have to leave it and you have to have other equipment to start with that. And then this is another very important, static containment is required. So the leak tight cells, we have to, wherever open solution handling is there, see, all aware that glow boxes, we are handling plutonium, where the leak tightness is almost 0.1 volume % per hour. Where here, we are handling cells of 100 meter cubes to 700 meter cube, we have to do the leak tightness up to 0.1 volume % per hour. This is the basic requirement of handling static containment actually. So, this shows how much the work involved in the fast reactor fuel. See, actually the nature of the fuel is slender fuel pins. Because of that, we cannot go for bundle chopping, which is done in thermal fueling. It has to go for a single pin chopping, otherwise crimping will be there, which will essentially lead to the poor dissolution. Then the fuel is pyrophoric. Pyrophoric means when we chop the fuel, it will catch fire. So we have to use inert cover organ purging during the chopping. Then again, when the fuels dissolve, that it gets soluble organics actually. That some of the things which will take plutonium and it will not give back. So this all has to be killed before going for extraction. And dissolution, it is again very high plutonium is there, and also level normal acid, corrosion, heavy corrosion. So we cannot use SS304, so we have to go for a special equipment titanium, and then the dissolver only is a titanium material. The different other parts of the plant is different material, that is SS. So titanium SS welding has to be developed by ourselves. So third phase formation, it is again during extraction, because of the high plutonium content, the organic will get into two split spaces, and the one which is lean organic and other which another high organic phase. In that, what will happen is it will be high organic plutonium will get accumulated and we cannot separate it. And then this is a major problem. All of you are aware criticality most, because see, maximum limit for with respect to concentration, 6 GPL at the most we can go plutonium handling. But what we are handling is 35 GPL, 40 GPL. So we have to take the plant without criticality incident to occur. And then very big amount of alpha, so alpha containment is required, for which requires that, whatever leak tightness which I have already told. And then there is a big problem is solvent. The solvent, there is a wonderful solvent developed by, in fact it was developed by USA at that time, and it is still we are using that. There are so many solvents, so research people are doing it, but still 30% TBP we are doing it, because the advantage of the TBP is it takes uranium and plutonium, and when you reverse the acidic thing, then it will immediately give back. But unfortunately, this tributyl phosphate with high level of radiation, what it happens is it becomes dibutyl phosphate, monobutyl phosphate, and phosphoric acid. Because of that problem, what happens? Those secondary products that they will take the plutonium and they will not give back actually. So that is a major problem. So we cannot use that pulse columns, a big efficient things which are used in the thermal fuels actually. Here we developed our in-house centrifugal extractors, and this with a very short residence time. It is having only maximum 1 minute in 20 columns actually. So that before that everything gets separated and comes out. Such a short residence time we have to operate it. So these are all the, see, why I am telling is so much of difficulties, so much process, equipment, everything. But in spite of all these things, let me come to the next. We have, in DFRP, we have achieved 99.9% recovery with a very good separation factor, and also we have, with both lean solvent and raffinate waste, which contains very less than 4 ppm. That is a very, in spite of so much restriction, that achievement is possible not by any individual. Not only IGCAR, so many groups in BRC, so many groups in IGCR worked together, and we could make this success. actually. See, with respect to coral, as I have already told, pilot plant, 20 years of successful operation. This compact fuel, coral is nothing but compact reprocessing of advanced fuels in lead cells. This has been commissioned in 2003, and 66 campaigns we have did that, and with fuel with burn up of 155 gigawatt day per ton has been processed with very good recovery and decontamination factors, and this reprocessed plutonium was refabricated into the fuel, and it is generating power in FBTR. Successful closure of FBTR fuel is demonstrated. The process and equipment developed for fast reactor fuel have been validated and established in coral. Mandarum expenditure, initially it was very high, now it is only 15% of what is the initial thing, Mandarum expenditure, we have for each campaign actually. Then the plant had completed the design. See, originally this plan mandate was to complete only 42 campaigns, that is 14 sub-assemblies of FBTR, but now we are running 67th campaign. This plant is relicensed by ARB up to 2028 and continues normal operations. With respect to DFRP, as I already told, this was it has gone into various stages of commissioning. Each stage, water and acid TBP and natural uranium. Each stage we gone to AERB and we got the clearances, and then only we have gone for commissioning. These plants were dedicated to the nation by our Honorable Prime Minister on 2nd January 2024, and on 25th April it has got hot commission, and then 2 campaigns with 155 gigawatt day per ton. In fact, see, coral has got 1 campaign maximum 20 pins. Here 1 sub-assembly we are going to reprocessing, and the 3rd campaign with complete 1 sub-assembly 60 pins in a single batch we have completed, and we have recovered all the plutonium, and as I have already told, we have recovered almost 99.9% of the material. This is with respect to the plant status. Now let say, just I wanted to briefly say, any spent fuel after coming, because all of you know that it is sodium is the coolant, so sodium in fast reactors, so we have to clean the sodium, and then sub-assembly has to be dismantled by top and bottom has to be dismantled, and then take the pin and wrapper cutting has to be done. The pins will be taken out and put it in a magazine and go to the chopper, and chopper it will cut into 20 pieces of that. Each length has got something like 561 mm pin has been cut 25 mm pieces, and then it goes for dissolution in a dissolver. Then this is the here also in thermal plants they use back filters actually, but here we are using if there is because after dissolution some undissolved particle will be there, some platinum materials will be there which will choke if you are not removing that, it will choke the entire plant. So feed clarification, we have gone for high speed centrifuge 20,000 RPM with we are able to arrest vibrations, and then finally we are able to now it is, we are able to successfully utilize in DFRP. After feed clarification, it goes for extraction cycles. One is co-extraction initially, then partitioning. Of course, solvent cleanup is there, evaporations are there, and then finally it comes to uranium product and plutonium product. This is the general stuff. Now let's go to the topic. Actually, this whatever I have told is still now is with respect to reprocessing plant. Now, how will with respect to this seminar, how we are handling radioactivity. See, as I have told that it is a facility for separation of the valuable materials. Second one is, see, the spent fuel is a source of both ionizing and non-ionizing, alpha, beta, gamma, and here neutron. Ensuring radiological safety in addition to chemical and industrial safety is important. To ensure radiological safety, radiation monitoring is needed. Okay, this and all of you know. Actually, just I put for some people, if anybody new to radioactivity, we all know that area heavy unstable will go to alpha, beta, gamma, and proton, neutron by spontaneous decay. And then that's what written in the unstable heavy nucleus attaining stable by means of emitting the form of radiation. See, the problem yesterday everybody was telling that when people are not recognized, when just like that they say radiation is dangerous and all. That is mainly because of this reason. The human body cannot feel the presence of radiation, unlikely heat, light and sound. So anything which is, seeing is believing. If there is no, if they are not able to see, there is always a question rises and we have to answer to them. monitoring of radiation is mandatory by appropriate radiation monitors. The radiation monitors are essential for the safety personnel in terms of dose rate contamination activity, helps to protect the personnel from undue exposure by enable the visual audio alarms in case of radiation level greater than the present value reported. Okay. Okay, all these and all generally alpha particles and how they are interaction, alpha, beta, gamma, it is this. And then see deductions. Any detector should have these features. Prompt detection, the signal output would be high strength, and then it should have sensitivity, resolution, accuracy, is to be easy to use and rugged, cost effective and simple electron. As far as the electronics is concerned, counting electron, it should have able to amplify a weak signal, because then only we can able to find even a small radiation also. I mean a better signal by noise ratio, display visual audio alarm, easy testing and calibration, data to transfer to control room. All these things are features of detectors in electronics. And also you all know that detection is by three methods: ionization, excitation and semiconductor tube. Excitation by scintillation detectors, photomultiplier tubes are there, ionization capsule chambers are there, semiconductor detectors are there. These are all the methods. And ionization here, gas is filled here as per the interaction of the radiation. Ionization, the current will be converted to voltage pulse and used for reduction. And in the case of scintillation, we got production of, as per the radiation level, light photons are emitted, and based on that we are able to determine the, in turn determine the radiation. And this is, there are three different inorganic scintillation detectors: zinc sulfide, sodium iodide, cesium iodide, lithium iodide used. Organic scintillation detectors, it includes stilbene, naphthalene and anthracene. Plastics, these are made by mixing scintillation chemicals with plastic. Actually we are using this only, dual phosphor scintillation detector, which detects both alpha and beta, both monitored in a single measurement, zinc sulfide AG coated with 0.25 mm thick plastic scintillators. Okay. And then semiconductor detectors are, there is NP region is there, as the depletion region is more, depletion layer is more, and per electron pole pair will become induced in the depletion layer and upon interaction of the radiation, and they are used for reduction actually. Actually, now these are all the monitors and the principle just I told, and now let's go to the plant actually. Radiation and zoning. Here we got a supervised area, that is white area where there is no nil contamination, and there is another green zone, normally free from contamination, but has potential to get contaminated. And amber zone, it is adjacent to that, that is where red zone is actually where the radioactive materials are stored, and adjacent to the red zone, mostly it is operating areas, because from here only people will be operating the inside the cells, and that is called amber zones. And here it has got the highest potential for contamination. So green, amber, red, white, these are all the four zones. And as here I mentioned here that white area is what are all the external, different radiation levels, radiation monitoring requirements, procedures for all these things are there. In the case of white area, nothing is there. Whereas in the green area, it should be, the radiation level should be less than normally 0.1 MR, maximum allowable 0.25. And then you have to enter by personal, there are personal exit monitors, hand clothing, all these survey monitors are there. Through change room only, plant crew, you can inside. Mostly change rooms are all called green area because they got least potential for contamination. Then amber area, as I already told, it is in the operating area. It is, normally it should be less than 0.1 hour per hour, but okay, we can maximum go to 1 MR per hour. Then here while going is individual monitoring, camps, periodic individual routine monitoring, area survey is there, plant clothing, restricted entry without respiratory PPE is normal. Normally, red area is where radioactive materials are entered. Actually, this may be written, but in the case of fast reactor fuel reprocessing plant, absolute there is no chance of entering inside actually. And then these are all the contamination levels. White area, all the areas it is air activity, external radiation nil, and green area it is less than 0.1 derived working level, whereas this is less than 2.5. That's what whatever I already do. Air activity is less than 0.1 DAC, whereas here it is less than 1 DAC. Actually. So radiation detectors. What are all the radiation detectors we used? Personal radiation monitors are alpha hand monitors, beta hand monitors, dual phosphate hand monitors, then personal contamination monitors. Area radiation monitors, all area gamma monitors and wide range gamma monitors, then continuous air monitors. Radiation survey monitors are area survey monitors, alpha survey monitor, gamma survey monitors, neutron and tele-detectors. This criticality alarm systems. Stack effluent monitoring system, alpha, beta, krypton and iodine we have to monitor. Radiometric nuclear counting system, alpha counting, beta counting system and ultra spectroscopy and gamma spectroscopy. And nuclear security monitors, special nuclear material accounts, materials we have to monitor that. Then nuclear drum monitors for waste assess monitors. These are all the things which are used for radiation detectors. And then AHCM. AHCM is checking the alpha contamination on both hands and essentially the AHCM is alpha hand contamination monitors. It, as the name itself says, it is hand alpha. It determines this determined by the SS grill, mylar film, zinc sulfide, scintillator, transparent sheet coupled with the PMT. This is the one. But then BHM is the beta hand monitors and checking beta and gamma monitors on both the hands. This is done by SS grill, lead shielding. Clothing probe is contain 1 GM tube detector which is shutter. And now actually we are using this only, that dibutyl hand monitors instead of this one actually. That alpha beta both monitor in a single measurement, and so that you can save the space and you can, instead of 2 equipment, 1 equipment can be used. Detector is this actually, zinc sulfide with Ag. Higher and uniform efficiency for both alpha and beta is more than 25%. Indigenously developed, this is in one thing which is developed in RPG itself. We have developed and we have made both alpha and beta combination in a single monitor actually. Then PCM, personal contaminator monitor. It is actually when you come out, if there is any exposure is there, then immediately it blocks the gate. Personal contamination monitor. And then of course area gamma monitors are there. This is nothing, essentially it ranges from 1 to 100 MR, whereas wide range gamma monitor is 0.1 to 100 MR. This is 0.1 to 100 R wide range gamma monitor. This is typical area gamma monitors located here. And then continuous air monitors are there. That is given by alpha and beta. Alpha for zinc sulfide with silver, and GM tubes are used as filter heads. Okay. Okay. Actually, let me just, I just mentioned only very important. These are all the in-house development. Plutonium in air monitor, waste SSA, management monitor, design of pulse processing circuit, conversion of existing alpha and monitor into alpha beta and monitor, stack monitoring system, silicon-based photomultiplier tube based on alpha, beta, hand, foot and cloth monitoring monitor, silicon-based photomultiplier based on alpha, beta spot contamination for detection within pipe, silicon-based photomultiplier based on alcin, alpha scintillator contamination monitor. These are all things which are mainly in-house developments, and just I will explain plutonium in it. This is one of the very important thing. Can I just 2 minutes?
We would like to complete within 2 minutes. Yeah. Please,
pardon?
Thank you. We would like to complete within 2 minutes.
Yes, okay, sir. 2 minutes. This is very one of the important thing. Isotope identification is this in-house development. Alpha, the air which goes here, no, it contains alpha, beta, gamma. All are getting alpha is differently when one multi-channel analyzer. Beta, gamma this flow will detect set. Remaining alpha, that is plutonium, and beta, both are detected. Essentially, this has been in-house development which we are finding extremely difficult from getting abroad. So we have made in-house development, and in fact it is given to other plants also. Nuclear drum monitors, and then design of pulse processing circuits, then conversion of alpha single monitor, then stack monitoring, especially stack monitoring, that you can see this alpha, beta, dual phosphor, iodine. Except this detector, everything was monitored. This alpha, beta, iodine and krypton. We have got 2 different lines actually. So all the things we are monitoring, whichever is going into stack actually. And then this is alpha, beta, hand, foot, cloth. This is used by silicon photomultiplier, this one. And then of course we got, you can see here that 2 ruby coin. This is just 7 mm, just to compare this. This is a very small arrangement. It was developed by ourselves. So inside a pipe we can put it and see whether any alpha, beta is there. This has been developed by ourselves. And of course, HMI based counting systems are used. And then these are all the all radiation monitors and corresponding radiation detectors. And just I wanted to finish this one, last slide. These are all area gamma monitors, 57 numbers, wide range gamma meters, 3 numbers, continuous air monitors, 25 numbers, criticality alarm system, 7 numbers, alpha, beta, 15 numbers, vessel nuclear meter, 2 numbers, wide body, this one is whole body, portal contamination monitor is 2 numbers, plutonium in air monitor 2 numbers, stack monitors 2 numbers. These are all installed at DFRP as of now. And finally, this was our Prime Minister has dedicated our facility to the nation. And then, thank you.
Thank you, Sri Rajan, for taking us from the journey of processing of 12 kg per year to 100 kg, then 500 kg, and now we are planning for 220 tons, and also covering the radiation detection and electronics. So we can have 1 or 2 questions from the, yes, Dr. Kulkarni, please.
Thank you for this nice presentation. I just wanted to ask you this plutonium in air monitor,
yes,
which you said, whether it is in-house developed?
Yes, sir. That was done by, of course, in-house development in the sense, I am not telling RPG alone, RPG, EIG, and in BRC also, ECIL. We all together, in-house means our indigenous development. It is
whether it is installed at your place?
Yes, sir. It is there in now. We are our RPG things. We are using it at DFRP.
How many of them you have installed?
How many of them?
You have installed at your place.
Sir, how many? 6 numbers, huh? 4 numbers. 4 numbers we have installed, sir.
So you have given to this BRC also? This
BRC, I think they, sir, it was BRC also asking for that. Some, but as of now, we have. I mean, I do not know what. Direct interaction was not that. They were interacting to EIC actually, EIG group. We are from our people. We have deputed some people. They were involved in developing this, and we have whatever developed in ECIL, we have installed in our thing, and it is very satisfactory working.
You have shown that inventory of all the monitoring instruments.
Yes.
Did you optimize their placement in the DFRC facility? How do you select the number of inventory of all the monitoring instruments you showed?
Yeah. Sir, the DFRP is a very big plant, sir. It contains almost very big cells, 7 and so you require all these things as per the regulatory requirement. See, as per AERB, whatever they require, and we have to put it, because of that only this much of equipments were there.
Any other question? Yeah.
Sir, during this 20 years operation, initial stages, you have to, any unusual occurrence and then leading to engineering structure to be modified or shielding to be augmented scenario.
See, any commissioning, it is went like that only. See, we are not directly going for hot commissioning. We are going for first with respect to acid. A lot of problems will be there. Because I can tell you, I have not, within the plan, nearly 1 lakh kilometer piping, and nearly 50,000, 5,000 kilometers piping, and then something like 1 lakh weldings are there. And the problem is so much piping and so much, very small piping, very intense piping, dense piping. And there is every possibility that welders, they do mistakes and all. When you start running the plant, at least some 15 to 20% there will be failure, and we have to rectify that. That's why first we run with water, and then acid, and then everything we have to, each and every stage we have to ensure that everything is safe. And then finally we go for performance studies, like when it goes for like acid and acid TBP means, then we see mass transfer, everything and all. Then actual uranium we are taking, cold run then. There we thoroughly study the equipments, how with respect to performance and all, and then after that only we go for hot commissioning.
During this FBTR top and bottom cutting also, nothing encountered during that time. No?
See, we anticipate, carbide is a pyrophoric in nature, so we anticipate that it will definitely give fire. So that's what we did is, initially there was a slight higher fire. So what we did is we reduced the vacuum now. What happened? See, essentially, if you are sparging argon and spark comes, the argon should quench the fire. But what happened if you give a very high vacuum in the system? This organ without so high velocity, it will go straight into that actually, without quenching. So what happens, your fire level will be high. So we reduce the vacuum in the dissolver, then this problem is solved, but slight sparks are coming. I am not telling it is not there, it is there.
Thank you, sir.
Thank you, audience, for the active participation.
Thanks.
I'd like to thank Rajan. I have yeah.
Thank you, sir. I request Chair of the session, Sri Prabal Chowdhury, to hand over the memento to Dr. Rajan. Thank you, sir. We will now move on to oral presentations. I hand over this session to the chair and co-chair.
Yeah, good afternoon, everybody. I am honored to welcome you to this session where we will explore the cutting-edge technologies and solutions driving the future of nuclear instrumentation and system development. Now, I invite Shri Sagar Baria to present his paper on development of a server-based web application for remote iodine 131 monitoring system.
Okay.
Good afternoon, all of you. Myself, Sagar Baraya. I'm working in Radiation Safety System Division, BRC. Today, I am presenting my work, development of server-based web application for remote iodine 131 monitoring system. Remote iodine 131 monitoring system is a radiation monitoring system with some extra features like data storage, processing, visualization, and remote access of this data over the network. This system has two components, iodine 131 monitor and server-based web application. Iodine 131 monitor is a GM tube-based radiation monitoring device which measures the radiation level and transmit the real-time data to the server. Second component is server-based web application. The main feature of this application is for data storage, visualization, and remote access. The data is stored in a secure database, and for visualization, we have provided a user-friendly graphical user interface. And this is a server-based web application, so you can have one server and data is stored there, and at multiple location you can access this application, and no need to install this application in every PC where you are accessing this. This is the software architecture of this application. The client server based architecture has been implemented here. The iodine 131 monitor and browser, these two are act as a client, and server has a three component: application server, Postgres database, and a front-end application. This application is hosted using Nginx web server. Iodine 131 monitor sends the data to the server using HTTP request, and application server provides various APIs. APIs are application program interface through which you can talk to the server, and this server store the data into the database. Front-end application provides a graphical user interface. It is built as a static files. It's contained HTML, CSS, and JavaScript file, which is hosted using Nginx server, and the client can access this application through the web browser using the URL provided URL. So based on the request from the user, application server fetch the data from the database and return to the browser. Application server, this is a main logic handling unit of this application. It executes the core functionality of the application. It provides the key functions like database communication for data storage and retrieval operation, and it's provide different APIs for example data upload from iodine 131 monitor, and it serves the request of front-end application for data fetching, user authentication, and user account management. It's established the WebSocket connection with the client for a real-time data update. The technology used here are this application is developed using Python language, and Python-based web framework Fast API has been used for API management, and Nginx web server is used to host this application, and for database operation SQL Alchemy, a Python based module, has been used. Data is stored in a database, a relational database management system. Postgres is used to store the data. It is open source and server-based database, which is a more secure database. And data is stored in tables like user information table, radiation level table, alarms data, and system parameters. A front-end application provides the graphical user interface. Key functions are like data presentation and real-time updates. The front-end application presents the data which is fetched from the server based on the user request in chart form, and it also provides the user to download the data. And for real-time updates, the front-end application establishes the persistent connection with the server to provide a real-time updates of the data in the front-end. Front-end application is developed using the Angular TypeScript-based web framework, and Bulma CSS is used to styling the application, and for real-time communication we have used the WebSocket protocol. These are the some features of the application. Here we have given the user authentication using username and password to restrict the unauthorized access of this application. The role-based access control mechanism is also implemented using three logical users like super user, data viewer, and data logger. Super user has a role to manage the user accounts and system parameters, and the data viewer can access the radiation data which is stored in the database, and data logger role is provided to iodine 131 monitor to upload the data to the server. This application provides a real-time remote data visualization and access to historical data to data viewer. It provides the data visualization and downloading provision in the CSV file format. This system also provides alarm generation based on user-specified alarm threshold, and it's provide a provision to generate the alarm reports in PDF formats. This is the home page of the application. As the any user type the URL in browser, this page will be shown. Here first user has to be registered in the system, then only it can access the functionality of the application. This is the new user registration form. User can register by providing a name, username, email, and password. And after the registration, the super user has to approve the his account. After approval from the super user, user can log into the system and access the functionality of the application. This is the real-time data profile, which looks like this is simulated data, and user can see the data, viewer can see the real-time profile of the monitor. Here we have provided the provision to give a list of search of alarm as well as unacknowledged alarm also. User can search the alarms by the period and see the profile, count rate profile during the alarm, and download the data as well as generate the reports of this alarm. This is the sample report of this system. It provides a time period during which the report is generated, number of alarms, and a list of alarm with start time, end time, max count, and alarm threshold. And it also provides the count rate profile during the alarms. This is the historical data. User can access the historical data with providing the time period during which you want to see the report, and download the data in CSV format for further analysis of the data. Thank you.
Thank you, Sagar, completing the presentation within time. Now we can have some 2-3 questions. If there are no questions, I'll just ask one thing.
Sure.
How does this web application handle the real-time transmission and processing of the data?
Sir, we are using a WebSocket based protocol. This is a two-way communication between the client and server. So server provides API for connection. So as the user log into the system, we establish the WebSocket connection with the server. So as the monitor transmit the data to server, so server will send the data to all connected client. So there can be multiple user has login. So all the connection are stored in the server, and it will broadcast the data to all the clients.
Good. Thank you.
Thank you, sir.
Next invited talk is T5011 by Dr. Priyanka J. Reddy. She will be presenting on development of methodologies for simultaneous estimation of strontium-90 and cesium-137 concentration in filter paper samples. I invite Dr. Priyanka Reddy, and you will have 10 minutes for your presentation. Thank you.
Good afternoon, one and all. Myself, Priyanka Reddy. I am working in Tritium Lab of Internal Dosimetry Section, RSSD. The topic of my presentation is development of methodology for simultaneous estimation of strontium-90 and cesium-137 concentration in filter paper samples without radiochemical separation. Cesium-137 and strontium-90 are the main radionuclides that are expected in the HEPA filter samples. Due to continuous use of these filters, particle removal efficiency of these filters gradually decreases, and hence they need to be replaced. This generates substantial radioactive waste containing these two radionuclides as major one. So radioactive waste is usually quantified on the basis of cesium-137 measurement, and strontium-90 quantification is usually not considered. However, estimation of strontium-90 is also an essential requirement before disposal of these filter papers. As we know, gamma spectrometry is the conventional tool for cesium-137 activity estimation. Determination of strontium-90 by beta counting requires either separation of it from separation of strontium-90 from yttrium-90 or from its inactive matrix constituents and variety of interfering radionuclides. Strontium-90 can also be quantified by beta counting when strontium is isolated, by following the ingrowth of yttrium-90 by counting the total activity of strontium-90 and yttrium-90 after secular equilibrium between the two is reached. So one day, health physicists approached us to find out whether there exists any other method which can be used for simultaneous estimation of these radionuclides so that this tedious radiochemical separation method for strontium-90 can be avoided. Hence, we tried to present a simple and rapid technique for simultaneous estimation of these two radionuclides, which is a combination of both LSC and gamma spectrometry without radiochemical separation. So LSC methodology required first optimization of certain parameters, and one of this is the volume optimization of the scintillation cocktail. So we used 1 centimeter by 1 centimeter square glass fiber filter paper. It was spiked with cesium-137 activity, and it was placed in 20 ml borosilicate glass vial. 5 ml of scintillation optiphase high safety scintillation cocktail was added. Similarly, other standards for cesium-137 were also prepared, and they were containing 10, 15, and 20 ml of scintillation cocktails. The same standards for strontium-yttrium-90 were also prepared, and the standards prepared were measured using Packard 4910 TR liquid scintillation counter. After counting the standards for counting efficiency was obtained for various scintillation volumes, and it was observed that the counting efficiency for both these radionuclides was independent of the scintillation cocktail volume. And hence, for further studies, we have optimized 5 ml of OP3 scintillation cocktail. These two spectrums represent cesium-133 spectrum of using LSS, and the other one is strontium-yttrium-90 spectrum in the filter paper sample of LSS. Excuse me. The other slide is missing. It's not there. So the other step in the measurement was calibration of liquid scintillation counter. That is, to have a relation between the quench parameter and the counting efficiency. So we prepared about 10 quench standards of cesium-137 and strontium-90 individually, and by spiking it with cesium-137 was spiked on the filter paper, it was allowed to dry and then placed in the glass vial, and 5 ml of scintillation cocktail was added. Similarly, strontium-yttrium-90 standards were also prepared the same way. Nitromethane was used as a quench indicator. Now, a plot of quench indicating parameter TSI and a counting efficiency was obtained. TSI represents the quench parameter, that is the transform spectral index of external standard. The methodology that we developed was glass fiber filter paper containing both strontium-yttrium-90 and cesium-137. It was placed in glass vial, added 5 ml of OP3 scintillation cocktail. Then the sample was subjected to gamma spectrometry. Gamma spectrometry gave us cesium-137 activity. The same standard was then counted in liquid scintillation counter. The activity, when the standards were counted in liquid scintillation counter, we got gross CPM that was due to both strontium-yttrium-90 and cesium-137. Also, a quench indicating parameter TSI corresponding to these standards was obtained. So we use this TSI value to obtain the counting efficiency of both strontium-yttrium-90 and cesium-137 also. Now this cesium-137 activity, which was obtained using gamma spectrometry, was converted into the count rate using LSC counting efficiency. The count rate of cesium-137 was then subtracted from the total gross count rate of the LSC, and we obtained the count rate only due to strontium-yttrium-90. The calibration curve was used to obtain the strontium-yttrium-90 counting efficiency was used to determine the strontium-yttrium-90 activity. And as these both are in secular equilibrium, strontium-90 activity was thus found out. The upper plot represents gamma spectrometry of cesium-137, the peak corresponds to 662 keV, and the below one is the LSC spectrum, which is a composite spectrum of both strontium-yttrium-90 and cesium-137. The developed methodology was adopted to the spiked samples, and it was observed that when cesium-137 activity to strontium-90 activity ratio was greater than or equal to 2, the activity was within 12%. However, when the ratio was less than 2, the activity ranged within 8%. This clearly indicated the interference of cesium-137 in strontium-90 estimation. It can therefore be concluded that the present methodology includes combination of a rapid, simple gamma spectrometry and LSC technique which does not require radiochemical separation. Experimental results are obtained within -11 to 7.6%. The MDA for strontium-90 and cesium-137 using LSC and gamma spectrometry is 0.07 and 0.05 becquerel respectively for 30 minutes counting time. The present approach can be an alternative in determining cesium-137 and strontium-90 in the filter paper samples compared to the conventional method. Thank you.
Thank you, Dr. Priyanka, for taking up within time. Will not take any questions. It's a very good effort from all the divisions of HSSG coming together, and I request all the users to follow this methodology, evaluate, and then make it a practice. Thank you.
Thank you.
Now I invite the next invited speaker, that is T5012, Dr. Amar Pant. He will be presenting on assessment of radio xenon in reactor systems using gamma spectrometry. Dr. Pant, you will be having 10 minutes for the presentation. Thank you.
Hello. Thank you. I am Amar Pant from Environmental Monitoring and Assessment Division from BRC. First of all, I would express my gratitude to the IARP 2025 organizing committee to giving me opportunity to present my recent work. My topic of my work is assessment of radio xenon in reactor systems using gamma ray spectrometry system methods. The outline of my presentation is, I will first start with the introduction of my topic. I will brief introduce my topic and what is the motivation of this work, and this is followed by the detailed explanation of the experiments. After that, I will explain the discussion of the results, and finally I will conclude my work. As we know, the xenon is a chemically inert noble gas which is present in the very trace amount in the Earth atmosphere. Due to its inert nature and high volatility, it can migrate easily through the atmosphere, and radio xenon migrate widely, and their presence in the environment play a crucial role in the monitoring of abnormal releases from nuclear facilities, like any split or failure or any nuclear incidents are happen. As we know, this xenon has the 9 stable isotopes, and there are the various radioactive isotopes are there, out of which this 4 radioisotope, which is xenon 131 metastable, xenon 133 metastable, xenon 133 and xenon 135, which is regularly used by International Monitoring Station for monitoring of this xenon isotope for any abnormal behavior of any nuclear facility over the globe. And out of these 4 isotopes, these 2 isotopes, xenon 133 and xenon 135, which is having a very high fission yield, more than 6%, and this xenon 133, which is in a half-life of 5 days, which is energy is 81 kV, is present in a longer time in environment expect than from other isotopes. And as these are the gases, novel gases, their standards are not available. That's why their quantification required the sampling of this gas and then measuring using a gamma ray spectrometry system. And any gamma ray spectrometry system, we require the calibration. For gamma ray spectrometry, two types of calibration are required. One is energy calibration and second one is efficiency calibration. For energy calibration, we can use any source like barium-133, cesium-137 and cobalt-60 source. But for efficiency calibration, we require a standard detective sources, which activity we have known. But for these novel gases, radioactive gases, we do not have any standard sources. So that we required a computational technique to generate this efficiency function for that radioisotopes. So for that we have used this activity concentration of this xenon isotope using the Dhruva reactor and using this HPG detector we have measured this activity concentration of this cover gas of Dhruva reactor. The experimental setups we have designed and fabricated this aluminum based gas cell. This gas cell is used for collecting this gas of fission product noble gases and measure this radioxenon. This cover gas is collected from the Dhruva reactors and analyzed using the HPG detector, which is 30% HPG, and coupled with the 8K multi-channel analyzer, and it is used by Intervenor 8 multi-channel analyzer software, analysis software. This is the first picture which is given. Is shown the gas cell, which is having a volume is 22 ml and diameter is 8 centimeter, and the thickness of this cell is only 0.6 centimeter and collar height is 6 centimeter. This collar height is given to this cell to mount easily into the horizontal this 30% HPG, and the window thickness is around 0.8 mm. This window thickness is designed in such a way that this 81 kV of xenon 133 can easily penetrate this cell and it can be measured by this HPG detector. As we know, this standard radioactive standards of this gas cell is not present. That's why we have used these computational techniques. First, we use this HPG detector model by the manufacturer design, and after the modeling, we have this validate this gas cell and HPG detector models with the standard source using the argon 41 standard. And efficiency calibration, which is generated by using this computational technique, are used for the measurement of this radioxenon. This is the efficiency calibration curve of HPG system for this xenon gas cell, which is generated by the simulated spectra. And next to my result and discussion, we have collected this cover gas and analyzed and characterized this few fission product noble gases, which is argon 41. This argon 41 is activation products, and other than this krypton 85 metastable, krypton 87, krypton 88, xenon 133, xenon 135, these isotopes are fission product noble gases which are characterized, and their activity concentration in kilobecquerel per liter are measured in the cover gas samples, and these activities are listed in this table. This is the typical gamma spectrum of this gas cell, in which you can see that this presence of this xenon 133, krypton 85 M metastable, krypton 88, xenon 133, xenon 135, and argon 41, which is always present in the Dhruva reactors. Because Dhruva reactor there is a argon air is used for the for cooling of the shut-off rods. And this is the minimum detectable concentration of gamma ray spectrometry system with this gas cell, which is a 22 ml volume. This is the minimum detectable concentration. And conclusion of my work is this monitoring method provides a valuable data for health physics surveillance, as the release of this xenon isotope is vital parameter for detecting any abnormal plant condition like any fuel failure. The study suggested that computational technique can easily be applied for monitoring of the fission products, noble gases in ambient air using the HPG detectors. And this method can also be applied for the measurement of this xenon gas in the air, but condition is that we have to pre-concentrate this xenon, because concentration of xenon in air is 87 ppb only. For this 22 ml gas, we required minimum 200 meter cube of air to pass through this gas cell. I would like to acknowledge Dr. D.K. Aswal, Director Health and Safety and Group, and Dr. Vinod Kumar, Head Environmental Monitoring and Assessment Division, for their continuous support during my work. And I would like to thank Dr. Sumitra Kar atomic minerals and metals division for the helping in the fabrication of this gas cell. Thank you.
Thank you, Dr. Amar, for presenting excellent work. We can have one question as we are running short of time. If there are no questions, then I'll invite next speaker. Thank you, Dr. Amar. Ms. Jayasthi Mali, she will be presenting her work on neutron fluence rate measurements in experimental canal of FBTR.
Hello. Good afternoon, everyone. I am Jeshti Mali from Radiation Standard Section of RSSD BRC. So today I'll be presenting a paper on neutron fluence rate measurement in the experimental canal of fast breeder test reactor. So first, let us PPT. First, let us understand why do we want to do that measurement. So we all know our much awaited reactor, prototype fast breeder reactor, is in its commissioning stage. So for the core monitoring of PFBR during the FSC, a special type of detectors has been developed, that is high temperature fission counters. So before putting these detectors into the core, first we have to do one detector from the production lot needs to be tested first. So for the testing, the experimental canal of the FBTR has been chosen. So before the testing of the detector, the neutron fluence rate measurement has to be done in that canal for the different energy range. So now the next question comes is how we are going to measure the neutron fluence rate. So we have two methods available. One is active methods and another one are passive methods. So in the active methods, we have precision long counter, that is the secondary standard. Then the transfer standard, we have a spectrometer. Then we have a flux monitor. And in the passive methods, we have foil activation methods in which we have various foils available like gold, copper, nickel, silver, indium, sulfur. So, but the situation there is the experimental canal's dimension is 73 mm. So these detectors, all these detectors available for the active methods will not be able to fit into that dimension. And the next thing is the temperature there is 200 degrees Celsius. So these detectors will not be able to withstand that temperature. So the most suitable method is foil activation method. So in the foil activation method, which foil we have to choose, that is the next question. So we have various type of foil available. For choosing the foil, we need to consider several parameters, that what type of reaction it undergoes, what is its half-life, it should not be too long or too short. Then we have to consider what type of activation product it will be formed. Then the melting point of the foil is very important because the temperature there is 200 degrees Celsius. So for the experiment, we have chosen the gold and copper foil for the thermal neutron fluence rate measurement, and for the epithermal, we have chosen the cadmium covered gold and copper foils, and for the fast fission spectra, we have chosen the nickel foils. So these are the decay scheme of the activation products. Now everything is ready, the setup is ready, let's move to the experiment. So what we have done, we have placed the foil inside the aluminum holder. Then we have taken 3 folders to cover the entire range of the HTFC. The length of that detector is 283 mm. So we have chosen the 3 folder to cover the length. And then we have placed a spacer between these holders to cover the entire length. And we have chosen the elevation such that at that elevation they will test the detectors. Then we have inserted the whole setup inside the reactor experimental canal of the FBTR reactor. The reactor power was 400 kilowatt and the effective irradiation time was 5.23 hours. So now let's go to the measurement part. So using this simple formula, we'll use the activity induce. The cross sections that we have taken the different cross section for the thermal, for the thermal and all the energy range for the different foils. And for the counting, we have used the HPGE detectors, and these are the peaks that we have taken. So using the counts of this foil and using the mass of this foil, we can calculate the fluence rate. But now here comes the another part, that we have to apply the various type of corrections, like decay corrections, because the foil will decay after the time you remove it. The counting time correction, because at the time of counting also the foil is decaying. Next is we have to apply the gamma abundance. So this formula will change into this. The another type of corrections that we have to apply the temperature correction to the cross section. Then we have to apply the self-shielding factor, because the inner layer because in the thick foils, the inner layer are seeing the different fluence rate from the outside layers. Then we have to apply the thickness correction for the gammas. So now comes the result. So these are the values that we have calculated for the different elevations and that we have reported. Now the conclusion is, so like this is the core of FBTR, and the experimental canal is somewhere here. So when we move towards the core of the FBTR, the thermal, epithermal and the fast fission neutron fluence rate, like this three fluence rates increases when we move towards the core of the FBTR. And if we take the average over the detector length, like we can see these are the values of the neutron fluence rate in the 3 energy range. And we can take the ratio also. So with this we can conclude that the spectra in the experimental canal is in the soft region of the fluence rate. So I will conclude, and I'll tell a fun fact, that the use of the foil irradiation is as old as our nuclear test. So during the Trinity test, these are the pictures from that test. There was a radiochemist named as Ernest Kalma. He used gold foil, cadmium covered gold foil for the thermal neutron fluence rate measurement, and he used the sulfur foils for the fast neutron fluence rate measurement. So thank you for your kind attention.
Thank you, JST, for completing within time and nicely presenting what you wanted to present, and congratulations for the nice work of fluence measurement for testing of PFBR detectors. And we can take 1 or 2 short questions. If there are no questions, I once again congratulate and wish you best wishes. Thank you very much.
Thank you, sir.
Now I invite upon the next presentation from MS Novotech Instruments. If representative of Novotech is present here. Yes, please. Yeah, Mr. Manish Pandey. You will have 10 minutes for your presentation. Thank you. Can we start the presentation, please? Yeah.
ये पॉइंटर ये है. Very good afternoon to all of guests. Thank you, sir, for giving us the opportunity. My name is Manish and I represent Novotech Instrument. We are probably the youngest company in Indian market who are distributing this radiation monitoring and safety instruments. We started our journey in 2020 and we try to provide quality international equipment from our partners who are based in Europe mainly, and few of them from USA. So our main line of business is health physics instrumentation, gamma spectrometry, and associated environmental radiation monitoring systems, which we present to the Indian customers. We started our business in the peak of COVID with alone starting after working at Artec instrumentation for long years in India. I started this business and we did a turnover of 55 lakhs rupees. Second year, with the support of you all, we did a turnover of 3.68 crore rupees. Last year, we did a turnover of 6 crore rupees. And this year, we are expecting a turnover of 10 crore rupees in the business. A few important projects which I would like to highlight, which we did for our NPCIL and DAE customers. Kaga nuclear power plant had an old model supplied by the French company and it was drowned in the rains. We upgraded it with the new detector software and make it functional. And with Rajasthan Atomic Power Station, we work with Centronics for their boron-coated ion chamber range. And maybe we got 10 days ago, we got the export license approval from the UK government to supply, and we are in the process of supplying fission chambers and boron-coated ion chamber to NPCIL and BARC. Narora and Rajasthan, we had supplied significant quantities of dosimeters from the French companies, and we do some of the material analysis work in EPR spectrometers, and we are working with the BARC. We supplied 2 units to BARC. We are in process to supply 2 units to RRCAT for their L9 dosimetry program in EPR spectrometer. Only Bruker and a Belarusian company, they make this product. And we represent Berthold instrument as one of the product line. And Berthold is a German company and they are making a beautiful radiation monitoring instrument, especially this neutron monitor. If you see, sir, it is very sensitive from 30 nanosievert to 100 millisievert and a thermal to 20 MeV range. The prices are a little bit on the higher side, but if you see the range and the quality, and there are different options which can be given. If you like to just identify plutonium, we have a different model which doesn't work with the REM wall, but a very portable system which is only dedicated for plutonium monitoring. LB124 is a very good instrument where you can do surface contamination monitoring along with a swipe counter. So you can use swipes to count it, and 170 mm square and 345 mm square as a surface meter. And you can put a GM tube also so that it can act as a radiation survey meter also. This is a new product development by Berthold where they are putting a new detector in which low dose and high dose radiation measurement can be done with ion chamber. And we have this whole body contamination monitoring from Berthold, which can have 24 detectors, plastic scintillator coated, alpha, beta and gamma all together. The key point is that if you want to optimize it, we can put the radars, we can put the CCTV, we can put the doors, we can remove the doors, and the head section is very flexible. If according to the height, it can come down from 210 to 160. So according to Indian condition, the head is adjustable, which can be done in this system. They have 2 very good hand and feet monitors. The first one is based on ZNS AG, and the second one is an industrial model more optimized for NPCIL application with the plastic scintillator coated with the ZNS AG. And this is a portable system, so it can be moved along. It's a big 10-inch display screen here, and the tight geometry is there, so at one time both front and the back of the hand can be tested in this. And if contaminated, then, and you can have, in this we have a detachable frisking monitor also. So both hand and feet monitor and cloth monitoring also can happen with this model. There are few important tritium monitors with Berthold. So LB110 is a proportional flow-through detector in which we can measure the tritium. And this is an particulate iodine and noble gas monitor. If you see, the options are you can choose different detectors, and those detectors can be customized as per your requirements. We have an alpha beta counter which is based on plastic scintillator, and it can be developed as per user requirement in multiples of 2. So standard is 6, but if you want to go up to 10, we can develop up to 10, and then you can use one at each. And earlier models were based on gas. This is based on plastic scintillator. And then we have stationary iodine monitors from the stack monitoring if we want to do. Even on nuclear medicine department also iodine monitoring can be done with this. Different type of GM tubes we have, low range, high range, and ion chambers, which can be coupled with the data monitoring devices. Air monitoring, Berthold is very good in air monitoring devices. So continuous air monitor, they have dedicated plutonium in air monitors, and then particulate also. So depending on the airflow speed, these monitors can be either portable or they can be installed at the site. And we have the second is environmental radiation monitoring system from our partner ENVINET in Germany, and they make products which will be used outside the reactor site and in air, in water, and in emergency situation. These three situations, they have the product. Gamma tracer was very famous, and Mira is a product which is as good as gamma tracer, and they start from 10 nanosievert and goes up to 10 sievert. They are battery operated. We can modify it with solar panels, battery backup. So 10 years of life is guaranteed. It can be mobile, it can be stationary, it can be mounted on the fields depending on the user configuration. The IP grade is IP65 to IP68, different models. For emergency response system, we propose MONA EPR, which is giving spectroscopy, and it comes with a battery, and we can have a nuclide specific calculation. Depending on the detectors what we choose, sodium iodide or cesium iodide, the configuration can be fixed. The data transmission can happen via 4G, LTE, and it can use radio network also. So all three are available. If department wishes to have through satellite link, that also can be incorporated in the offering stage. Now this is SARA, is an spectroscopic monitor which is can be used for spectroscopy in soil and air. Tuna is a special detector for gamma, and it can go up to 2000 meter of the depth. So in my knowledge, this is first detector which I am seeing which can go in such great length. Generally we have 30 to 50 meter depth, but in marine environment, in fresh lake and rivers also, you can use this up to 2000 meters. So this is a very good memory. Additionally, if high dose rate is required, we can have a GM tube also incorporated inside it. So this is one of the very good products from them. And then we have CIRA. CIRA is an aerosol monitoring system, and it is highly customizable equipment. You can use sodium iodide or cerium bromide, and this can be installed outside the plant area and will do the continuous monitoring of the system. And if you don't want to use as a base station, there are 3 different base stations in this, which can be configured as per the department requirement. We also are into gamma spectroscopy, and our intervenor software is one of the preferred software in nuclear power plant and DAE. In past 4 years, we have more than 30 installations in atomic energy department, where our Orion MCA can be coupled with germanium detectors. It can be coupled with other semiconductor detector, and it can be also used. It comes with 2 input also, where you can have 2 germanium detectors at a time, or 1 sodium iodide and 1 germanium detector at a time. It's a 64K true digital DSP based technology MCA. Excellent feedback for this product. ITEC also supplied alpha spectrometry system. It starts from 2, goes up to 8 chambers. And we have a handheld isotope identifier.
It can be coupled with sodium iodide or it can be coupled with lanthanum bromide also. Sodium iodide comes with 2x2 options and 3x3 inch options. Again in NPCIL and BARC we have sold more than 30 to 40 units of this system. Very cost effective if you compare with other competing companies, and you get a true intervener software. So fully spectroscopic manipulation capability in a portable system is available with this product. As I told you, we supply this whole body counter also. This is a standing type 4x4 into 16 inch sodium iodide detector coupled with intervener software for dose management, and the MDA is 150 for cobalt 60 at 1 minute counting. We are working with Indian Navy to provide a customized solution for them for this particular product, where we will be giving the designs where this product can be mounted on a trolley or a truck, and it can be made mobile. So it will be very specific application we are doing in this particular product. Venus is a 4K MCA where 14 pin base detectors, scintillation detector can be coupled. We supplied in Tarapur for a lung counting system. NFC have our lung counting systems. So we supply psionics detectors coupled with intervener software, and Venus for lung counting systems in DA. HPG, we are a small company, not Marion and Canberra. We don't compete. We make small detectors up to 60% HPG. Few customers have our products, and our manufacturing capacity is 30 to 40 detectors a year. So, but our detectors are in KAGA, in BARC, in AMD also, and we continue to supply, but not for the bigger detectors. In handheld, we represent a company called as PHDS. They make electrically cooled germanium detectors, and this is vertical HPG mount, so the capacity is very good. Up to 40% HPG detector is being used. It can come with the vision also, so you can do the imaging along with the detection. If in waste assay monitor we are not looking for full-fledged solution, this may act as a temporary solution where we can do this. We also represent VF, their neutron monitor range, sir, and this is the waste assay system which we represent with a 50% HPG detector. We also supply gamma irradiator for calibration, and this is a special isotope identifier with CJT detectors. So we represent a company CJT S3D, which makes very beautiful detectors, and these are few. Thank you very much for the time, sir.
Thank you, Mr. Manish Pandey, for sticking to time. Thank you very much. And I think your stall is there. People can visit the stall for more details. With this, I'd like to congratulate and thank all the speakers to sticking to time, and we could
Shri Prabal Chaudhary and Dr. Shashank Saindane, the chairs and co-chairs of the session. Thank you, sir. Now, there will be poster display. All the poster presentators are requested to stand near your respective posters. Poster evaluation will be done. We will now take a short tea break. Please take this time to visit the trade exhibitions and poster displays. We will resume this session at sharp 4:45 p.m. I repeat, we will resume the session at sharp 4:45 p.m. And those who have not submitted the PPT of tomorrow's oral presentation, I request you to please submit the PPT along with the pen drive today at before 7 p.m. I repeat, hello, hello. Good evening, everyone. Our final session of the day will be chaired by Dr. P.M. Ravi, Mangalore University, and Professor Ganesh Sanjeev, Mangalore University. This session will focus on environmental monitoring and radioisotope application. And now we'll have a brief introduction about chair and co-chair of this session.
The chair of the session, Dr. P.M. Ravi, retired head, ESS HPD BARC, currently working as visiting professor, carer, Mangalore University. He was Marie Curie postdoctoral fellow of European Commission, worked at Bordeaux University, France. He was a convener in various AERB committees and was actively participating in IAEA MEREIA program as a member of Common Framework Group and Working Group. He has about 150 research publications in peer-reviewed journals, conferences, and book chapters. He was also a member of International Advisory Board of Journal of Radiological Protection, published by Official Journal of Society for Radiological Protection. He has received DAE and IARP awards. His current areas of interest are teaching radiation protection, research activities in environmental impact assessment, sustainability assessment, and green technology. The co-chair of the session, Dr. Ganesh Sanjeev, Senior Professor, Head of Microtron Center, Department of Physics, Mangalore University. His area of research is radiation effects on quantum dots and functional materials, radiation dosimetry, and microtron-based research studies. He has 371 publications in national and international journals and has 253 conference proceedings. He has guided 6 PhD students and guiding 8 presently. He has completed many research projects funded by UGC and DAE BRNS Government of India as a principal investigator, co-investigator and principal collaborator. He is also a lifetime member of ISPA, NAARRI and Indian Science Congress and Geochemical Society of India. I welcome Dr. P.M. Ravi sir and Professor Ganesh Sanjeev sir, and we are handing over the session to them. Over to you, sir.
Good afternoon to all of you. Good afternoon to all of you. And this is the final session of the day. And we have the very important cultural program waiting for you after this session. So I'm sure we will be able to finish it as early as reasonably achievable, taking social and economic aspects into account. So we have one invited talk by eminent personality, Dr. Haridasan. He will be talking on the recent international guidance on radionuclides in food and drinking water. And Dr. Haridasan is already been introduced to this audience when he chaired the session. And only thing which I wanted to tell is he started from a humble beginning and became one of the global experts in radiation protection. So we are all looking for hearing a very interesting talk from him. So Dr. Haridasan, please. I think you have 25 minutes, 20 minutes, as early as possible.
Good afternoon, everyone. Thank you, Chair. I will try my best to finish in 20 minutes. This is about the recent international guidance on radionuclides in food and drinking water. In my presentation, I will cover radionuclides in environment and food. I will very quickly touch on it. Key standards and supporting guidance, relevant requirements in the IAEA safety standard, and brief mention about the Codex Alimentarius Commission report and WHO drinking water guidance. Then IAEA review of studies on food radioactivity and recent safety guidance on food jointly developed by IAEA, FAO and WHO. And the key output was safety report series 114 and Tech Docs 2011. This safety, both of this document I was responsible for publication. As you know, I think I can skip very quickly radionuclides of natural origin, particularly radionuclides in the uranium and thorium series and potassium-40, of which all are present throughout the environment. So natural radionuclides. Radionuclides produced by cosmic ray interactions in the atmosphere. Authorized discharges, that includes both natural and human-made radionuclides. Then fallout from testing of nuclear weapons, which occurred primarily in the early 1960s. The main radionuclides of interest are strontium-90 and cesium-137. Then residual radioactivity from past practices and non-regulated activities. Both natural and human-made radionuclides are present in the environment and in the food chain. Accidental release of radionuclides, for example, steam accident in 57, then Chernobyl nuclear power plant accident, which was mentioned here, Fukushima Daiichi accident in 2011. Cosmogenic nuclides, the main radionuclides are tritium and carbon-14, and the primordial radionuclides, potassium-40, rubidium-87, thorium-232, and uranium-238 chain of radionuclides, out of which rubidium-87, the dose to the individual is approximately 2 microsievert per year, so it is not normally not of great interest. The dose from potassium-40 to humans generally range 165 to 185 microsievert per year. And there, of course, there are differences with gender and age. And potassium-40 in the human body is unamenable to control. So it is out of scope of the standards accepted by all the international organizations. The long-lived radionuclides of uranium and thorium series are present in very low concentrations in most foodstuffs, and the main contributors to annual dose is lead-210 and polonium-210. I will come to this at the end. This I will skip. UNSCEAR estimated dose from carbon-14 as 1.7 microsievert per year through food chain, and tritium 0.009 microsievert per year, cesium 137.35, and strontium 90.56 to have an idea about the likely doses. Key standards, we have two situations in this. At the national level, both emergency exposure situation and non-emergency situation. We are considering two things. For all emergency situation, the applicable standard is GSR Part 7. This is preparedness and response for a nuclear or radiological emergency. The requirements are specified in GSR Part 7 during an emergency. And the associated criteria for use in preparedness and response is provided in General Safety Guide GSG 2 published by the IAEA. And in non-emergency situation, the radiation basic safety standards, generally this is known as basic safety standards, GSR Part 3. All the requirements are stipulated in this safety standard. And for specific international trade after an emergency or during an emergency is mentioned in the Codex Alimentarius report that is to be applied for international trade of food materials. The main requirement in the BSS in non-emergency situation I am focusing, the regulatory body or other relevant authority, sometimes the food authority or whoever it is, shall establish reference levels for radionuclides in commodities. The regulatory body shall establish specific reference levels for exposure due to radionuclides in commodities, construction materials, food and feed, and in drinking water, each of which shall typically be expressed as or based on an annual effective dose to the representative person, generally that does not exceed a value of about 1 millisievert. You see the problems and flexibilities here. The dose to the representative person and value of about 1 millisievert per year. Again, in the next paragraph, it is mentioned the regulatory body shall consider the guideline levels issued by FAO and WHO. For WHO for drinking water and FAO for food materials. So our issues were reference levels. The most regulatory body or national authorities, they don't understand the meaning of reference level properly. These are not limits. Reference levels are levels above which it is not good to expose people and below which optimization should be applied. This is the definition for reference levels. And annual dose about 1 millisievert means what? About 2 millisievert can be about 1 millisievert or 3 millisievert can be about 1 millisievert. So these are national interpretations. Then representative person for food exposures. Then each of the standards that was issued by FAO and WHO at different times, and they used different terminology and different dose concepts for food material. So there is a need for harmonization of these standards, and that is how IAEA undertook a study on radionuclides in food and provided recently a guidance. IAEA published in 2016 a criteria for radionuclide activity concentration in food and drinking water that basically mentioned the uncertainties and non-consistencies in international standards. They did not say use this, use this. No, they just mentioned WHO say this, FAO say this, IAEA says this, like that. So, and they left the decision with the national authorities. That made huge confusion among national authorities, and therefore IAEA undertook a study, and this is published last year as Safety Report Series number 114. Exposure due to radionuclides in food other than during a nuclear or radiological emergency. Part 1, technical material. This gives data of most of the published data until date. They have collected unscared data available until the 2000, and then 2000 to 2024, all the published literature has been scanned and analyzed statistically this information for all the radionuclides available through food products published. And then the key issue was how to implement the requirement number 51 mentioned in GSR Part 3, that is also co-sponsored by FAO and WHO. So a tech doc, this is published last year, and this gives the advice by the international bodies in case of managing food during non-emergency situation, and it could be scaled up during an emergency for taking action or reference or comparison or for all those purposes. And Codex report is applicable only for international trade, and for all drinking water, WHO drinking water guidance must be used. And if there is any doubt or on WHO methodology or the words used, the WHO recently published a document, Management of Radioactivity in Drinking Water. This gives a definition and explanations of things mentioned in this drinking water guidance. Codex gave generally in the infant foods and for food other than infant foods. These are the numbers given by Codex. It applies only for international trade, and it only applies to food contaminated as a result of a nuclear or radiological emergency, and it assumes that only 10% of the food supply is imported, that is contaminated. So this was a huge problem when Fukushima happened. Immediately Singapore, Malaysia and many countries have banned the import of fish and other food products from Japan. So it involves a lot of economic problems. So initially applied to only the first year after an accident, but that time restriction has now been removed. And WHO guidelines for drinking water, it gives two values for gross alpha and gross beta, 0.5 becquerel per liter for gross alpha and gross beta 1 becquerel per liter. To derive these values, WHO used an individual dose criterion of 0.1 millisievert in a year. That is the established value for deriving this number historically for over several years. If screening levels are exceeded, check if this is a once-off result, or then that means you confirm the results, and for gross beta, delete the contribution from potassium 40, identify the key radionuclides that contribute to the dose, and compare with the guideline level prescribed in this guidance. Now, we try to summarize this. IAEA, in its study, they found 4 radionuclides, radium-228, radium-226, lead-210 and polonium-210 deliver over 90% of the total dose from all radionuclides in food. And it is almost 97% of the dose from the uranium and thorium series nuclides, and potassium 40 is excluded. So if any food monitoring program is undertaken at national level, you need to focus only these 4 radionuclides, and you need not waste time for analyzing thorium concentration or uranium concentration in the food samples. Next most important radionuclides are carbon-14, cesium-137 and strontium-90. You can see the percentage. But large differences to be expected at national, regional, local and individual level. This is one observation. There are some data issues. This is the actual dose that is calculated based on the 158 dietary surveys and studies reported in journals. And you can see polonium-210 is the maximum contributor and lead-210 is the next contributor. So seafood, especially mollusks, have the highest concentration of polonium-210. So if there is a huge fish intake, then there is a possibility for high intake of polonium-210. Which individuals receive higher doses? Fish and shellfish concentrate polonium-210. Certain wild animals accumulate polonium-210 from aerial deposition and do some wild mushrooms. Cesium-137 accumulates to varying degrees in all forest products. Cesium-137 and strontium-90 accumulate in freshwater fish. This was the conclusion of this survey. These wild animals, recently there was an issue in Sweden. Wild animals meat from the market, suddenly they found a high cesium-137 concentration. And they were thinking how it can happen. And they found that these animals migrated from a Chernobyl impacted area to kilometers away, maybe 1,000 kilometers away. They moved, and suddenly in a market they found these animals got contaminated, some wild boar's meat. So they issued some advice in their website to manage how to manage this less intake of this meat, etc., etc. They did not ban the food, but they gave some advice. For natural mineral waters and bottled packaged waters are generally classified as food, not as water. Only tap water is considered as drinking water by the WHO. And the key radionuclide to be analyzed is lead-210. So in the new approach, the two approaches are outlined: assessing dose from the diet and assessing radionuclide concentration in individual foods. Food samples are representative of the diet. Radionuclides analyzed are those that are known to be the most significant contributors to dose, and dose assessment of food samples based on the food consumption data for the country or region in question. If there is no consumption data available, WHO has a database called GEMS, G-E-M-S. This database gives worldwide food consumption data on a regional basis. So Southeast, Northeast on a WHO region. So this data can be used as a default if there is no actual measurement or data available on the food consumption. For the individual foods, assessing radionuclide concentration of individual isotopes it should be based on derived guidance levels. So this is the terminology now they have agreed upon. Use guidance levels. And it enables harmonization with the WHO guidelines for drinking water quality and considers statistical distribution of natural radionuclides in foods that could exceed guidance levels. There are several methods for diet analysis, either total diet or market basket, sample directly from a canteen and what you consume, or duplicate diet method, or canteen meals method, individual foods method. There are many methods, and this is explained in safety report series 114. If you are interested, please have a reference. And this is the basic equations for estimating doses. You can see activity concentration and the mass intake, the mass of food consumed per year. A default value of 550 kg per year is used for calculation, most calculations. again for the individual radionuclide, the individual dose criterion used is 0.1 millisievert in this case. So this tech doc number 2011, this gives radionuclides values for those who do analysis. They can compare this table for their reference, and if it is below that, then forget and do nothing. That is the advice they give. Or sometimes it may be above that values, then this book also for individual food items, they suggest use the 95% percentile. And 95th percentile value is given in table 4 of this guide. So you need not work on it. So just refer, and a 95th percentile value, for example, a crab sample, and suddenly you found that the cesium 137 this much, then have a look on this number, and if it is below that, do nothing. That is the advice like this. So a flow diagram is given. So here you can see the first question is this a nuclear or radiological emergency? Then if it is yes, then you must refer to GSR part 7 and the Codex report and the GSG2 guidance. If not, if it is a normal situation like this, then you decide whether it is a general diet sample and analysis or individual food items that is being analyzed. So different radionuclide, 4 radionuclides identified is given, and all other cesium and strontium is also to be checked. So compare with the guidance levels provided in table 3 and table 4 of this guide, and you can follow this pathway. So if the guidance level consistently exceeds, then only one should think about consider actions to reduce dose. It is not banning of the food products, but to provide some advice so that people get low exposures. You can see the first 3 columns were the historical, and then the tech doc you can see in non-emergency, the reference level criteria used is 1 millisievert per year, and the individual dose criterion used for calculating the values is 0.1 millisievert per year. And monitoring programs is also very important. Activity concentration, if it consistently exceeds values in table 3 and 4, then only establish a long-term monitoring program at a national level. Can be easily scaled up in the event of a nuclear accident. So that is the advantage. And it all depends on the national resources, capabilities, and availability of equipment, etc. It is good if you could participate in the Almera network of the IAEA. They have a laboratory network, and they do periodical intercomparison exercise, etc. And this data will be always useful for trend analysis purpose, to provide reassurance to the public, or to ensure compliance with regulatory requirements in planned exposure situation. So a data collection will always help. To summarize, this is the advice for the food and drinking water. Apart from during a nuclear or radiological emergency, the dose received from radionuclides in the diet is managed as existing exposure situation. Assessing compliance with the dose requirement of about 1 millisievert for food seems best achieved through the collection and analysis of diet samples. You need not analyze each of the food items. So general diet, what you consume, just do a screening type of analysis. For baseline dose, it recommends canteen meals approach, that is direct thali analyze and then give the baseline data information. Then for representative person, a duplicate diet approach is always recommended. And there are 7 radionuclides to be checked for food, the 4 natural radionuclides and the 3 the carbon 14 also. That contribute bulk of the dose from the diet. In situations where individual annual doses assessed from diet sampling approach or exceed a value of about 1 millisievert, Again, this is an interpretation of the national regulator or the individual who is doing this. It is about 1 millisievert, and then only you do analysis of individual food products that would be appropriate. For natural radionuclides, that contribute about 90% of the total dose. For these 4 radionuclides, 95th percentile activity concentrations have been developed for several food categories. So in this book, there are individual food items and the 95th percentile values to be referred. For some radionuclides and food products, activity concentration at the 95th percentile value may result in doses to consumers that exceed 1 millisievert. Suppose if they have a persistent, consistently large quantity intake, then probably there may be a possibility of exceeding 1 millisievert as well. But these may be appropriate for use as reference levels for the 4 radionuclides in question. For all other radionuclides, it is suggested that the WHO guidance values for drinking water be used directly as reference levels for food. The guidance values developed by the WHO for drinking water are appropriate as reference levels for food products. Exceptionally, uranium in food products should be assessed based on chemical toxicity rather than radiotoxicity. And in all these cases, justification, optimization, and graded approach are very important. So, I thank you.
Thank you, Dr. Ravidasan. Now the session is open for questions, couple of questions.
Haridas, nice presentation. Just wanted to ask you why potassium 40 is not added in the list of radionuclides considered for bulk dose from diet.
Yeah, potassium 40 is homeopathically controlled in human body, and whatever you intake, it is already automatically adjusted, and you get an average dose of 170 microsievert, depending upon your weight and etc. And you cannot have a good control over this dose in the human body from the potassium 40, and therefore potassium 40 is out of scope of the BSS or the safety standards of the IAEA. It is not included.
Because the consumption patterns are different from child to...
Because you cannot do, it is not viable to control.
Milk and other...
It is basically unamenable to control. That is why it has been taken out of the standards.
Yeah, general question regarding the controversy of uranium in drinking water. Yes. Prior to 90, WHO made a limit of 140 ppb. All of a sudden in 90, they brought it down to 2 ppb. Then they brought it down after a few years to 15 ppb. Now they have brought down it up to 30 ppb.
Yes.
Okay, and you made that chemical toxicity should be looked into, but the different nations have got different limits.
Yes.
Okay, for example, Finland has got 100 ppb. Okay, there are some Slovakia, I think they have got 370, depending upon the uranium in drinking water. Yeah. Okay. Now, the question is that when there is so much of variation, and the Finland report clearly said that they have not received any negative impact in their population, even they were drinking up to several hundreds or up to thousands of ppb. There are detailed reports written there. So why does the WHO dance upon these numbers?
That's a good question. I am unable to answer this from the WHO side, but to my understanding, these numbers, they use this 0.1 millisievert criteria for deriving the values for the ppm or ppb, and the dose coefficient is also periodically changing. Now you see the occupational intakes of radionuclides. There are 5 volumes has been published quite recently.
Your question is different.
Yeah.
When there are solid studies, particularly in the Finland,
yeah,
that the large population who drank the drinking water had no effects, ill effects.
Yes.
Okay, even from the chemical toxicity point of view.
Yeah.
So how does they come up these kind of numbers?
The WHO is always saying that they are on public health perspective. See, when for the radon, IAEA basic safety standard prescribed 300 becquerel per meter cube, WHO prescribed 100 becquerels per cubic meter. And when we asked WHO, they said, we are considering on a public health perspective and we want to give world a message that this should be reduced, and because children are there, infants are there, there are a different group of people in the community, so they want to reduce. So a similar approach is also taken in the drinking water.
No, I feel that is unscientific one. Okay,
yeah.
thank you. Just a similar one in addition to this question, what I am asking is, this most of this means decision by this IAEA for uranium in drinking water is 30 ppb. And most of the countries which are participating is all European countries, and but in the most of the European countries the levels are much lower. Say Germany 2 ppb to 5 ppb, like that they are keeping. So they are not even following the WHO standards also, even though they are participating in the WHO, but and in determining these values.
Yeah, WHO standards is like an advisory nature of standard. It is not that legally binding. Legally binding is mostly in the case of IAEA if IAEA support is taken by the country. Still, for other countries, it is not even a binding, legally binding. So therefore, WHO gives a general advice, and their role is mostly important when during or immediately after an accident. Everybody looks at the WHO numbers for that.
Okay, last question from my side.
Yes, please.
What happens is all the K40 from the body is removed?
All K40 from body removed?
Is removed, yes.
You will die.
So it means you agree that some radiation is needed?
Yes.
Right?
Yes.
Then, and that's what I argue upon. The radiation protection, you say that any radiation is harmful. So there is a contradiction. So as a established IAEA expert, now, can you resolve this paradox?
I think this morning we had an excellent lecture from Maya Sab on this, how this has been derived at, and he also mentioned this LNT and other modeling and how they look at, etc. I think different times for different purposes, different standards have been developed, and that is why recently this IAEA, because of this member states complaints, they have started harmonizing things. So FAO and WHO and IAEA sat together, the relevant sections and committees, and they agreed upon this number now. So this is the current number, but it is not legally binding for India to take it and go forward. But if we deviate from international guidelines, it's very likely that this can be questioned in our legal system. That is where we should take a cautious approach.
Okay. Last question.
Yeah. You told it is not legally binding on any country. But when I see the methodology, when people are arriving at these numbers, the consumption rate, that plays a very important role.
Yes.
For example, I found the data from Japanese who consume fish all the 3 times.
Yes.
Whereas if you take India,
yeah,
I don't think there is any family who is consuming fish, and many even will not, once in a week they don't consume. So just by this number, if they arrive at using the data of a country who the consumption rate is very high, and go to a country where the consumption rate is extremely low, you will be giving an impression for them that even for their consumption, they may arrive at a very high dose.
Yes.
So I go by your statement that it is not legally binding, but what impression it gives to these different countries?
Yeah, but this for harmonization purpose, they have checked all the regional and national consumption pattern that is available. This data is periodically available with the WHO, and they got a regional database, as I mentioned, the GEMS database. And from this, if they want India consumption pattern, they have some data. And if they want a regional southeast region of the world, then they have some data. And a number has been arrived, a consensus and average, or I don't know.
That is exactly I'm asking.
Yeah. But there may be cases, this also the questions. If there is a heavy intake of a particular type of food, then there may be cases that can go beyond 1 millisievert per year. In that case, maybe a restriction or an advice. Food restriction is extremely difficult, and those countries they have restricted has had problems. So what they suggest is to give a proper advice to public that please have this meat only once in a week, or reduce the intake into say 5 times in a week, something like that. So not that this food should not be taken as because this is giving high dose.
I think
that should be the approach.
I think we can, because it's a very interesting topic, and I'm sure there will be a lot of discussion. Yeah. So, if there are no more questions, I thank Dr. Haridasan for his wonderful, thought-provoking lecture, and thank you for that, and especially concluding within the time.
Thank you.
So now I will, next presentation is by Anmol Batra, and he will be talking on a diagnostic two-dimensional wind field model based on point iterative technique. Anmol Batra, please.
Hello.
So you have 10 minutes, 8 minutes presentation, 2 minutes.
So good evening everyone. This is Anmol Batra from Radiation Safety Systems Division, BARC Mumbai. Today I am going to talk about a diagnostic model that is developed to generate a two-dimensional wind field based on a point iterative technique. So I will start by discussing that what is the need for such a model and what are its practical applications. Now, the knowledge of wind field data serves various purposes such as atmospheric dispersion modeling. Now, any material that is released either accidentally or deliberately into the atmosphere, the transport of such a material is heavily dependent upon the wind speed and wind direction. For the purpose of understanding how these pollutants will spread into the atmosphere and what will be the concentration at specific locations of interest, atmospheric dispersion models are used. And wind field data is one of the most critical input which is required by these models. Next, the wind field data is also used for the purpose of weather forecasting. It is used as initial condition and boundary conditions for various numerical weather prediction models, which are used to simulate the behavior of atmosphere on the basis of fundamentals of fluid mechanics and thermodynamics. Then, by analysis of wind characteristics at specific locations, one can get crucial insights about the wind turbine siting, the turbine performance, and the overall energy generation. Now, because of these numerous applications of wind field data, the measurement of this data is carried out using various weather stations, employing some remote sensing techniques or through satellites. But these measurements are often very sparse or they are unevenly distributed. So, a mathematical technique of interpolation is used to estimate the wind field data at the points where the direct measurements are not available. But while serving a useful purpose of finding out the wind fields over the entire domain, this interpolation technique has some challenges with it. First one is it excludes local factors. The wind speed and direction, it can vary significantly over short distances due to various local factors such as some terrain effect or the different land use types. But while interpolating, it is assumed that there is a smooth or continuous variation between the observation points. So this leads to discrepancies. Then error propagation. Now, if there is an error in the measurement itself, it can propagate to the entire domain through the process of interpolation. Then the most serious drawback of using this interpolated wind field data that it does not take into account any of the physical principles such as the conservation of mass, momentum, or energy. So to overcome these shortcomings of interpolated wind field data, a diagnostic approach is used to model the wind field data over the entire domain. Now, how these diagnostic models work? These diagnostic models use the interpolated wind field data and as an input and adjust or make the corrections to this data so that the physical principles are satisfied. So this diagnostic approach ensures that along with the usage of mathematical technique, the physical principles or the physical reality of the system is also taken care of. So the diagnostic model developed here, it is based on the principle of conservation of mass, which states that the mass can neither be created nor be destroyed within a closed system, and it can be represented mathematically in the form of a continuity equation. This continuity equation states that the rate of change of mass within a controlled volume can be balanced by net mass flux entering or exiting the volume. Now, for various practical purposes and to simplify the situations, especially for smaller spatial scales where the variation in temperature or pressure, they are not significant or they are too slow, the density of air can be assumed to be constant and air can be regarded as incompressible fluid. Under this condition, the continuity equation is reduced to the form which states that the divergence of the velocity field should be equal to 0. Now, the methodology for this interpolated wind field to satisfy this continuity equation was introduced by Enlich and is based on the point iterative technique. Now, since these interpolated wind fields, they do not satisfy the continuity equation, so there exists a finite value of the horizontal divergence, which is represented by delta here. This equation, it can be discretized about the point ij using the central finite difference scheme. Now, our purpose is to find the u and v components such that this delta is either reduced or it is removed. Now, this can be achieved by applying equal and opposite corrections to the u and v points. The corrections to the u component is done at the points which are shown by the red cross here, and the v components are corrected by at the points which are shown by blue marks. And the corrections are represented by u prime and v prime. Now, in this equation, the right hand side to be 0, these terms added should be equal to the minus of delta. And by assuming that these components contribute equal in cancellation of delta, the u prime and v prime can be written in terms of delta. After applying these modifications, the final wind field components about the point ij can be shown by this set of equations. Now, if the new delta is calculated using these equations, it has reduced to 0 at point ij. But these wind components have altered the delta value at the neighboring point. So that delta value is also reduced using the same procedure. Then the step is repeated for the entire domain. But it is quite possible that all the points do not receive significant divergence reduction after this process. So the iterations are continued until a required convergence is achieved. Now, this non-divergent velocity field could be an example of an ideal wind field for which the continuity equation is satisfied. But to test our algorithm, we have altered this field to introduce an artificial value of divergence. So there were two cases made, each of which is differing by the magnitude of this artificially introduced divergence. In the second case, this value was higher than in case 1. So these are the results which are present for case 1. On the left hand side, we can see the original divergence for case 1 was 0.5 over the entire domain. And on the right hand side, we can see that the divergence is reduced to an order of 10 to the power minus 7 to the 10 to the power minus 8 over the entire domain, which shows that the model is performing satisfactorily. For case 2 also, in which the divergence was higher than in case 1, and its value was 0.9 over the entire domain, the model reduces the value up to an order of 10 raised to power minus 7 to minus 8. Now this represents the original and the adjusted wind fields for both the cases. An important point to note here is that in case 2, the deviation of the adjusted wind field is more than in the case 1. This is because, as in case 2, the magnitude of artificially introduced divergence was higher, so the more amount of corrections were applied to the original wind field so that it can adjust it to reduce the divergence. Now coming to the conclusions, the developed model is very effective in removing the divergence and it does not use any boundary conditions. The final value of reduced divergence for a lower initial divergence case achieves a similar order as with the higher initial divergence case, but the magnitude of corrections applied and the number of iterations used to receive the convergence criteria are depending upon the degree of divergence. So with this, I thank you, and I thank you all for your kind attention.
Thank you, Anmol Batra. Now the session is open for 1 or 2 questions. If there are no questions, let us thank the speaker, Ms. Anmol Batra. Thank you. The next speaker is Mrs. Arya Krishnan K. She will talk on thermal oxidation and liquid scintillation counting method for the carbon-14 determination for quantifying the natural and synthetic components in bio-based products.
It's on? Yeah, thank you. Good evening all. My name is Arya Krishnan. I'm a PhD student at Career, Mangalore University. So first of all, I would like to thank IARP for giving me this opportunity to present my research work in front of you all. The presentation title is Thermal Oxidation and Liquid Scintillation Counting Method for the Carbon-14 Determination for Quantifying the Natural and Synthetic Components in Bio-based Products. So we all know that there is a high demand for bio-based products these days, whether it be food products, cosmetics, flavorings, or any aromatherapeutic products. What we look into it is the label, natural, or organic, or herbal, right? So the demand for these products are increasing very quickly. So we can see a bar diagram here, wherein in 2023, the global bio-based material market size was about 41 billion, but it is expected to be about 396 billion in another 8 years. So with this, we are very much able to say that the bio-based material production global market size is going to increase very quickly. Also, the export of spice, specifically in India, the export of spice and spice products has valued to be about 4,464 million US dollars. So the growing demand for this bio-based product is a cause of concern. Why? Because when the demand is high, there are higher chances that these products can get adulterated with synthetic or any other petrochemical derived materials. So due to this issue, many countries, most of the many developed countries has implemented a rule wherein they have to produce, the exporters or the manufacturers has to produce certain certification on the purity of the products. If not, they are not able to export the items to other countries. So in order to assess the purity of a bio-based product, you need to have some analytical techniques, right? So these are some of the analytical techniques which are being used right now: GCMS, FTIR, HPLC, etc. But these methods are not very useful when the adulterants are, synthetic version of the original product. For example, let us say turmeric powder. Turmeric powder, if you know the composition of a turmeric powder, it is very easy to produce it in the laboratory. With GCMS, you will be able to know the composition of a turmeric powder. So we can prepare literally a turmeric powder, a synthetic version of a turmeric powder in the laboratory. But with these methods, we are not able to say whether the turmeric powder is pure or not. We can only say that this turmeric powder has this composition. So GCMS, FTR, and HPLC are not able to say whether the turmeric powder is synthetically produced or naturally produced. So this is where carbon-14 comes into picture. So carbon-14 is the only authentic method which we can rely on to determine the purity of a bio-based product. So there is an immense need to develop carbon-14 measurement techniques across India in order to help exporters, so that if more exporters is happening, then the economy of a nation will be enhanced. Okay, so as I said, detection of adulterants by carbon-14 is one of the tools to determine the adulteration. But how? As we all know, carbon-14 is a naturally occurring radionuclide, which is having a half-life of 5,730 years, with endpoint energy of 156 kilo-electron-volt. So naturally, carbon-14 is released by the interaction of cosmogenically derived neutrons with nitrogen atoms present in the atmosphere. So once carbon-14 is released to the atmosphere, it quickly oxidizes and becomes carbon dioxide. And this carbon dioxide is assimilated into plants. Okay, I have given a pictorial representation here. You can see here. So I have taken caffeine powder as an example. So caffeine powder is extracted from coffee bean. Okay, so the C14 specific activity in the atmospheric air is about 226 becquerel per kg of carbon, which is equivalent to 100 PMC. So PMC is percent modern carbon, which is the unit that has been using. Currently, we are using PMC as the unit for carbon-14 specific activity. So 226 becquerel per kg carbon is equal to 100 PMC. So a natural product will have a C14 specific activity of 226 becquerel per kg of carbon or 100 PMC. So a caffeine powder is expected to have a C14 specific activity between 95 to 105 PMC. This range has been given by ASTM, American Society for Testing and Materials. So if we have a caffeine powder and if we determine the specific activity of this caffeine powder, if we get the carbon-14 specific activity between 95 to 105 PMC, we say that it is completely natural or organic. If we get a carbon-14 specific activity below 95 PMC, then it has been adulterated with synthetic caffeine component. That is how we determine the presence of adulterant. So basically, there are two techniques for the determination of carbon-14. One is accelerator mass spectrometry, AMS, and another one is liquid scintillation spectrometry, LSC. So in India, there are only two facilities available as of my knowledge. One is in PRL and another one is in IUAC, where AMS facility is available. Okay, next one is liquid scintillation spectrometry. It is again divided into three: benzene synthesis followed by LSC, CO2 absorption followed by LSC, and direct LSC. So benzene synthesis followed by LSC is quite laborious. Also, the sample preparation is very complex and it is expensive as well as time consuming. As I said, in the case of benzene synthesis, but the accuracy of benzene synthesis followed by LSC is much more compared to the CO2 absorption followed by LSC as well as direct LSC. But the thing is that since it is very much time consuming and laborious, for the for the adulteration purpose, it is not at all recommended. It is not at all recommended, but it is not that viable. In that case, we'll go for the CO2 absorption followed by LSC. And in AMS, in the case of AMS, the thing is that since we have only two facilities in India, these common people like manufacturers or industries cannot approach them. It is only dedicated for the educational purposes. So we need to have a method which is very much easily available for the exporters or exporters or the manufacturers. So that is why CO2 absorption followed by LSE is one of the most used method right now. So in our lab we have a spiralizer system and LSE. So for this study we have analyzed about 40 samples of commercial products, including turmeric powder, caffeine, beetroot extract, vanilla extract, berberries extract, beet extract, moringa extract, etc. So we have what we have done is we have combusted the sample in the pyrolyzer system at about 500 degrees Celsius using organic program. So the carbon dioxide released during the combustion process was absorbed in an absorber, and it was mixed with scintillator and subjected to LSE. So then after that we have calculated the C14 specific activity as discussed in our previous publications. So coming to the result and discussions, out of 40 commercial samples analyzed in this present study, C14 specific activity of 32 samples ranged between 95 to 105 PMC. You can see I have given a range of 95 to 105 PMC, which I have discussed earlier. So out of 40 samples, 32 samples were within that range, but 8 samples were below that 95 PMC line, which shows that these were adulterated with synthetic materials. So out of 8 adulterated samples, 5 of them were having a C14 specific activity below 10 PMC, which indicates that these were completely synthetic materials. So to conclude my talk, the capability of the thermal oxidation and LSE-based method for the carbon-14 determination to quantify the natural and synthetic component in commercial product labeled as natural products was demonstrated by analyzing varieties of samples. Out of 40 commercial samples analyzed, 32 were obtained to be natural or organic, and 8 of them were identified to be adulterated with synthetic materials. The facilities available at the Center for Advanced Research in Environmental Radioactivity being used by about 40 industries from different parts of India right now, and we are getting lots of samples from different parts of India, mostly southern part of India, and we are so happy to extend our facility to them so that they get help out of it. Thank you.
The paper is open for discussion.
In order to prepare the synthetic caffeine or the synthetic turmeric, don't you think there might be some components which are also containing natural carbon-14 or compounds?
No, ma'am, no.
Nothing?
Nothing.
Totally
it is totally synthetic material, does not contain any carbon-14 in it.
Totally inorganic?
It is that, yeah, it does not contain the carbon-14. It contains carbon, but C14 is 0 in that. So C14 is what we are looking for. If C14 content is 226 becquerel per kg of carbon, then it is completely natural. If not, it is not natural. If it is completely derived from synthetic materials.
Okay.
Yeah, thank you.
Any other question?
Hello.
Yes,
yeah, it was a nice presentation.
Thank you, ma'am.
I have 2 questions.
Yes.
How much weight you have taken to pyrolyze the sample?
Okay.
And Quantalus, that 1220 system you have used.
Yes.
So what is the MDA for that, carbon-14 measurement?
Okay. Yeah. To answer your first question, we have taken about 3.5 gram of organic product for the combustion. And like any organic samples we combust, we take about 3 to 3.5 grams of that sample. That will be enough for us. And
but how you have optimized that amount?
Okay, so what we need is we need to saturate the absorber. Otherwise, quenching effect will be there. So if we are able to saturate the absorber up to 2.3 grams of carbon dioxide with 2.3 grams of carbon dioxide, then the quenching effect will not be there. So we have optimized taking from 2 grams to 2.5, 3, 3.5 like that, and we analyzed whether the absorber, 10 ml of absorber is saturated or not. If it is saturated, we'll take it for we'll mix it with scintillator and take it for counting. So the main criteria here is to avoid quenching, we need to saturate the absorber. So for that, for saturating the absorber, how much grams of sample is required, that much sample we take for analysis. So that was about 3 to 3.5 grams.
Okay. And what is the MDA?
MDA for a 500 minutes counting time, it is 12 becquerel per kg of carbon. And if it is 1000 minutes counting, it is 7 becquerel per kg of carbon.
Okay. Thank you.
So, if there are no more questions, we thank Arya for the wonderful presentation.
Thank you, sir.
And now we will call upon,
thank you.
I think R. Jana. I think Anu David Raj is not there. She has not come, I think. So now we will call upon R. Jana to present her paper on study on the significance of geolocation of micrometeorological stations on short-term Gaussian puff modeling in complex terrains using argon-41 as a gamma tracer.
Good afternoon, all. I am Reena Jana. Thank you, Chair, for giving me opportunity to present the paper entitled Study on the Significance of Geolocation of Micrometeorological Stations on Short-Term Gaussian puff modeling in complex terrains using argon-41 as a gamma tracer. So this title itself is containing the so many complexity in the study. Here, short-term means geospatially near field, and temporally it is sub-time scale. Usually in air dispersion modeling, we use 1 hour as the standard time period for the atmospheric modeling. Above it, this Gaussian puff model is advanced model upon the Gaussian plume model, which is usually used for the monitoring of mapping of pollutants, if it is there, especially the radionuclides here, and it is primarily for the monitoring and emergency preparedness purpose. So how we come into this study. Previously, for a decade, we were studying on the time scale of the such kind of air dispersion modeling, but recently we have documented it that 10 minutes per second, that micrometeorological field in 10 minutes average period is the optimized period, which is recently published by myself and Prabal Chaudhary 2024. So based on that, there we have found that the wind field in surface layer have shown a complex flow pattern over complex terrain, which becomes even more intricate during averaging period shorter than 1 hour, and hence we arrived at the optimized period. So in the present study, we tried to find out that what about the impact of the geolocation of the existence of the micrometeorological station. So thinking that we have this field study is carried out. Of course, our field stations are experimental stations which are existing throughout the year, but such kind of analysis or study we carry out as and when we think about. So in the present study, it is further focused on the evaluation of the importance of multiple micrometeorological observatories to incorporate in air dispersion modeling system to arrive at a realistic dose rate at any given moment at any geolocation. This study has importance to plan and handle near-field radiological and nuclear emergencies, especially for the short-term event, which is just for a day. This is the several sections how we have planned the field experiment. The prerequisite of this study is the study area should be a complex terrain having sub-timescale data generation facilities. Here we have used advanced micrometeorological instruments called 3D ultrasonic anemometer and along with other associated sensors, assessing complex terrain module of Gaussian puff air dispersion model, and also we have used gamma radiation measurement facilities at interval of 1 hour, which is taking instantaneous value, but that averaging period is 1 hour. And then the analysis and inferences. The study area is taken BRC Trombe site, which is a hilly valley, which have hills, valley, and coast of Arabian Sea. Spelling of Arabian Sea is wrong here, please pardon me. Through determination of digital elevation model. And data acquisition has been done in 10 minutes interval, continuous data, but averaging period is 10 minutes. Throughout the January month, data has been studied, but one-day data has been taken into account for 2 locations, which is named as MMS1 and MMS2. And 3 case studies are carried out. See if the only MMS1 is present, what will be the situation in argon 41 distribution. And case 2 is only another station is available, and the case 3 is both the observatories are available. So it is a stochastic analysis of model output as gamma dose rate at receptor point versus measured by detector by eliminating background radiation. So determination of background radiation is one of the important study in this. So one day is selected purposefully. The day is selected when heterogeneity is maximum due to the wind direction, which is residing at the line of sight of Gaussian puff model's receptor, as well as the measuring instrument of airman. So wind field along with associated essential parameters from 2 experimental meteorological stations, as I have told before, the one is near Bhaba Point, other one is Mandala Hilltop. Who is aware of the BRC campus, they can understand it easily, which is apart by 4 kilometers on the complex terrain. Standard daily source term is used of that argon 41, which is stack release of Dhruva from 100 meter stack, which is a research reactor. And the gamma dose rate was assessed at each receptor's point, considering all Gaussian puffs in influence, assuming the spherical puff, that is sigma y and sigma z is same as the air dispersion coefficients. That influence of that radius of influence is considered as 1 kilometer. Basis of the gamma dose model, a semi-infinite cloud model at the ground level. So for the estimation of gamma dose rate, it is used, and all uncertainty is minimized by the these 4 steps, and residual uncertainty factors are neglected. in this study. The study examined the correlation between the estimated and measured dose rates using a linear relationship. This is the complex terrain of BRC site. It is derived from the using shuttle radar topography mission data, which is NASA's data, with a special resolution of 90 meters to get one elevation data. But further, we have reduced it to 250 meter horizontal resolution for our easy study. We can see the complex terrain of this, the land with DEM and the coastal land, and also the what is called present of the sufficient water bodies as Arabian Sea. So source is very near to the MMS1 and detected is around 300 meters away from the source. This is one part was from the measured airborne data. It was necessary to eliminate the background radiation to go for the correlation study. That minimum value of hourly gamma radiation measured by airborne within taking 10 years observation 2013 to 2023, having just 1 nanogray per hour variation for the January month for the day. So that way we have found that the value of mean, max and minimum dose rate of airborne, and it is found 70 nanogray per hour, which is having diurnal standard deviation below 1 nanogray per hour. So after eliminating background radiation, the correlation coefficient is studied for under case 1, case 2, and case 3. We can see when we are taking MMS1, the correlation is very poor, but that meteorological station is very near to the 100-meter stack. But in case 2, it is showing good correlation with a good t-test, and in case 3, it is further improved. So the conclusion is that there was significant heterogeneity between data of MMS1 and MMS2 on the study area as this case study, and it was verified through the correlation coefficient. And why such heterogeneity has been seen? As I have told, it is complex terrain. It is not only the case. The case is that it is also non-monsoonal period where and winter day where the complexity of the wind field is more crucial. In this particular day, neither the local land breeze and sea breeze, usually land breeze, sea breeze cases, we get the harmonization, but that kind of possibility is also eliminated from this study. So as a result, we can say that maybe internal boundary layer is playing a crucial role for this complex terrain. And that way I concluded, and this is the reference. Thank you.
Thank you, Arjana. The session is open for only one question. If there are no questions, let me thank Arjana for a very informative lecture. With this, we conclude this session. We thank all the speakers for maintaining time appropriately. Thank you everyone.
Thank you, sir. I request Dr. M.S. Kulkarni, former Head Health Physics Division, BARC, to hand over the memento to Dr. P.M. Ravi and Professor Ganesh Sanjeev, the chair and co-chair of this session. Thank you so much, sir. Now, I request Dr. Karunakarayan, convener IARPNC 2025, to come on the dais for further proceedings.
In which one of the life members of the IARP, Dr. K. Tayalan, Kuppuswamy Tarayalan, as you know, recently he has brought out a book on radiation safety manual for hospitals and healthcare institutions. This English book was available in the market, and recently this Kannada version of this book has been is being brought out, and Dr. Sayalan has requested the organizers to have the possibility of getting this book released in this before this August gathering. So accordingly, we had a discussion, and we thought we will have, because this book is very relevant to the medical physics students, and the Mangalore University has a medical physics program, and in its context, and also the book is coming in the Kannada language, the edited version of this English book. So we thought we would get it released here in front of you, and for this a brief function, I request Dr. Aswal to come over the dais, and I also request Dr. Tayalan to accompany him. I would like to briefly introduce Dr. Tayalan. Dr. Tayalan is a senior medical physicist in India and presently serving as head medical physics division, Dr. Kamakshi Memorial Hospital Private Limited, Chennai. Earlier, he served as professor of radiologic physics, Madras Medical College. He has 36 years of experience both in clinical and teaching. Dr. Tayalan has been engaged, is involved in teaching assignments in Mangalore University as well, and he is one of the well-known teaching fraternity among the medical physicists in the whole country. So may I request the volunteers to get the books to Dr. Aswal. Yeah. Thank you, sir, for kindly agreeing to release this book. And on behalf of Dr. Tayalan, would like to thank Dr. Aswal.
Okay. Good evening to all. I am very thankful to this IARB National Conference organizers as well as Karnar Rao and the Health Physics Director for having released this in an appropriate forum to this radiation safety manual I incorporated what is the AERB guidelines as well as NABH guidelines relevant to the hospitals. We started 2 years back actually putting in English. Some 2000 copies we actually give free of cost only bulk only we do this as a awareness program. Then we converted into Tamil. Now this is the third attempt it has come in Kannada. So therefore I thank every one of you for gracing the occasion. Thank you very much.
With this, we conclude today's session. Let's have a big round of applause for all our distinguished speakers for sharing their valuable knowledge with us. Thank you everyone for your attention and participation. I would like to announce that juice has been arranged in the food counter for all the delegates. At sharp 6:30 p.m., we are going to begin the cultural event. I request all the delegates to be present on time. I repeat, at sharp 6:30 p.m., we are going to begin the cultural event. I request all the delegates to be present on time.